दोनों बाजू में। Hello, am I audible? Am I audible?
Yes, we can hear
Yes,
you.
we can hear you.
Okay, thank you.
Shall we start, sir? Respected Chairman, ISRO, Secretary Department of Space, Dr. Somanath, sir. Respected Scientific Secretary, ISRO, Dr. Shantanu Bhattadekar, sir. Respected Dr. P. Shrikumar, sir, Satish Dhawan, Professor, ISRO Headquarters, and former Director of the Science Program Office, ISRO Headquarters. Respected members from Ministries of Government of India, Dr. Jagadisha, Deputy Director, and Dr. Maria Antonita, Program Manager, Space Science Program Office, respected academicians, scientists from academia and institutes, directors of ISRO DOS centers and ISRO headquarters, my colleagues from the ISRO DOS fraternity, research scholars, and dear students. A very good morning to all of you. Today we have assembled here to set the stage for the one-day national meeting on aeronomy science with the theme Science of Near-Earth Space and Applications. Aeronomy, as we are aware, is the domain of study about the Earth's upper atmosphere, which is the first entity that feels the perturbation caused to the Earth system by the solar events. This necessitates the study of the distributed, disturbed and quiet time ionosphere-thermosphere systems at high altitudes. So in this forum, we have also invited respected members from several ministries of Government of India that deal with different various facets of our daily lives like communication, navigation, civil aviation, power, information, broadcast, and many more. From these discussions, we will get a holistic picture of how space weather affects or the space weather effects don't remain as a mere heliophysical phenomena, but also raises concerns for the earthlings, and in this context, how important is the relevance of space-based aeronomy research. This meeting will also witness the confluence of the wisdom, expertise, and experience of the learned academicians and scientists of academia institutes, as well as the ISRO DOS scientists, to bring out the conditions of the effects of the space weather and how the Earth's aeronomy study receives the first signature of this disturbance. At this juncture, I request Dr. Shantanu sir, Scientific Secretary ISRO, for his introductory note.
Thank you, Dr. Das. respected Chairman ISRO, Secretary Department of Space, directors of ISRO centers, and the chairs of the various technical sessions, Professor Shri Kumar, Satish Dhawan, professor, and he is the main force behind organizing this particular national meet. Scientists from academic institutes, researchers, and the students. Good morning and hearty welcome to all of you. As just now told by Dr. Das, that aeronomy basically deals with the Earth's upper atmosphere, which is the region of space which gets to feel the wrath of sun first before it percolates down to the lower altitudes, and is closely associated with the science of the space weather. While the main scientific objective, if you say, of the space weather studies is to understand the solar terrestrial interactions and relations, it also drives the mechanism to provide early warning for the critical space weather events, to initiate preventive actions, specifically to safeguard the space-based assets. ISRO has taken up programs specifically aimed at getting deeper and closer understanding of Sun-Earth system and allied aspects of space weather. Toward this, two satellites have been conceptualized as a twin satellite for Aeronomy mission named Disha H and Disha L, where basically H indicates the high inclination orbit, which is about 85 degrees, and similarly L refers to the low inclination orbit, about 25 degrees. Why we really require these two satellites, as you know, that the magnetic latitude and longitude play a major role in the manifestation of the effects of the space weather events, and its effect on the Earth's upper atmosphere has both latitude and the longitudinal effects. So thus we have planned the two satellites in lower Earth orbit at low and high inclination, and both the satellites will have identical set of scientific instruments. Both satellites are planned to have payloads basically for measuring the parameters of electron and ion current density, ion drift velocities, the neutral mass spectrum, and the air glow intensity fluctuations. And these missions are expected to yield space weather data, which is linked to solar activities at its peak during the solar cycle, with a near uniform coverage globally. You're also aware that ISRO is geared up for the study of Sun with its Aditya L1 mission to be placed in halo orbit around the first Lagrangian point known as L1. And the data from the Aditya L1 mission, together with these two twin satellites, Disha H and Disha L, will help in understanding the linkages between the solar activities, interplanetary propagation, and its effect on the Earth's ionosphere at all latitudes. So I think in this regard, the national meet deliberations will set the stage in the right direction for the discussions, and the meet is also structured with well-conceived lectures covering the outline of both the missions which are conceived by ISRO, the physics of ionosphere thermosphere system, its state during quiet and active sun periods, and effects during the space weather events. If you really see the entire event basically has been comprised in the 6 sessions covering the topics of these missions, the global impact of the space weather and ionosphere thermosphere system, the potential applications of space-based aeronomy studies and challenges in modeling, as well as the focus will be on the panel discussion on interministerial views for the application of near-Earth space observation from the satellites. And we are very happy to see the active participation of the scientists and academicians from IIG Mumbai, Dibrugarh University, LASP Boulder, IAP Germany, IISER Kolkata, Indore, KL University, Guntur, and many other premier institutions, apart from the participation of scientists from ISRO and DOS. And as I told, the major focus of this will be the panel discussion, where we have the nominated officials from several ministries, from communication, defense, civil aviation, power, earth sciences, information technology, and information and broadcasting, who will share their views on the need of the space-based observation on Earth's economy. So with these words, I once again welcome you all for this important event, and solicit and request your active participation of the academia, institutes, and ministries to brainstorm in order to maximize the benefit from these two proposed missions. Thank you very much.
Thank you, respected sir, for your address and setting the perspective of today's meeting. I now request respected Chairman ISRO, Secretary DOS sir, to kindly deliver the inaugural address.
Can you show the screen in the tile mode? I would like to see all people.
Yeah, you change the.
Below.
Okay. Sorry, in fact, this being an online meeting, I would like to see all your faces before I start speaking. Otherwise, it will look speaking in my own conference call. Okay. So good morning, all of you. Good morning, all those distinguished members who have joined for this meeting. I am not addressing each one of you by name. So it's a very interesting thing to participate in a meet on aeronomy research. Especially, we have been having a back-to-back meet on such interesting topics. Last week we had one on Venus mission, and now we have something on aeronomy research. Maybe the public may not figure out what exactly it is, aeronomy research. Unlike what you heard in terms of Venus, it has a great PR potential. But what I want to tell you here, aeronomy has a great scientific potential. So how we don't really realize how best this the global climate connected by the observation that we are talking about in aeronomy research, outer space, are linked in a way. And this link is something that scientists are so keen to understand and connect with the day-to-day applications of technology that are available, provided through space and other means. For example, even in terrestrial, industrial activity, that the connection is still there. So the whole objective of this exercise today is to bring all those people who are going to be connected or affected by the understanding that is going to be generated by the scientists in the coming days. In the last century or so, there has been a lot of work done in understanding the atmosphere, upper atmosphere, the phenomena related to the interaction of sun with Earth, the magnetic field of Earth, and also how it connects with the daily life of us. The whole thing started with the space program itself. We realized that when the Tumba Equatorial Rocket Launching Station was established, when we were youngsters, we were told that there is a magnetic equator going nearby. I have never come across that, but still, there is a magnetic equator nearby. And that's why the location was chosen as the sounding rocket place for understanding those phenomena which is happening up above there. And we had a different class of sounding rockets developed and launched, and world across scientists came there, conducted experiments, and it's still continuing. That legacy is still continuing. From there, ISRO has traveled quite a bit in terms of its ability to build rockets, put spacecrafts, and the interest now shifted from space-based observations rather than sounding of the upper atmosphere. Though we had ability to go even up to 500 kilometers in terms of sounding rockets, but the capacity was limited for very short duration observation. The ability that is provided by platforms like a spacecraft is a long duration observation, a consistent set of observations with the time scales. So this is the biggest gain of having spacecrafts up there. So today, when we look at this Disha H&L mission, of all those who are behind this, conceiving this idea of instruments for observation, do realize that this gives you such a fantastic opportunity to look at the phenomena happening upper atmosphere, and then conduct very useful and fruitful research that will finally be benefiting to all those who are here in the ministries. See, finally, we should not do these type of missions just for the sake of a few people's interest to understand the scientific part of it, but it should also bring that a larger segment of people in terms of benefits. So these questions are very relevant, as I have earlier mentioned. That scientific desire to know more is very, very important, and we must find a way to satisfy that, but also should find a way that it has a connection to our needs of the nation in terms of creating some knowledge base here, also connecting with the observation to some of the issues that we are likely to face in the coming days. So that way I'm very happy today. We are not only bringing scientists who are going to do research here, the people who are going to work on the satellites, who are going to deal with the data set that are going to come from the satellite, but more into the people who are will likely to get affected, like the communication, the defense people, the civil aviation, the power sector, the earth sciences, many of them, and from science and technology, those who are connected with it, electronics and information technology, broadcasting activities. So all this really has an influence from the space weather. Of course, we hear quite a bit from the work done by elsewhere in this world, because there are a lot of missions happening. And from there, a lot of information is also coming, and our scientists are connected to all of them. So we have quite a bit of data, but what is the contribution that we are making to the global knowledge in this domain? This is also an equivalent, it's a very relevant question. And that's the motivation for building such an idea, such a satellite. Now, when we conduct this national meet on aeronomy, I'm very happy that we have a lot of participants across the globe. In fact, already our Shantanu Bhattacharya has already mentioned about the participation from various countries, scientific establishment, both from India as well as from abroad. And specifically, I would like to thank all those people from the academic institutions who have a very strong scientific research background. And we also want to have more people in coming into this foray. This is also an invitation for people who are listening to this, maybe today or maybe the recorded interactions later. They will get inspired on such possibilities and research. And we would like to have good pool of people who will make use of this research outcome for their own scientific quest, also for the benefit of for the nation. So I don't want to prolong on all those details because it's all coming up in the coming lectures. There is going to be presentation on the spacecraft, also on the technologies and observations. Details will be presented by our ISRO people. And also there will be utilization part and science part will be discussed by various people. So I leave it to all of them. My goal is only in this such meet is that we must have continuously such meets in the future. It should not be limited to this satellites which is coming up. We have also great scientific missions lined up, like the Chandrayaan-3. We would like to also expose Chandrayaan-3 to the community and then look at it how this can finally benefit. We also can host a lot of instruments in our regular operating satellites. So this has been our tradition. Make use of the spacecraft for something more than that it is capable of. So that little more thing, if you can put it, it will really help all of us. In terms of the science community will be benefited, the research community will be benefited, and finally the knowledge in this domain will get strengthened. So it's an invitation, and it's a collective work to make this mission the most fruitful for the entire community. So your dialogue and discussion should be oriented towards that, to create the national view on this to be formulated. And finally, we should also drive such R&D and science missions are very important for the nation to continuously pursue. So that's a goal. I wish all those people who are taking lead in organizing all these people, especially the science program office, Dr. Das, Dr. Srikumar, Shantanu, and our directors of centers are all there. The PRL director, Dr. Anil Bharadwaj, is there. The registrar of PRL, Dr. Pallam Raju, is there, and there are other senior members. So let me greet each one of you for your time, for your participation to enthuse the gathering, and also to bring young people interested in what we are trying to do. So it should be a little more popular. I believe that whatever you're speaking should contain scientific content, but also should contain something that will go into the minds of common people. Why it is important? Because all scientists has a dual responsibility. They have to satisfy the scientific set of people and their interest, but they should communicate with the common people. They should also understand that their money is being taken to build such fantastic machines and equipments. They must also feel that yes, it is done for us as well. So let us do that task, and I greet each one of you for today's science meet, national meet on aeronomy mission, and let us make an effort to make them understand what exactly it is for public good. Thank you so much. All the very best.
Thank you very much, sir. Respected sir, for this beautiful address and encouraging us. And we look forward to the scientific sessions ahead. And it is going to start in a couple of minutes. Thank you very much for joining in the inaugural session.
Yeah, 10 minutes. Yeah, after 10 minutes, what time?
10:40. We are starting at 10:40. Okay. Good morning and welcome back to the session. We are starting the session 1, which is dedicated to the discussions on science investigations and future programs for aeronomy research. And this session will be chaired by Dr. Anil Bharadwaj, Director of the Physical Research Laboratory, Ahmedabad. Over to you, sir.
Thank you, Dr. Das, and good morning, everyone. Namaskar. I hope I'm audible.
Yes, sir, you're audible.
Okay, great. So, welcome to the session 1 of the National Meet on Aeronomy, which is focusing on with the theme of science of near-Earth space and application. This is the first such meeting of its kind to discuss more particularly the mission which ISRO is planning, called DISHA, which is a disturbed and quiet ionosphere thermosphere system at high altitude. In this session, we have two distinguished speakers talking about science investigations and future programs for aeronomy research, Dr. S. Gurubaran and Dr. Pallam Raju. Each talk is 30-minute duration. So I will give a warning for 5 minutes before the end so that you can wind up. And probably we'll take up few questions in the end of the talk. So may I now request Dr. S. Gurubaran to deliver his talk on current understanding of ionosphere thermosphere system. S. Gurubaran is a senior scientist and professor at Indian Institute of Geomagnetism in Navi Mumbai. And he has more than 30 years of experience area of ionosphere thermosphere systems, looking at this system as a whole and probing it using radio and optical instruments. Over to you, Dr. Gurubaran. Dr. Gurubaran, can you hear us?
Are you able to hear my voice now?
Yes, perfect.
I think I had muted it now. Yeah, let me share the screen.
Yeah, it was there earlier. Yes, just make it full screen, possible.
Yeah. Is it okay now?
Yes, perfect. Go ahead, please.
Yeah. Thank you. I would like to thank the organizers of this meeting, especially Space Science Office, for inviting me to give this talk.
Gurubaran, we are
There is
not
no
able to hear you. Your presentation also has gone. Guru, are you there?
Just a minute.
Okay.
This there now? Now?
Yes.
Okay. This is supposed to be an overview kind of talk on the atmosphere thermosphere system. And we already heard about the definition of aeronomy. It refers to the physics and chemistry of the upper atmosphere, including the distribution of temperatures, densities, and chemical constituents, etc. But the ionosphere thermosphere system, that concept is also not old, not new. Sometimes in 80s, this concept evolved, and I am able to. Are you able to hear my voice? My voice is clear.
Yes, yes, it is perfectly
And
clear.
the slides are there, no?
Yes, slides are there. Can you make it full screen?
I am having a problem here. It's coming and going kind of a thing. I don't know why it's, yeah. Now it's
We
full
just,
screen, right?
yes, full screen. Just change the slide to check.
Yeah, thank you.
Yes, it is working.
Yeah, the ionosphere thermosphere system, when we say it actually refers to the ion neutral coupling. As we all know, within the upper atmosphere, the neutrals and the ions actually they coexist. Neutrals are much more in number. We call that as a weakly ionized plasma. And we also know that the plasma is magnetized, and in the sense that we refer to what is called the collision frequencies to gyro frequency. In the E region, say between 90 to 150 kilometers, ions are somewhat coupled to the neutrals, electrons are not. But above 150 or 200 kilometers, both electrons and ions are magnetized, though collisions do play an important role there as well. So these motions are coupled, however, due to collisions, as I mentioned. And one species apply some kind of a drag on the other. When we have ions producing frictional force on the neutrals, we call that as ion drag, and vice versa. There is a continuous transfer of momentum and energy from neutrals to ions and vice versa. Why this study is important? Why we need to study about the aeronomy? The phenomena of our interest all takes place where the low Earth orbiting satellites orbit. The neutrals and the ions, they are continuously exposed to solar radiation and energetic particle inputs from the sun. And that being the cause of the variability, much of the variability. But when it comes to quiet times, when the sun is quiet, we still see some kind of a variability. And that is produced by waves and winds and other factors, all having their origin in the lower atmosphere. The practical application comes from the point of view of understanding the impact of the space weather or the ionospheric weather, whatever you call, on a variety of space-based application systems, GPS or GNSS, for example, and the satellite operation as well. Because as you know, the upper atmosphere responds to solar radiation. So you can look at the temperatures here, solar minimum to solar maximum. You see a solar maximum, you see larger temperatures because of the greater radiation input when compared to the solar minimum. And for these reasons,
Rubaran, we lost you. Are you there? There is an issue with Rubaran, can you hear us?
are you able to hear my voice now?
Yes, I think we lost you in between as well as the presentation.
I think it's some problem with the connectivity. I'm sorry about that.
Maybe you can just bring back your display.
Yeah, it's now clear. Its screen is there now.
Yet.
My apologies for this discontinuity. I'm facing some problem.
Not yet up. Yes, it is coming up. Can you make it full screen? Yes. Through your voice is not coming up.
I think it's going under the mute mode.
Maybe.
Every time it gets disconnected, it goes to the mute mode. I am very sorry about this. And it takes a couple of few seconds to come back. I don't know, since morning I'm having this problem. Yeah.
Okay,
Is
go
it
ahead.
okay now? Slides are seen now? Slide is seen now?
Yes, yes.
Okay. So I would prefer to keep it this way, not full screen, so that I can see you all on the sides. Is it okay?
Oh, okay, I think it's fine.
Yeah. Maybe I can. Okay. And so the fundamental processes that are important for the ionosphere thermosphere system are the absorption of solar UV and UV that sets up the thermal structure. It also photodissociates and photoionizes the species there. And the large thermal energy, part of which flows downward where it is removed. So besides the temperature profile, the electrodynamics is largely controlled by the dynamics there. I think I'm lost again.
No, you are audible. Please go ahead. We can hear you. Gurubaran, are you there? Okay, issue.
So there is a problem with the IoG network here. So is it okay
Right.
now?
Guru, can we do one thing? Can you find a better solution?
Can I come back? If you excuse me, can I come back after some time?
Yeah, I think there's only 2 talks. So the next talk is by Dr. Pallam Raju. So
I'll try to.
shall we take
settle.
that one first? In the meantime, you can find a better solution for.
Yeah, please. Yeah. My sincere apologies once again, please.
Yeah, we can understand. No issues.
Thank you.
So, Dr. Das, I think we should take Dr. Raju's talk now, and we will call Dr. Gurubaran after Dr. Raju. We have lost about 15 minutes now, but anyway, we have to do that. So, shall we go ahead with the next talk?
Sure, sir.
Okay, thank you. So, we go to the second talk of today's session. We'll come back to the first talk later. Which is on Disha H and L, ISRO's proposed twin Aeronomy mission. And the speaker is Professor Pallam Raju, who is Senior Professor and Dean of Physical Research Laboratory. And without wasting much time, may I now request Dr. Pallam Raju to deliver his talk on Disha L and H, which is the first of its kind of a mission conceived by ISRO. Over to you, Dr. Raju.
Good morning. Am I audible now?
Yes, perfect.
Okay. Thank you, Professor Bharadwaj, for the introduction. And I would like to also thank the organizers for giving me this opportunity to share with you or with the community the type of work or the Disha mission, what is it about. And I'm speaking on behalf of all the science team members, and there are various participating institutes as shown here. And it's a DISHA has already been told. It stands for Disturbed and Quiet Ionosphere Thermosphere System at high altitudes. And the broad outline of my talk is I'll just give you the motivation for this Aeronomy mission, and the talk about the scientific objectives and the experimental payloads that are planned, and the other complementary and supplementary experiments and the modeling work that is required, and summarize. So okay. So the motivation is, if you think of it, in our modern times, we have surveillance cameras in all our societies, in the cities, in the malls, basically to monitor the surroundings and also to provide warnings of any strange activity and also analyze the situation after any event that has happened. So in some sense, the near Earth space environment, which is our surroundings, it's kind of inundated by various forcing from the above due to the solar activities that keep changing from time to time, and what are called the geomagnetic storms are formed, and that has various effects on the applications such as trans-ionosphere radio communication, geonavigation, satellite hardware, the orbits of satellites, the human space activity, and so on. So the ISRO's Aeronomy satellite mission DISHA will be kind of akin to surveillance cameras in the near Earth space environment. And these satellites will provide information on the upper atmosphere during geometrically quiet and disturbed times, provide data to analyze the global effects of space weather, during this several fundamental questions will also be answered in the process of monitoring the space environment. When I say space weather, I think that's by definition it refers to various conditions on the sun and the solar wind, the magnetosphere, ionosphere, thermosphere, and these effects influence the performance and reliability of spaceborne and ground-based technological systems. And adverse conditions in the space environment can cause disruption to satellite operations, communications, navigations, and electronic power grids, leading to several socio-economic losses. So the most of the brunt of the space weather effect is felt in the ionosphere thermosphere, and that is also a region where it is it is kind of intermixed with various extremes in terms of transitions in temperature in the lower thermosphere region. The atmospheric mixing changes from well mixed to a diffusive equilibrium. And there are a lot of spatial and temporal anomalies in terms of plasma densities and neutral densities and temperatures, which are again coupled to one another. And as I already said, this is the region which receives the brunt of the adverse effects of the happenings in the sun and between the sun to the earth. And there is, in addition, the ionosphere thermosphere region is also has an effect from the lower atmosphere in terms of gravity wave breaking, etc., that I'll just talk about. So as these disturbances are global in nature, it is essential to investigate the various elements that are affected by the space weather. And this is a kind of broad summary plot wherein you can see that sun, which emits the magnetic fields, solar photons, UV radiation, and particles. And in terms of, the magnetic fields interact with the magnetosphere, and the photons give rise to ionosphere and thermosphere. Thermosphere is neutral component, and ionosphere is formed out of the thermosphere, which is around 3 orders of magnitude less in densities. And in terms of radiation, so these are have these effects in this. And as far as the marks, the things that are marked in the red are concerned, these are the applications aspect. Is the one might have seen the beautiful aurora, but underneath it, it's actually the formation of several currents, which give rise to reverse currents on the ground because of induction, and then power grids get affected. Once the ionosphere is formed, there are the variations in the densities will give rise to will adversely affect the radio communications. The increase in densities cause the satellite drag, and with more human activity in space, these radiations have an effect on the humans that are orbiting in the space. And in terms of the things that happen in the ionosphere thermosphere region, once the heat gets generated in the particle due to particle precipitation high latitudes, both in north and south hemispheres, this temperature gradient forces give rise to traveling atmospheric disturbances or traveling ionospheric disturbances. They move towards the lower latitudes, which lower latitudes and equatorial latitudes are highly dynamic in their own way in terms of electric fields and currents that are generated over equatorial regions, which gives rise to several phenomena, several anomalous behavior in terms of neutral densities, particle plasma densities, temperatures, winds, and and then all these get affected due to what is called due to the space weather effect that we are discussing. There are on several locations in the nights, there are what are called the plasma irregularities get developed and plasma bubbles get developed. And you can see this is a global picture of the most probable region where the plasma scintillations are maximum. So it is around the equator, magnetic equator. You can see this is different from the geographic equator. And along the magnetic equator, you can see this is where, in our tropical regions, we all are affected because of these plasma irregularities that get generated. And this is these effects in the low latitude. This is a range time intensity map from our own Gadanki MST radar, which really clearly shows that there are plasma bubbles, plumes at 3 meter irregularities going up to 600 kilometers in altitude. And the interesting part is that this kind of behavior is independent of solar activity. So solar space weather activity does create a lot of issues that we are interested in and we need to understand. But in the low and equatorial latitudes, we have a problem of our own in the sense that these features can occur irrespective, in spite of even though solar activity is not strong enough, and also in the lower solar activity regions. So in just what I have been talking about is that this is the region, ionosphere thermosphere region, which refers to the ions and plasma and neutrals. And this is forcing from above, and then from high to low latitudes is what we have seen. And there is a component which is the forcing from below, in the sense that there are a lot of waves in the lower atmosphere, and which are formed because of the orography differences, land-sea contrasts, hill and terrains, and temperature differences, and various other wind systems that take place. And these waves they go up in altitude, and because the neutral density is decreasing exponentially, to conserve energy, these waves have to increase in amplitude as they increase, but they can't go on increasing indefinitely. And they break at some region around 100 kilometers, which is the turbopause. And there are secondary and tertiary gravity waves created around that region, again, by which process there is a lot of momentum and flux is released from the lower atmosphere to higher altitudes. And these secondary and tertiary waves generate generate waves which can affect the upper atmosphere. So this is the coupling from below in terms of the lower atmospheric forces. And there are other factors like space stratospheric sun warmings, which also have an effect from in the stratosphere region. So they have a coupling to the low latitudes. So the scientific objective of the Disha mission is how do these neutrals and plasma in the Earth's ionosphere thermosphere region respond to varying space weather influences at different latitudes and altitudes. So for that, we need to quantify the structures of various scale size of waves from tens to thousands of kilometers. that get developed in the upper atmosphere during both space weather disturbances and quiet times. And to obtain the plasma waves that I showed you, one of the example from RTA instability, that is at one particular wavelength. But then there are waves of different scale sizes, right from few meters to hundreds and thousands of kilometers. So those we need to generate a map of the whole distribution around the globe. We need to quantify the neutral electron density characteristics due to plasma fountain effect. This is another low latitude feature which refers to the larger electron densities on either side of the equator, and that's where the plasma scintillation occurs. That the kind of two bands around the globe that I talked to you about. And in terms of high latitudes, there are various features like plasma cap patches, magnetospheric cusp, storm enhanced density or mid latitudes. So these are all space weather effects which have an effect on the whole aspects in terms of our applications. And the lower atmospheric effect in terms of cyclones, tsunamis, stratospheric sun warmings, all these give rise to large-scale waves which go up in altitude and have an effect in the ionosphere-thermosphere region. So with that with that kind of broad background, Aeronomy satellite mission Disha will yield the required information to answer fundamental science questions relevant to space weather effects on terrestrial upper atmosphere. And this is a twin satellite mission. One is with an inclination orbit of greater than 85 degrees. Other is a 25-degree inclination orbit, and both of them will be orbiting for around the scheduled plan is of around 5 years with a common periodicity of common duration of around 3 years, and these will be at circular orbit at 400 kilometers, and the kind of the measurements are plasma structures, neutral densities, neutral airglow emissions. Airglow emissions are nothing but the emissions from the upper atmosphere, which gives rise to the information on the species that generate them. So we'll be observing different airglow emissions, which will give information on different species, and soft X-ray emissions, plasma drifts, electric fields, and plasma waves. So these are in terms of spatial resolutions vary from tens of kilometers to above, and again temporal resolution will be of the order of, again depending on the instrument, from few seconds to minutes. So these are the Disha H will contain 7 payloads, and this is the high frequency Langmuir probe, which has with the parameters that will give electron densities, the relations and the percentage enhancement or variations in electron densities, amplitudes of plasma waves. And I'll show you that such a Langmuir probe has never been flown in any satellite mission so far around the globe. And this will give first synoptic picture of plasma scale sizes, again as I said, from tens of meters and beyond, both under quiet and disturbed times. There's again another airglow photometer. It's narrow bandwidth and narrow field of view, which will be operated 2 wavelengths that originate from the upper atmosphere, and that also has not been flown before, and that will give an imprint of the space weather signatures on the upper atmosphere on global scale. And a drift meter, which consists of a retarding potential analyzer and a drift meter. It's a combination, and which will yield ion drifts, bulk motion of plasma, major ions, concentration, ionospheric ion temperatures. And this is for the understanding the dynamics. This will form the backbone for understanding the plasma processes in the ITS. And electric fields can be derived without the use of long booms. And we'll be able to generate global maps of the equatorial electric fields, which are the primary drivers of various phenomena in the low latitudes. Neutral mass spectrometer will give neutral composition from 1 to 300 AMU, and ion mode is also getting planned. And this will give information on the various spatial composition effect and also neutral densities around the globe. Continuing on, we have another instrument called the Upper Atmospheric Visible Airglow Spectral Imager, URVASI, and it will have a large coverage of between 530 to 780 nanometers, and it has two channels, one high resolution and one larger coverage. It will give global maps of sodium emission lines, which will be obtained for the first time. And they will also be used to obtain the O by O2 ratios, which have space weather implications, and simultaneous information on wave dynamics from mesosphere to thermosphere will be planned. The electron temperature analyzer, which will give rise to electron temperature and densities, and it'll capture the information on electron temperatures and during plasma fountain and low latitudes, manifest with cusp at high latitudes. AXIS, which is auroral X-ray imaging spectrometer, which will have a coverage from 0.3 to 2 keV, and it will be first spectroscopic observations at soft X-rays in the terrestrial atmosphere, which has again not been that kind of measurements are not existing so far. Just a brief about each of the payloads. The Langmuir probe, it is it looks like this, small tip there, but there will be a couple of Langmuir probes will be flown, and which will give rise to the measured fluctuations in electron density and not inferred. That has done been before. And a lot of several experiments have been done with this Langmuir probe, and will give because of unique guard electrode, it reduces the time constant, and it has kind of measurements from very small time scales, from spatial scales, from 2 to 8 meters. And it is extremely important to understand the energy cascading process. And 2 probes will be deployed, one to perform the sweep, the other to give the plasma potential. So in the spacecraft, potential can be obtained. The other one is the air glow photometer, which will be operated in 45-degree angle separation, which will measure 2 wavelengths, 630 and 7774 angstrom region. And then this is a typical example of how it looks when they are separated by 45 degrees. If there are evolving structures in plasma irregularities, you'll see the time shift. This is x-axis the time, and the y-axis the intensities. And if there are magnetospheric disturbances are there, you can see both of them from 2 different directions showing the same behavior. So that is an indication of the space weather effects on the induced fluctuation. So this is a typical part of the ZIMAX design of the instrument. Drift meter, as I said, it consists of it's a kind of couple here. It's RPA and drift meter together, and it consists of it will give rise to mass. It will give information on mass range from 1 to 40 AMU, which will cover major ions. An energy spectrum of the thermal ions in the vehicle frame of reference will be obtained. Ion temperature will be obtained, and based on that, we'll get the V parallel, the direction of drifts along the direction of the satellite. And there is the next suit is the drift meter, which is kind of different in structure, in the sense that it has 4 detectors electrically isolated, and where the satellite motion is greater than the ambient ion motion. So that's the ion motion is considered to be can be considered to be a collimated beam. So the ratios of the currents obtained between A plus B and C to D will give rise to the one of the V perpendicular the other direction, and A plus C and B plus D gives rise to other orthogonal direction information on the direction of the ion velocities in the other direction. Neutral mass spectrometer. This has has a long heritage. It has been flown in the past in various missions. And in terms of moon impact probe in Chandrayaan-1 and Mars and Chandrayaan-2, it has a mass range of 1 to 300 AMU, and it can give up to 10 raised to 2 species the density wise. And this is details of its working. I'll not talk about at this point of time. This is Urvasi in terms of this has a large wavelength region as a coverage, as I told you. from sodium to oxygen green line, red line, 7774, O plus 732 nanometers OH, and it will be looking at the forward limb. And this has a different resolutions, 0.1 nanometers for sodium studies specifically, and for synoptic picture, the larger 0.5 nanometers. And it will has a altitude resolution of 2 kilometers, and it will give information on what is happening between 80 to 500 kilometers. Electron temperature analyzer, it has got, it will give electron temperature, electron energy distribution, and it will be located in the RAM direction. And it has two probes, gold coated planes composed of two semicircular discs, as is shown here, which are electrically insulated by around 10 millimeters here. And in the one of the hemisphere is subjected to floating variation in sinusoidal wave with respect to the other one, and it yields the temperature in that fashion. And these are some of the tests that are going on with this particular breadboard model. Axis is a soft X-ray, gives us a soft X-ray spectra, and this it looks in the nadir, it looks in the downward direction, and being the albedo in the X-rays is almost negligible from the Earth, almost zero, so you can see the X-ray emissions coming from in both in the day and night time, so about greater than 55 degrees, where the particle precipitations are maximum, as I told you in one of the earlier slides. That's where the software X-rays are produced, and that's what this X-rays will detect. And the spectra of the soft X-rays in auroral arcs will be obtained, and the charge there is also in terms of magnetosphere solar wind interaction with the magnetosphere, the kind of charge exchange processes will be obtained by this instrument. And when the solar flares that they occur, we'll be able to get X-ray fluorescence and scattering over low and equatorial latitudes during the solar flares. So this is how it looks like in terms of the placements. These are Langmuir probe, neutral mass spectrometer, drift meter are all in the forward limb, and also electron temperature analyzer. The Urvasi is in the forward limb, and AP it will be in the side in terms of pitch view, pitch direction in the limb view, and axis in the nadir. And because of the requirement that several of these instruments have to be facing RAM direction all the time, so the satellite team at URSC has come up with a very innovative design wherein this whole thing is placed on a rotatable deck or platform, so that the scientific payloads that are facing in the RAM direction are maintained for long duration in spite of the periodic maneuvers of satellite that are required. And Disha L doesn't require that kind of table or the rotating table. And these are the instruments. These are 6 here, except for Axis. All the others are here in this particular Disha L. So each of these experiments can provide new and standalone science results, which I have not talked about here for want of time. But in combination, several more science issues can be solved and discoveries made. Thus, in the words of Aristotle, the whole is greater than the sum of its parts. So, as was also discussed earlier, the effects that take place for real in the near Earth space to understand, we need to understand what is happening at the Lagrange point, L1, and ionosphere thermosphere regions. And as I already told you, that ionospheric space weather can be independent of the occurrences of the disturbances on the sun. And this is all latitudes. The plasma irregularities is an example I had given you. There are other things like Perkins instability or mid-latitudes that also happens irrespective of the space weather events. And there are, of course, other internal processes, which are in terms of stratospheric sudden warmings, wave force structure, wave coupling from below, which are also again independent of solar storms. So ionosphere thermosystem is kind of sandwiched between the forcing from above and from below. So this is the domain of the research which that Disha will carry out, taking inputs from other missions in terms of solar effects and interplanetary effects and magnetospheric effects. But what all effects that I talked to you about touched upon here are in terms of high latitude, mid latitude, low latitude processes. So this is the domain of Disha's interest, Disha's focus. So it is with this appreciation that the twin Aeronomy satellite mission Disha has been conceived. Experiment on board Disha will address the space weather effects in upper atmosphere, which are both internal and external. And based on the assimilation of data from Disha, several aspects of applications will be addressed. So to give a broad summary of the things that I talked about, I started with the science objectives, which are in terms of quantifying the structure and various scale sizes of waves. And for that, the required measurements are optical emissions and neutral plasma parameters. That will be accomplished by the instruments here, which are NMS, LP, DM, AP, Urvasi, and ETA. And the data products that will be generated by these instruments are the airglow emission intensities, neutral densities, composition, and major and minor, major ion densities, and which will in effect answer the question that we set off to address to begin with. In the same way, distribution of plasma waves, ion drifts, electron drifts, and temperature during space weather conditions will be to understand this, we require electron density variations, amplitudes of plasma waves, major ion densities, ion drifts, electron temperatures, which will be provided by these instruments, LP, DM, and ETA. And the products are this in terms of what are given here, which will address the question that we set off to begin with. And in terms of quantifying the neutral and electron density characteristics due to plasma fountain and plasma cap patches, as I said, the lower atmospheric coupling, lower atmospheric effects also have an effect on this, which will be required measurements are all the measurements that are there in Disha, and all the instruments will be involved there. And so in that way, one can get a broad overview of what are the questions that the objectives that we set off to understand, and the required measurements, the instruments used, data products, and to answer the question finally. Obviously, yes.
Raju, 2 minutes.
Yes, I'm done. Obviously, this whole thing will require, just the satellite, but also several ground-based and space-based missions will be required to be complemented by other ground-based techniques, which are several on the ground, and also will be touched upon in later talks. So I'll not talk about those things at this point of time. Modeling also is an important aspect that will be required to be done finally to really understand comprehensively as to what is happening. And data from missions such as Disha will help in providing the required information. So to summarize, the upper atmospheric regions that get adversely affected due to both solar forcing and internal dynamics in the ITS has been described. Twin satellite mission Disha is planned with 7 payloads, and Disha H&L will yield critical information on structures in plasmas and neutral parameters which adversely affect radio communication navigation aspects. With increasing space missions from ISRO in geospace, it is important to gain fundamental understanding of the ITS, and Disha will yield new insights into the ITS and show new directions, the Nai Dishaएं, in terms of broad understanding of the space application aspects of space weather effects on ITS. So with that, I thank you for your patience.
Thank you, Dr. Pallam Raju, for an excellent overview of the Disha LNH, summarizing the instruments, the parameters which these instruments will observe, the capability of each instrument, and the science which is going to be addressed by this Disha. I don't know whether there are any questions in the chat box. If the organizers can help me. Is there are any questions in the chat box or anywhere else? Dr. Das?
Yeah, we are checking.
No questions in the chat box.
Yeah.
I think the talk was very clear, and it is actually an overview talk to tell the community what is the capability of this Disha mission. And I, on behalf of everyone, is requesting the community to join this mission, because this is going to be the first of its kind where we have two missions, one in the low Earth orbit, one in high inclination orbit, looking at the aeronomy of the planet Earth. So with this, I would like to thank Dr. Pallam Raju for this talk, and we now go to the next talk, which is actually the first talk of this session, by Dr. Guru Baran. Guru Baran, are you there? Guru,
Yes. I think you are able to hear my voice now. Yeah.
Yes, perfectly well. I hope your connection is also stable now.
Yeah, I think sorted out.
Take your talk now. Can you share your screen?
Yes.
For those who have joined us late, let me tell you that we have to switch the talks. So we are now going back to the first talk of this session, which is by Dr. S. Guru Baran from Indian Institute of Geomagnetism, Mumbai.
You are able to see my slides now?
Yes, perfectly well.
Okay. Thank you. And once again, my sincere apologies for not getting through. There was some problem with the network connectivity. Hopefully, this time I will not have any issues.
Only
Dr.
request,
Pallam Raju has already.
Guru, only request is
Yes?
that I will cut you short a little bit, so maximum 20 minutes.
Yeah, I am about to say that. Yeah, I'm about to say that. Dr. Pallam Raju has already spoken a lot about the physical processes, both at high latitudes, low latitudes, and also the phenomena taking place due to the solar radiation and the particle precipitation and the other high latitude influences, as well as the lower atmospheric forcing and so on. I think he had already set the tone right for providing some kind of justification for the Disha missions, and also he has given an overview of the various payloads and the scientific objectives. So I may not take more than 5 minutes. Maybe I'll just quickly. I deleted some slides as I was listening to Dr. Raju's talk, because I didn't want to repeat. So I'll make it short. No point in repeating the same thing, because both of us we all think the same way, and our thoughts and thinking processes are all same. So I don't want to repeat. Just maybe a few processes here and there I'll just touch upon, and I'll conclude. So this I will skip this. And when it comes to dynamics in the ionosphere thermosphere system, there are all some very basic stuff, because the winds are the ones which drive or generate electric field through the dynamo, and also winds are largely responsible for the upper atmospheric variability. And so it's very important to measure winds. And what are these winds due to? We can have quiet time winds on one side and the disturbance winds on the other side. Quiet time winds essentially during the normal times, they blow because of the unequal heating between the day and night, also between the summer and the winter, what is called the annual tide or the diurnal tide. Now these basic tidal components, the tidal modes, now they respond to the variability from below in the form of atmospheric waves. And those waves can have periods in the range of minutes to tens of minutes when it comes to gravity waves, and several days when it comes to planetary waves. So as I was mentioning, also these waves, these tides, during the quiet times, when they blow the ions across the magnetic field, they produce some kind of an electric field. And these electric field, the basic or the primary electric field, what we call, is largely responsible for the quiet time electrodynamics of the low latitude ionosphere. Any variations on that, they could be either due to forcing from below in the form of waves or forcing from above. This is what the essential framework that we need to understand. And of course, the winds, the neutrals and the ions are coupled, so winds can undergo a drag in the presence of plasma and vice versa. So when it comes to disturbance winds, so we have particle precipitation in the high latitudes, and also penetration of electric fields, magnetospheric electric fields into the high latitudes, and that can cause some kind of a heating, a warming, and a direct circulation can be set up there at a high latitude. Can also drive large-scale winds into the system. And these winds can carry the ions and the neutral species, and they can affect the composition. So by means of energy S and by means of electric field S, these solar originated disturbances can reach the ionosphere-thermosphere system. And when it comes to tides, as I was telling, the tides are essentially 1 minus 2 kind of basic, the background solar-driven component. On that, we can have a superposition of wave components coming from below. One of an important tidal component which is coming from below is the what is called the dynamics, the diurnal eastward propagating wave number 3 tide, that is essentially set up in the lower atmosphere due to convective forcing. So we can see here that besides the wave number 1 diurnal tide at about say 90 kilometer altitude, we also see a wave number 3 kind of tide, which is coming from below. So this is a direct evidence to confirm that we have a wave propagating from below, and these waves have been shown to be generated in convective forcing. So this wave number 3 tide can induce a wave number 4 pattern in the low latitude ionosphere-thermosphere system. A number of parameters have shown this kind of wave number 4 structure, starting from the image satellite results by Imel et al., where we see the electron density with respect to longitude producing a wave number 4 structure. There is also neutral mass densities at the same altitude of 400 kilometers producing the wave number 4 structure. Besides that, in the ionospheric dynamo region, where we have this electrojet current flowing at low latitudes, the reversal of the electrojet current, the normal current, can be explained now, it seems, by the diurnal eastward propagating 3 type, especially in the climatological sense. These are all from the timed satellite results. And the paradigm shift that occurred in the early 21st century, the turn of the century, was that we have the background upper atmosphere, which is forced by the solar radiation. On that, we have a forcing from above and forcing from below. This schematic shows the wave number 4 kind of structure is seen in a number of parameters. You see these convective clouds having wave number 4 structure. It essentially reflects the ocean-land distribution on close to the ground. And this distribution can set up non-migrating tides, so DE3 tides or SE2 tides, and they can cause perturbations in the E region and all the way to the F region at 250, 450 kilometer altitudes. A number of parameters, satellite and as well as ground data, reflected this kind of a wave 4 signature. I think another aspect is the sudden stratospheric warming. There has been a considerable interest in a couple of decades or so, where a disturbance at the high latitudes in the stratosphere can cause perturbations in the ionosphere at low latitudes. In this, both TEC as well as the ground magnetic field variations have been used to show that the SSW, sudden stratospheric warming, can have some kind of perturbations that can produce some kind of a perturbation at low latitudes. And one more phenomenon that is important is the medium-scale traveling ionospheric disturbances, MSTIDs. They are also now gaining a lot of attention in recent years because of the kind of weather of the ionospheric weather they can induce, changes in the ionospheric weather they can induce at ionospheric altitudes. They can be seen during the daytime as well as during nighttime, and more often they are seen in at mid latitudes in sky images. But in recent years, we are seeing this kind of a signature at low latitudes as well. One example from NARL Garanki, where this kind of a signature was seen at very low latitude. So though the features seem to be different, and perhaps we need to look into the mechanisms that are responsible for this. Though because very close to the equator, the Perkins instability may not operate. So you must be looking for some other mechanism. So when it comes to low latitudes, I think these have also been discussed well by Dr. Raju. Perhaps I will not go through these details. This is the last slide. The ICON has been bringing in a lot of insights, have been throwing so many newer insights because they have two instruments. One at say about 500 to 600 kilometer altitude, making in situ measurements of drifts, iron drifts. Then another remote sensing instrument that is looking down to say altitudes of say about 100 kilometers, looking at the airflow emissions there. And so they make simultaneous observations. Winds there at lower altitude, say about 100 kilometers, and in situ measurements there at say about 500, 600 kilometers. I think this is what has been lacking all these years. Why we could not track, or why we could not understand the day-to-day variability was essentially simultaneous measurements from different altitudes. So if we have wind perturbation at say about off the equator and producing some kind of a perturbation in the electric field, these perturbed electric fields can map all the way to the ionospheric F region over the equator, and they can induce changes there. So we can directly look into the cause of those changes at the ionospheric altitude. So these very exciting results are coming from the ICON satellite mission. There are also attempts now to address the day-to-day variability using the ascending and the descending orbits of the ICON satellite. Exciting results are now coming from that. Now with Disha coming up now with the two simultaneous satellites and with a suite of instruments, very interesting array of instruments. So definitely we'll be looking into some of the challenging problems that I mentioned, and also Dr. Raju had mentioned earlier. And so I think exciting times ahead, and so a great promise ahead. Thank you very much.
Thank you, Dr. Gurban, for an excellent talk summarizing the science issues as well as our current understandings, how this can be taken forward with help of the Disha mission. I believe there have been some chats going on and as well as answers being given with respect to the previous talk as well as this talk. There are any questions which need to be answered by the speakers, may please be brought by the SPO, the speakers right now, because we still have 3 minutes left for the next session to start. And thanks to Guru for trying to cover up the lost time.
Sorry about that.
Thank you so much. Is there any questions which need to be answered by any of the speakers?
I think there are some questions in the chat box. Yeah.
Just trying to look at some of them.
There is one question for Palam Raju, sir.
Yes, what is that?
By Dibendu Nandi. Is there a plan for joint coordinated observations with Aditya L1, perhaps joint working groups, if Disha is funded? One can very easily put together the in situ plasma environment measurements at L1 from Aditya L1 with the Disha observations at LEO to establish causal connections between solar activity and ionospheric perturbations.
Yes.
Yes, Pallam.
Yes, sure. There will. Yes, sure. There will be definitely joint coordinated works once these two missions are on. Absolutely, there's no two questions about it, because one is giving the cause and other is giving the effects. Okay, Aditya L1 mission is measuring what is happening on the sun and the causes for the space weather, and Disha will be telling us what is the effects of that space weather on the ground or in the terrestrial environment. There should be, in fact, in one of my slides also I said that the L1 mission data also will be used, in terms of simultaneous observations. Definitely, yes.
Essentially, what it means is that there will be ground-based observations, coordinated observations along with the mission, as well as Aditya.
Aditya mission, yes.
Yeah, I think there is another question for Guru Baran. At Disha's orbit, there are both solar wind as well as lower atmosphere dynamics which acts together. Are there models which account for both through coupling, plasma models with neutral atmosphere? I think this is again by Dibendu Nandi. Guru?
Yeah, yes, of course, the same instruments can look at what is happening on the sun and their effects at those altitudes. They can also look at phenomena or waves or wave disturbances coming from below. When the sun is quiet, we expect some kind of a quiet time weather, space weather. There's a naturally induced variabilities. And when the sun is active, we see those disturbances, solar or sun-related disturbances superposed on the quiet time variability. When it comes to models, of course, there are general circulation models that pull the climate-related forcing into the upper atmosphere. And those models, they need some kind of an input at the lower atmosphere, some kind of a forcing at the lower atmosphere. If we can somehow identify those forcings and then feed into that those general circulation models, they can give rise to the events or the features that we are looking for. Of course, the sun-related solar wind and radiation and particle precipitation are related inputs that are already incorporated in those DCMs. What we need is information regarding the lower atmospheric forcing. Then everything is taken care of.
Okay, thank you, Guru. There is one more question from Rajneesh as MCF. If the orbit of Disha H and L is slightly eccentric, for example 400 plus minus 50 km, then the in situ measurements for each orbit at different altitude is possible. Any such thing is envisaged. I think this is aimed to Dr. Pallam Raju.
Yes, there have been, I should say here that there have been missions with eccentric and varying altitudes. And the difficulty there had been in terms of deciphering or delineating the altitude versus the latitude effects or the altitude effect especially. So we wanted to reduce 1 degree of freedom by proposing this method, and also we have to be in a with the varying, because it's a long duration mission. So we have to be in the thick of the happenings, so to say, with the whole duration between low solar activity and high solar activity also. So that's why circular orbit, in that sense, again is a unique way in which this addresses that issues.
Okay, so essentially what you're trying to say is that circular orbit is more preferred because of the science which it is going to address. But at times, if required, we can try to have an elliptical orbit if the mission allows later on.
Okay. Yeah, sure.
Okay, I think we are already overshooting our time. Yes.
So we have a question from Dr. Shekumar. A quick question, is that okay?
Yes, Dr. Shekumar.
Yeah, this is to Dr. Pallam Raju. You had indicated the possibility of the mass spectrometer was also looking at ion mode. RPA was also has up to 40 AMU coverage for looking at mass spectrum. And I was just wondering, if you were to compare either the sensitivities or capabilities of these two in that 1 to 40 AMU, do you have any comments on where each of them stand? Just trying to see, should we really go for a cross-calibration requirement given the commonality of the AMU range?
Yeah, I think that the ion mode is getting developed, by understand from the PI. The NMS is already there, so they are trying to augment it to make it more. Once more information is available, once more tests are done, definitely we can try.
Is there any comments from the SPL team on that? When the ion mode, they've already demonstrated partially, I thought. Just curious to know. Tarun?
Anyone from SPL?
Okay, don't worry, we'll take it up later. I just also wanted to have a quick comment. Dr. Bharadwaj, if you recall, 22 years ago, I think, we had a space generation task group, which had a science group. You were there, we were there, Rajiv was there, and Dr. Sita and others. And our current chairman was overall leading the program. I just remember that you had proposed a twin satellite. Now, after 21, 22 years, you're actually seeing the realization of this system. So thank you. Just wanted to inform others.
Thank you, Dr. Shikumar, for reminding and remembering those things. I too also remember that we are talking about this twin satellite not only around Earth but also around other planets too. Great, thank you very much.
Just 1 minute. We have a quick comment from Tarun about
Yes,
processing.
Tarun, please go ahead. Please.
Yes, it's regarding the cross-calibration possibilities of using the ion mass spectrometer, the ion capability, and our PA. Definitely, this will in the lower mass range we can have a cross calibrations, as Dr. Pallam Raju indicated. Once our capability, right now we are trying to increase the efficiency for the ion mode. So once that capability is added, I think it will be a good thing to do. We'll definitely attempt it.
Great, thank you. Thank you, Tarun.
Yeah, thanks.
I think the last question before I end the session is from Ankit Kumar, who's asking, can we find out the transition height of the ionosphere to plasmasphere by Disha mission? Pallam?
I think the answer to that is that we have aimed to be in the ionosphere. Okay, that is the whole focus had been, because to go higher altitudes it's much easier, but to be in the altitude range where the plasma densities are at least 10⁻³ and 10⁵ to 6 range. So that's what our focus, our effort had been, and luckily, we had the ISRO and the decision makers had been very good enough to kindly agree to that particular altitude. 400 kilometers will not be able to see the transitions because plasmasphere is much higher.
Okay, I think so. Essentially, what Pallam is telling is that our focus is more on the lower atmosphere in terms of the height of the plasmasphere. So we are looking at processes which is happening closer to the Earth. I think with this, I would like to thank both the speakers for this session, for wonderful talk, as well as replying to the queries and questions of the audience. And I would request all of you to take active parts and continue to have discussions with all the speakers as well as the PIs of the Disha mission. With this, I will hand over to SPO, Dr. Das, to continue on with the program.
Thank you very much, Dr. Anil Bharadwaj, sir, and thank you very much for having driven this session so nicely and having made it so lively. And thank you very much, Dr. Guruvaran, sir, Dr. Pallam Raju, sir, for this excellent presentation and also for this vibrant introduction. And we understand this is just a beginning. And with this lecture, the discussion will continue. And thank you, thanks to all of you. Before we go to the next session, which is session 2 of this national meet, dedicated to the discussions on the global impact of space weather processes on the ionosphere-thermosphere system. This session will be chaired by Dr. S. Guruvaran, IIT. Over to you, sir.
Yeah, let us start this session. The first speaker is Dr. Divendra Nandi. I think his slides are already there. Please proceed, Dr. Nandi.
Can you hear me, Guru?
Yes.
Okay, all right. So good morning, everyone, and thank you to the Space Program Office for inviting me to give this talk, talking about space weather connections and its manifestations near Earth. So I'm representing a team from the Center of Excellence in Space Sciences, India, at ISRO Kolkata, where about 10 years back, we established a multi-institutional center involving various institutes, including ISRO, with one of our primary goals being the development of indigenous space weather forecasting capability. So in today's talk, I have contributions from scientists and students who are listed there: Shobhik Roy, Yoshita Barua, Subhadeep Sinha, Arnav Boshak. And I'd also like to acknowledge some discussions that I had with Pallam and Dibyendu Chakraborty from PRL regarding some details of the Disha mission. So what you see here in my first slide is a dynamic event, which is a solar filament eruption associated with a large-scale ejection of plasma from the sun. The sun, which is our host star, is in fact an active star, and the variability of the sun impacts the near-Earth space environment, including the satellite technologies and other technologies that are dependent on space. And I would like to give an idea today of why it is important to understand and assess space weather. The plan of my talk is the following. So I would like to briefly cover, in a very general way, which is understandable to everyone, what is space weather and what governs space weather. I will highlight the impacts that space weather has on modern human society and our space-based technologies, and discuss how advanced nations like the United States and the European Space Agency, the European Union, are dealing with space weather. I will talk about why understanding space weather is important for India in the national context, and highlight the Aditya L1 mission, which is under development and will hopefully be launched soon. And I will also briefly talk about the Disha mission and what it can do in terms of establishing causal connectivities between solar events and its manifestations near Earth. And finally, I'll talk about some indigenous capabilities of space environmental models and forecasting that we have developed at SESI at our space weather prediction laboratory, and how we can utilize this to support such missions. So the sun has a magnetic cycle, and this magnetic cycle typically is an 11-year cycle. And often you see this emergence of active regions or magnetically strong regions on the sun, which emit radiation in high energy, such as extreme ultraviolet and X-rays. And often these active regions on the sun also become destabilized. The magnetic fields associated with these active regions become destabilized, and they give rise to solar storms. But before coming there, let me just point out the connection between the solar activity cycle, the magnetic cycle, and the radiative output from the sun, because this has some climatological consequences. So what you see here on the right-hand side, the bottom plot is the variation in the number of sunspots, which are the strongly magnetized regions on the sun. On the top, you see the total solar radiation that arrives near Earth orbit per unit time, per unit area. And you see, in fact, that is not a constant, that is a variable. And that variable is...
You may have to move the slide. You may have to move the slide. I think your slide is not changing, I think, right?
Okay, so slide is, let me try this again. Do you see the slide changing or no?
No.
No? Okay, let me,
yes, now it is changing.
That's strange. So in full screen mode, it is not changing. Is it changing now?
It is the plan of this talk, which says, this slide.
Did it move beyond that?
No.
Okay, let me stop sharing and reshare. I don't know what's going on. Okay. So usually full screen works. Do you see the slides changing now?
Just a second. It does not yet come. Yeah, the Soho ESA. Yeah.
Now it's changing. You see the next slide?
Yes. Yeah. Now it has changed. Now
is that the total solar energy output measured at Earth orbit. And one of the important things to figure is to figure out what are the distinctions between anthropogenic and natural solar-driven causes of climate change, which is an important area of research. Sometimes these magnetized active regions on the solar surface become destabilized. And when they become destabilized, the magnetic energy associated with them is released to heat up the plasma, which radiates in high energies, and then you have X-ray flare, and it accelerates particles and plasma out of the sun, which can then travel out and impact the near-Earth space environment. The energy content in each of these solar storms, on the average, is about 500 million nuclear explosions at the same time. That's the energy equivalent of each of the solar storms, and that tells you the humongous amount of energy they carry. And when they're Earth directed, they can result in severe space weather at Earth. What you see here is a coronal mass ejection, which often results from a very strong flare, where a large part of the corona is ejected out. In fact, this storm happened last year and arrived during Diwali, and we actually successfully predicted this storm, and this we had dubbed the Diwali solar storm. And our successful prediction of this storm arrival was in fact highlighted in various papers during the time as well. What happens is this, that when the solar storms occur, because of the energy that it releases, this high energy solar energetic particles can arrive at Earth orbit and impact the sensors of satellites. It can impact human health, astronauts, and give rise to anomalies in different satellite sensors. They also, when they impact the Earth's upper atmosphere, give rise to this beautiful phenomena known as auroras. And in fact, during the solar storm last year, there were significant auroras which lit up various high latitude countries. And you see a report on this here. Why should we worry about space weather? Guru, I hope that my slides are changing and you can see them now.
Yes. Okay. Please go ahead.
Okay, this slide is very important, particularly for the agency representatives who are here. Let me first take on the polar regions. Often people say that only people who are living in the polar regions, countries in the polar regions, high latitude, should be worried about space weather and not us. Let me debunk that myth. We have airlines now which fly over polar routes, because you want to fly over New Delhi to New York, you want to go over a great circle, which minimizes the fuel content, and that means you have to fly over the poles. The polar regions are susceptible to space weather. And what you see here in this small subplot is that since accurate space weather predictions became available, the number of polar routes also opened up, and more polar flights have started happening. And these flights actually do conform to space weather predictions. And whenever there is severe space weather, they do avoid the poles. We are dependent on various satellite-based technologies. Our telecommunication systems, our navigational systems, satellite broadcasting systems are dependent on satellites, which are all subject to space weather. In fact, there are GPS navigational anomalies, positional errors when there is a solar storm or a geomagnetic storm. I will not go into the technical details of that, but this is something that affects each of us who carry a cell phone and are trying to navigate or are trying to communicate. If you are in a high latitude country and you have a large conductor like electric power grid or even an oil pipeline, when a solar storm induced geomagnetic storm occurs, large currents or voltages are induced which can trip power grids. In 1989, the North American power grid in Quebec was taken down by a solar flare, and Quebec and Montreal was out of power for a couple of days. And this tells you how strong the impacts of a moderate level flares could in principle be. Very recently, the SpaceX Starlink satellites, 40 of them, which were launched on 3rd February 2022, were lost due to a geomagnetic storm which was induced by a CME hitting the Earth's atmosphere. And this resulted in joule hitting of the atmosphere and higher atmospheric drag, resulting in the deorbiting of the satellites, and you see them burning up here as they re-entered. So 49 satellites were launched, out of which 40 were lost, and therefore we often think that space weather is limited to high altitudes, but even at LEO, there are serious impacts of space weather, and various imaging satellites, communication satellites are in fact in low Earth orbit. You see, we are analyzing this event now in detail, and this green line that you see here, this vertical line, is the time of launch of the Starlink mission. And you see that just before that, there was a CME hit. Again, I'll not go into details of that because this is an event that is under study. But we think we have a very good idea now through a combination of observations of modeling of what really happened, which brought down the Starlink satellite. So to summarize, the impact of space weather extends not only in outer space, but also to ionospheric perturbations, which is very crucial for, in fact, high-frequency radio communications, which is defense, as well as disaster management agencies depend on. It impacts telecommunications, GPS navigational networks, the aviation sector. It impacts satellite health and also lifetime because the drag depends on space weather and astronaut safety. All of this are technologies that India has invested upon and the modern Indian society is very heavily dependent upon. And so it's important to acknowledge and understand that space weather impacts us in spite of us being a low latitude country. What does other nations do about space weather? US, of course, again, is way ahead of the game here. In fact, they take space weather so seriously because of the significant assets, starting from defense to communications to other assets they have in space, that the US president issued an executive order in 2016, which stated that it's the policy of the United States to prepare for space weather events to minimize the extent of economic loss and human hardship. The federal government must have the capability to predict and detect a space weather event. The plans and programs necessary to alert the public and private sectors to enable mitigating actions for an impending space weather event. This executive order was followed by a law which was enacted by the US Senate in 2020, called the Pro-SWIFT Act, to protect the United States from space weather events. If you look at the international strategies for dealing with space weather, there are multiple agencies, including from the United Nations to COSPAR and the UK Met Office. I'll not go into details of that. I'd like to highlight two centers which are actually involved in operational space weather forecasting. One of them is the United States NOAA Space Weather Prediction Center. The other is the Center for Excellence in Space Sciences India at ISRO Kolkata, where we are also doing operational forecasting for the last 7 months. Our forecasts are publicly available and anybody has access to this, just like the US NOAA Space Weather Prediction Center. If you look at the satellites which have been launched by various agencies to look at solar activity and characterize space weather, there has been at least, I would say, about 30 satellites which are already up in space looking at characterizing and monitoring space weather. India is going to launch its first comprehensive solar space mission, the Aditya space mission, whose primary objective is to understand the genesis of solar activity, but also to monitor the near-Earth space environment. And this is particularly important because it's the near-Earth space environment that impacts the Earth's magnetosphere and ionosphere and produces hazardous events that eventually leads to impacts on our technologies. Let me talk a little bit about Disha and why is it important to have such a satellite. So space weather originates at the sun, it propagates to the interplanetary space and then impacts planetary systems such as Earth. Now Disha is a mission that proposes to constrain the ionospheric variability. The ionosphere is a very interesting layer because it's really sandwiched between space, outer space, and the neutral atmosphere. And it is through this layer that any space weather effects actually propagates down to the atmosphere. It is also this layer which is extremely important for communications, not just radio communications, but scintillations and plasma bubbles at this layer gives rise to signal losses between satellites up in space and ground stations. So observations from Disha will allow us to assess the impact of space weather that originates at the sun, thus allowing us to do Earth system science studies and establish causality between an event on the sun and its impact near Earth. So what are some desirable capabilities from the perspective of a theoretician or a modeler, which I am, which is my expertise? One would be to have a neutral density monitor. This is very important for figuring out atmospheric drag and its impact on low Earth orbiting satellites. It's important to have electromagnetic fields monitor, electric current monitor. These are important because eventually a solar storm generates geomagnetic storms and impacts the DST index. And this is what is the final manifestation of a space weather event. And this kind of monitors allow us to constrain the perturbation and look at the intensity of geomagnetic storms, which are also, by the way, monitored by ground-based magnetometers, which I think Geeta, who follows me, will talk about. Plasma density perturbations is also something that is important to measure because the plasma bubbles and density perturbations due to ionospheric storms and injection of plasma winds from the sun, which impact telecommunications, creates GPS scintillations, as well as produces blackouts in high frequency communication. So these are some important elements that one would like to see in the Disha mission. And ideally, if there is an overlap, and I see that there is a mistake here, this should really be Aditya L1 plus Disha overlap. This would give rise to a sort of system-wide assessment of space weather. So what can SESI do for Disha? So we are.
You have 3 minutes left. Huh?
Sure. Yeah. So we are experts in theoretical interpretation of observations through our computational modeling, and we can provide computational modeling support to the mission. We can establish physical model-based causality across the Sun system, and we can predict the arrival timing and intensity of solar storms, which can then be utilized to appropriately plan observations by the Disha instrument. So we have, for example, developed over the past couple of years the ability to forecast the strongest solar flares, the MX class solar flares, based on big data analytics and machine learning techniques, with the accuracy of our forecast reaching almost 96%, which is one of the best in the world. Our bulletins, space weather bulletins, including storm arrival forecasts, are available online for everyone at our website. You can just do search for SESI space weather, and you will find this website where routine bulletins are updated. We do modeling of the Sun Earth system. So what you see here is the background state of the magnetosphere influenced by the supersonic solar wind impact with the magnetopause, which really helps protect the Earth's atmosphere, and this magnetotail formation due to the stretching of the Earth's magnetic field lines by the solar wind. When there is a storm impact, this is a simulation from the SESI storm interaction module, a CME impact on the heliosphere. You see this large current systems developing. And I'll quickly go to the next slide to tell you the importance of why it's important to have 2 satellites and not 1. So what you see here is the magnetosphere ionospheric system being perturbed by the impact of a solar magnetic storm. This is the view from the Sun looking at the Earth. This is a view from the ecliptic plane looking into the direction of revolution of the Earth. And so if you place a satellite in polar orbit, it will be sampling this plane. And then this is the view from the North Pole. And so you're looking down into the ecliptic. And if you place a highly inclined near equatorial orbit satellite, then you'll be sampling that plane. What we see here is the ionospheric magnetosphere structure is highly inhomogeneous and reacts in a way that any one orbit will not be able to properly assess, and therefore 2 different or even multiple different orbits completing the whole plane around the 3D global sort of atmosphere around Earth would be particularly important for. This is my last slide. So space weather originates from the Sun and impacts near space environment. and various technologies starting from telecommunications, navigational networks, and in fact, even the World Wide Web. Our country and the world needs to understand the risks associated with space weather and create mitigation strategies. One of the recommendations that I have is for India to create an interagency overarching mechanism, fund programs which are necessary to develop national capabilities in this front. Our center, SESI, provides very critical advanced space weather knowledge, in particular space weather predictions, which very few groups around the world are capable of doing. And we believe that a synergy between such computational modeling, big data analytics, as well as space-based missions will create the overall domain understanding to be able to assess, understand, and predict the impact of space weather on our modern technology. Thank you very much.
Thank you. Let's see if there are any questions in the chat box. I think there are no questions yet. I have one question, maybe one clarification. This is regarding the total solar radiance, right? You mentioned about the total solar radiance. But I think you need to have variations over a much longer period, maybe thousands and thousands of years and millennial scales to induce any change in the global climate. Rather, what is believed currently is the spectral irradiance. This is what is responsible for regional climate or local climate or whatever you call it. Whereas the total solar irradiance, perhaps it doesn't contribute to the climate that we understand now. But yes, in the longer run, yes, but not in the shorter time scale, say 2 or 3 solar cycles.
So in fact, there are ways to reconstruct the total solar radiance over longer time scales. I didn't really go into details of that, but one can reconstruct this based on cosmic ray flux, open flux, and then solar activity, and then do some forward modeling to reconstruct them, which are actually fed into the IPCC climate models. And yes, the spectral irradiance is extremely important, particularly the variability in the ultraviolet wavelengths, which is the primary wavelength which drives atmospheric dynamics. But of course, the ionosphere is particularly sensitive to extreme ultraviolet and X-ray radiation.
Of course.
There are questions in the chat box. David?
I cannot see the chat box. Can somebody read out the questions if there are any questions in the chat box?
Yeah, there's one question. How do you plan to parameterize the influence of space weather on neutral abundance?
Right. So this is a question actually I posed for Guru Baran. Trying to understand if there are models which can actually, in fact, so the models that I portrayed just now, these models that we have developed, these are completely MHD models. So they are basically, they deal with ionized plasma. So they're okay for the upper part of the ionosphere. They're not so okay for below 400 kilometers, for example, right? And then around 400 kilometers, you have a mix of neutral atoms and ions. Now, of course, one can develop models because the physics is sort of understood in the sense that you expect the ions will couple to the neutral atoms through viscosity and collisional dynamics. And while the ions and the electrons will be influenced by the electromagnetic fields, the neutrals will not, but the coupled motion will therefore be driven by forcing from the top. On the other hand, if you have atmospheric dynamics, which is leading to forcing from the bottom, and they are able to move the neutral mass, then the ions and electrons are also coupled to them, so they'll also move. So this is a very interesting and complex region, and therefore I was trying to figure out if my guess is in India nobody really has made such models, but I suspect in the world there must be people who are doing this, and this is a capability that one must think of developing in India as well. This is something that perhaps we should be looking at.
Yeah, I think there are a couple of more questions. What are the EM electric current monitors that can be used to predict geomagnetic storm intensity? Electromagnetic, maybe. Yeah.
So right now, the best monitors are on ground, and I will respectfully defer to the next speaker. I think Geeta, I don't want to steal her talk. Geeta is going to talk about the ground-based magnetometers. She's from IIGM, the premier institute which looks at in India, which looks at measuring geomagnetic storm intensities. And I will later answer that question for you.
Fine. This your model, this model provides any knowledge about the magnetospheric current systems.
Yeah, exactly. So it does. In fact, this Stormy module that we have produced, this paper that's in preparation, we have managed to, based on the ionospheric currents that is induced, we have managed to develop a scheme for predicting the DST index, which is the geomagnetic storm index that ground-based magnetometers measure. So yes, so we can actually what you see here is in fact currents following the impact of the CME, and we see this beautiful reconnection in the magnetotail, injecting the current back through the polar regions, and this is the magnetic sheath region where also there is magnetic reconnection and therefore currents. And you see the manifestations of that. Again, this is, if you look at this small little plot here, it's actually measuring current density. I think it's in nanoamperes per meter square. So it's in fact magnetospheric currents. So we can do that from these models.
Thank you very much. I think we should move on for want of time. Thank you very much, Dibyendu. Appreciate that. We'll have the next speaker now, Dr. Geeta Vichare. He will speak on geomagnetic storms and substorms triggered by space weather. Geeta, you are there?
Yes. Am I audible?
Yeah, you're audible. Please share your slides.
Yeah, I'm trying to. Are my slides visible?
Yes, make it full screen, no?
Okay. So, are they up?
It's not yet full screen. Please
Not
press
yet?
that button again.
For me,
No.
for me it is full screen. What about now?
I think it's taking time. It's not changing, I think.
Geeta, just when this happens, sometimes it helps if you stop sharing, then reshare, and you choose full screen sharing. When you not the window, but the full screen sharing.
I should first stop sharing, right?
Yeah, first stop sharing, then go back and share again, and then when the option comes, choose full screen. That might help.
Okay. Entire screen.
And then confirm the button below.
Yes, now it is full screen. Yeah, it is full screen. You can hide that button. No? One button is there. Please hide that button.
Yeah, yes. Yeah.
Yes, perfect. Please go ahead.
Okay. Thank you, Gurubaran sir, and good afternoon to everyone. I'm Dr. Geeta Vichare from IIG. And firstly, I would like to thank the organizers for giving me this opportunity to present in this national meet. And today I'll be talking about these geomagnetic storms and substorms triggered by space weather events. By this time, from these previous speakers, we have fair idea about the space weather, and everyone knows about the sunspots, and number of sunspots keeps on varying over 11 years, and that is called as solar cycle. And when the number of sunspots are more, it is the solar maximum activity is very high, and when it is low, then the maximum solar activity is low. And all these phenomena like solar flare, coronal mass ejections, or co-rotating interaction regions (CIRs) they do take place when the solar activity is fairly good. And all these variability, solar variability, that influences the magnetic field records on the Earth. And that is why even in the previous talk, Dr. Nandi insisted that ground magnetometers importance is very much there, because even ground magnetometers can catch these signatures and whatever the phenomena is happening on the sun and interplanetary space. So we know that when these solar eruptions take place from the solar surface, it evolves in the interplanetary medium, and when they reach near the Earth, then it interacts with the Earth's magnetosphere. Now, Earth's magnetosphere, it is a cavity, basically a cavity inside which Earth's magnetic field prevails, and outside there is a interplanetary magnetic field. So, in reality, this interplanetary magnetic field or solar wind, they are not constant. They are very time varying. They're very dynamic. So their density, velocity, or interplanetary magnetic field strength and direction, orientation, that also keeps on changing. And continuously our whole magnetospheric cavity, it compresses, relaxes, and a lot of dynamics takes place, particle injection from various parts of the magnetosphere. And all these things constitutes the space weather effects on the Earth. When this high-speed solar wind, which is usually a highly supersonic in nature, that reaches the Earth's magnetosphere, then what happens? Earth's magnetic field acts as an obstacle, and it forms a bow shock in front of the day side of the magnetosphere. And magnetopause, this is the magnetopause boundary. Inside there is a white color, so that separates the Earth's magnetic field from outside. So this boundary, is my cursor visible? My cursor visible?
Yes, yes.
Okay.
Yeah, cursor is visible.
Okay.
Yeah.
So this is the magnetopause boundary. This is the bow shock. And in the day side, the magnetic cavity is compressed, whereas in the night side, it is stretched, it is elongated. This is called as magnetotail. In the tail, in the equatorial plane, there is a neutral point, and most of the plasma of the tail, that is concentrated near the equatorial plane. That is called as plasma sheet. Now the plasma in this green colored region, that is the plasma sheet, that can map along the field line and they can precipitate in the higher latitudes, that is auroral oval. And this plasma sheet, it separates the magnetotail into north lobe and south lobe. Now in the north lobe, the direction of the magnetic field is towards Earth, and in the southern lobe, it is away from the Earth. So these magnetic fields are oppositely and almost parallel to each other. This blue color region, this is the plasma sphere, where our radiation belt is present. Outer radiation belt, inner radiation belt. Mostly outer radiation belt is from around 2 to 10 RE region. RE is the Earth's radius, so which is around 6,370 kilometers into 10, like that. And the region between bow shock and magnetopause, that is called as magnetosheath. This is highly turbulent region where the temperatures and turbulence is very high. And there are some regions called as cusp, polar cusps, where the magnetic field lines are open and they are directly connected to the interplanetary fields or conditions. Now what happens, this is the Earth here at the center, and these are the magnetic field lines. From the day side, from the solar side, sun side, solar wind is coming, and Earth's magnetic field is from south to north directed. If the interplanetary magnetic field is southward directed, these two at end point, these two Earth's magnetic field and interplanetary magnetic field, they are opposite in direction and they reconnect. So in the result of this reconnection, what happens? This field line, which was earlier closed, that becomes open. and it drags towards the night side and it goes here. Now from in the tail region, from top and bottom, the pressure, it tries to push the magnetic field lines closer to the equatorial plane, and again there is a reconnection takes place. So there are two places magnetic reconnection can take place. One is the subsolar point in the day side magnetopause, and another one is in the magnetotail. So reconnection, it facilitates the energy entry or the entry of the particles, so particle injections. Now, when the particles are coming, charged particles in the presence of magnetic field, it exhibits several basic motions like gyration motion, bounce motion between two poles, between south and north pole. It keeps on bouncing. The other one is because of the gradients and curvature drifts, the particles also drift in the azimuthally in the equatorial plane. Now, all these motions constitutes various current systems in the magnetosphere. Now, when this reconnection takes place, it also generates the electric fields inside the magnetosphere. Those electric fields are called as convection electric fields. These convection electric fields are normally in the dawn to dusk direction. These electric fields drives various currents like ring current, substorm current, wedge currents, FAC, that is field aligned currents. Magnetopause currents are basically because of the compression of the entire cavity, because its size has changed. It is now narrow shaped when it is compressed, and hence in order to balance the things, it is a balance between Earth's magnetic pressure and solar wind dynamic pressure, and as a result of this balance, the currents flow, and those currents are called as Chapman-Ferraro current or magnetopause currents, and they basically try to increase the magnetic field inside the Earth's magnet. Now, here several currents are there. I told about tail current, neutral sheet current, but what is our present interest is the ring current, because we are going to talk about the geomagnetic storms. So, this is the picture of ring current, azimuthal picture in the equatorial plane. The currents are moving westward. Now, when these geomagnetic storms occur, this occurs when the interplanetary magnetic field turns southward. That means there is a reconnection and remains southward for a prolonged time, at least 2 hours and above. Then what happens? The convection electric field tries to push the plasma inside in the radiation belt, and there the particles move azimuthally around the Earth, constitutes a westward current. Westward current in the magnetosphere creates the H variation on ground negative. So that is why during the geomagnetic storm, what happens? First, I told about the magnetopause currents. That means solar pressure is trying to compress the entire cavity, and as a result, Chapman-Ferraro currents flow on the magnetopause surface, and that enhances the H component, horizontal component on the Earth, and that is why there is a sudden increase in the H variation. That is called as storm sudden commencement. Then it may remain there for positive for some time, that we can call as an initial phase. And when actually ring current establishes, westward ring current, then the H component suddenly drops. It becomes negative. So this negative going, this is called as the main phase. And when the particle injection stops, then automatically it will try to decay. The ring current decays, and that takes time, and that is called as recovery phase. That is coming back to its pre-storm level, and this is the recovery phase. So for the storm, there are mainly main phase and recovery phase are must, but sudden SSE and initial phase can be there. But that is not the necessity. What is the necessity for geomagnetic storm is the ring current. That means ring current signature is only main phase and recovery phase. So to represent these variations or geomagnetic storms, there is a DST index. DST index, it is used to describe the geomagnetic disturbances at low to mid latitudes, and it has a time resolution of 1 hour. Similar to DST, there is another index called as SIMH index, but it has time resolution of 1 minute, because many things within a 1 hour, many things changes because things are so time varying. So within a time frame of 1 minute also, the things change very drastically. So it is important to have high resolution. Now, how do they compute? They take the magnetic field measurements from all over the globe. So these are the select few geomagnetic observatories. Based on their data, SIMH and ASIMH indexes computed. Now, what is CMH and ASIMH index? CMH is the ring current which is symmetric, which is flowing everywhere. So what they do, they take the magnetic field observations from all the observatories. They try to pick up the observatories which are equidistant in the terms of longitude. And they remove the quiet time pattern, because quiet time pattern, other than this geomagnetic storms or disturbances, there will be SQ currents or electrojet currents, which are the quiet time variations. They first remove that, and then they try to compute the average pattern out of this selected observatories. That is called as CMH. And not necessarily that every observatory will have the same amount of variation. So the minimum and the difference between minimum H variation and maximum H variation, that is called as asymmetry index. So to compute the symmetric and asymmetric index, these observatories are used. Using this artificial neural network, we try to attempt to predict the CMH and ASIMH indices. So this is one storm during March 2017, and this is the CMH variation. Blue one is the predicted one and red one is the observed one. One can see, okay, it is matching fairly good, even asymmetry index. And interestingly, like small scale variations, it is able to reproduce fairly better way. Now this is the signatures of magnetic field variations of solar flare and also the geomagnetic storm. The earlier signature what I showed is the ideal signature, but in practice we may not get very nice main phase and recovery phase. There will be some fluctuations here and there. This is the event in April 2001, and this is our Tirunelveli H variation data. So on 10th April, during noon time only, there was a sudden increase. Solar flare, it actually enhances, it is electromagnetic radiation basically, and it tries to ionize the ionosphere strongly, and it produces whatever existing currents will be there, it will try to enhance it because of the enhanced conductivity. And this is the sudden increase in the current on this particular day. Otherwise, this one was a normal EJ kind of variation at this location. Next day was also like that, and on 11th of April there was sudden increase, that is SSC, and there was a main phase. Main phase was also in a multiple steps, and it reached minimum over here, and then the recovery. So this is a typical magnetic field variations during geomagnetic storm. In history, everyone knows that in 1859 there was a very strong geomagnetic storm, which is also known as Carrington event. And Colaba Observatory, that is having the magnetic record for this geomagnetic storm. So at Colaba, the variations was around 1600 NT. This doesn't mean that DST was like this. Since Colaba was during noon time and it has produced this much variation, but DST can vary because localized effects can be different. Then comes substorms, because my topic given is storms and substorms, so I would like to talk about the substorms. Substorms are basically short duration disturbances.
You have 5 minutes, Geeta.
Okay, sir. So when the interplanetary magnetic field turns southward, then the reconnection takes place and energy gets deposited in the tail region. It keeps on storing the energy, and that is called as growth phase. But after several such kind of events that is slowly keep on increasing, at one instance what happens, the very explosive things takes place, and that is called as the substorm expansion phase, where the energy stored in the tail is released, and the field lines which are stretched in the magnetotail, they become more dipolar, and this is called as dipolarization process. And this dipolarization process, what it does, it energizes the charged particles and it pushes the injected particles deeper inside, means towards the radiation belt or towards the lower L values or towards the lower field lines, and which can get mapped to the higher latitudes and it will precipitate. So the auroral oval, which is normally around 60 or 70-degree latitude, during these times it can expand. It can expand towards equator, or as well as it can even expand towards the pole world. And when the particles precipitate there, and instead of bouncing back and forth, if they precipitate, they collide with the atoms and molecules of the upper atmosphere, and they release the energy in the form of visible light, that is called as aurora. This picture even Dr. Nandi has shown. Then after the expansion phase, there is a recovery phase, and that recovery phase, it brings the whatever the conditions to the quiet state. So the storage and release of energy in the magnetosphere during substorm leads to the enhancement of currents, and those currents are there, so magnetic field also we can identify. So using ground-based magnetometer at high latitudes, around 50 or 60, 70-degree latitude, one can see this kind of signature. So this is the typical slow negative variation, that is a growth phase, and suddenly there is a negative variation that is called as the expansion phase or substorm onset, and then the recovery phase. So this movie, I'm sure many of you might have seen it before, but whatever I spoke, that will be better clarified through this movie. That is why I thought of keeping this. So Jetta is coming from the sun, and now it is interacting with the Earth's magnetic field. Magnetic field track in the night side. Reconnection took place there, and plasma is getting, particles are precipitating in the. So to represent this auroral electrojet, there are different indices. That is auroral electrojet index. Mainly for the substorms, we use AL index. That is auroral low index. That is negative excursion we want to see. And these are the several observatories in the northern hemisphere. Normally AE, AL, AU, northern hemispheric observatories. So there is a bias in the northern hemisphere because there are very limited observatories in the southern, near this 60, 70 degree. Now this slide I thought of keeping because it differentiates between the geomagnetic storm and geomagnetic substorms. Though the words appear very much similar, but there are substantial differences between these two. These are not just the substorms, are not just a subset of storms. They differ in many ways. Firstly, during geomagnetic storms, they are because of the ring current flowing in the Earth's equatorial plane, and substorms are ionospheric currents at high latitudes. Then geomagnetic storms inject large number of ions in the outer radiation belt, whereas during the geomagnetic substorms, the particle precipitation in the auroral region and no particle injection in the radiation belt as such. A geomagnetic storm takes place for a period of several days, whereas geomagnetic substorms are very short term, that is only few hours, period of few hours. Storms are mostly observable from everywhere, like from equator to say 50, 60 degree latitude, whereas substorms are only visible, magnetic field signatures are visible in the high latitudes. Though related to the substorms, there are PI2s and all, which can be seen at the night side of the low latitude. Then the frequency of occurrence of geomagnetic storms is around once or twice in a month during solar cycle maximum. But substorms are more frequent, just a gap of few hours between consecutive substorms. the magnetic field disturbance because of substorms can be because of storms can be of the order of like -50 to -400. Sometimes it is like 700 or so, but very rarely. But normally it is of this range, whereas substorms are normally of 200 to 4000 NT. Phases of geomagnetic storm are, as I said, storm sudden commencement, initial, main, and recovery phase. Whereas for the substorms, it is growth, expansion, and recovery. So here I end my talk. Thank you.
Thank you. You were sharp on dot. Any questions in the audience? I don't see any questions in the chat box. I have one question maybe. So how are these ground magnetic field measurements? This is a very general question for the audience sake. How are these ground magnetic field measurements? How are they going to supplement or complement satellite mission, for example, Disha missions? In what way you can think they can complement?
Yeah. In earlier days, before Disha, there were many low Earth orbiting satellites of ESA as well as NASA, and many Indian scientists were involved in analyzing that data. And at that time also, we have utilized to support the satellite observations. What is inferred or extracted from those observations? Is it complemented by the ground observations or not? That we had checked. Everything, satellite as well as ground, has their own merits and drawbacks. Ground observations, though it can give a large time series, and at a given location one can see the phenomenon continue. Whereas satellite at different locations one can see, but there is a dismerit that we cannot have at a time at different locations. So in that sense, it is very important to have ground support, because satellite has this limitation that at a given time we cannot have at multiple locations, we cannot have the observations. As suggested by Dr. Nandi, that we should go for double or multi-satellite missions, which like SWAM and all. SWAM has 3 satellite missions, and many nowadays satellites are multi-spacecraft missions. So those are very helpful in order to get any understanding of the phenomena. And obviously ground is also support.
There's one question in the chat box.
Sorry?
There's one question in the chat box. Are ground-based neutron monitors, the data relevant for studying storms or substorms? Ground-based neutron monitor.
Okay. Neutron-based data. Neutrons, it is basically it is a secondary cosmic ray particle. Where the primary particles interact with the atmospheric particle, it creates a cascade of particles, and neutron is one of those. So it is a proxy for the primary cosmic ray. So cosmic ray, it is it depends on, it is a particle. So based on their energy, it is called as cosmic ray particle. Now neutron and things during solar disturbances, geomagnetic disturbances, especially during the CME ejecta and all, because of the high magnetic field at the magnetic cloud, it tries to diffuse the cosmic rays coming towards the Earth, and that is why there is a less number of cosmic particles during the passage of CME, or particularly during the passage of magnetic cloud, and that is why we see the strength of the cosmic neutron monitor count. It goes down. That is called as Ford-Bush decrease. Now this Ford-Bush decrease depends on the total magnetic field, IMF magnetic field. Whereas for the geomagnetic storm, the IMF has to be southward. If the magnetic field is turning southward, then only geomagnetic storm can take place. But normally in the CME, the orientation, the magnetic cloud magnetic cloud structure is such a way that the orientation moves from north to south very nicely. So some part of it has southward orientation, and during that, so they are normally simultaneous phenomenon seen in the electron monitor as well as the magnetic field measurement. Have I answered the question?
Thank you. I think we have to move on. There are a couple of more questions in the chat box. So please do look into those questions and you may reply in the chat box. But we'll now move on. Thank you very much, Geeta, for an excellent overview of storms and substorms. I'll move on to the last talk of this session. It is a global impact of space weather processes and IT system. This talk will be given by Dr. Rajkumar Hajra. High to low altitude coupling during space. Yes, Dr. Hajra. Please share your slide.
Yes, I understand. So my screen is on.
Put it in full screen mode.
This one.
Yep.
So it is visible now.
Yes.
Okay, so thank you very much for the invitation. The title of my presentation is High-Speed Solar Wind Steam Effects on the Topside Ionosphere, which I will try to explain using high to low latitude coupling. And actually, this presentation is a part of a paper that was published in 2017 in Geophysical Research Letter, which was co-authored by Bruce Surutani, Cristiano Bloom, and Ezequiel Lecher. So I would like to mention their names. Now, the topside ionosphere actually starts above F layer and it extends up to the protonosphere. So the range is about from about 200 kilometers to up to about 3,000 kilometers. And this region of ionosphere consists of oxygen, hydrogen, and helium ion. Now, the physical processes of topside ionosphere is significantly different than what we see up to F layer. Because of this high altitude, the neutral concentration is very less. So the collisional loss of the ions is insignificant in topside ionosphere. And the plasma distribution in topside ionosphere, that is mainly controlled by diffusion process. For topside ionosphere, there is an important altitude that is known as transition altitude, at which altitude actually the total concentration of heavy ion, that is oxygen ion, is equal to the total concentration of the lighter ions. So above the transition altitude, the lighter ions, they dominate, and below it, the heavier ion, that is oxygen ion, dominate. This transition altitude as well as the entire topside ionosphere is strongly variable, and the variation depend on many factors, but most important of them are solar ionizing flux and atmospheric neutral winds. Actually, there are several works on this topside ionospheric variability using data mainly from RSCB observatory. But main focus of this presentation is how the topside ionosphere respond to external solar wind forcing. To be more specific, how the topside ionosphere responds to high-speed solar wind stream emanated from coronal hole. So here is a brief introduction on high-speed stream emanated from coronal hole. This is a solar image taken from Solar Dynamic Observatory of NASA, and the black region here is known as coronal hole that emanate high-speed stream. In this schematic diagram, you see this is our sun, and these yellow lines, they represent flow solar wind. They have speed between about 300 or 400 kilometers per second, and the blue region that represent high-speed stream emanated from this coronal hole. When the high-speed stream overtakes this slow stream, a compressed interaction region is created that is shown by this red shaded region. Now the coronal holes, they are long-lived structures. They can survive more than one solar rotation. So these high-speed stream, which are emanated from this coronal hole, as well as the interaction region that also co-rotate with the sun. So we call that co-rotating interaction region or CIR. Now both CIR and high-speed stream, they carry Albion waves, and the southward component of the Albion wave, they cause magnetic reconnection with geomagnetic field, and as a result of which substorms and convection events take place through which energetic particles in the range of 10 to 100 kiloelectron volt, they are injected inside the magnetosphere. So this is kind of basic background of high-speed steam emanated from coronal hole. Now, from the title of my presentation, you see that I want to understand what is the impact of high-speed steam on topside ionosphere. But before going to that, let us understand the typical behavior of topside ionosphere when there is no high-speed steam. So we choose a low-speed steam interval from 2009. And in the top panel, V solar wind is the speed of solar wind plasma. In panel B, black and red, they represent the plasma density and ramp pressure of solar wind. In panel C, black and red, they represent magnitude of interplanetary magnetic field and temperature of solar wind plasma. And in panel D, this is the digit component of interplanetary magnetic field. And all this solar wind data, they are collected from OmniWave of NASA. And this actually tells us about the solar wind condition near the boson nose of Earth's magnetosphere. And from the variation, you can see that solar wind was almost quiet. So there was no high-speed steam or any other type of solar wind disturbance. Now from the CMH index here, now CMH index, as already discussed, it is the index for ring current. And when CMH goes below minus 50 nanotesla, we identify a geomagnetic storm. But here you can see that CMH minimum value was around minus 20 to minus 30 nanotesla. That means there was no geomagnetic storm. And in this panel, F and G, SME and SML, they represent auroral electrojet and the westward component of auroral electrojet. And from the variation, we see that auroral activity was not that drastic during this time. Now the bottom panels from H to M, they represent the variations of different parameters of the topside ionosphere from Arecibo Observatory. And the NE means the electron density of the topside ionosphere. You can see that the electron density actually decreases if you go above 400 kilometers. And secondly, the electron density is more during daytime and less during nighttime. If you see the oxygen ion density, the variation is almost similar. That means it decreases above 400 kilometers slowly, and it is stronger during daytime and lower during nighttime. But the variation of hydrogen ion is just opposite. It increases above 400 kilometers. It is lower during local day and higher during local nighttime. Okay, and the transition altitude that actually separates these two variations, that is shown by this black curve here, HT. So transition altitude is high during local day and low during local night. Now bottom two panels, they represent the electron and ion temperature at different altitudes, including the altitude of this transition height. And in general, what you can see is that the temperatures are high during daytime and they are low during nighttime. So all these parameters actually, they represent a typical behavior of topside ionosphere, and when there is no geomagnetic or solar disturbance. Okay. Now this is the main result where I am showing the same data of topside ionosphere during a high-speed steam interval, and the panels are in the same format. In the top panel, you can see here is a low-speed steam, and this is a high-speed steam emanated from coronal hole about 2 days before we identified near the boson of Earth. And the interaction region between this low and high-speed steam, you can see that is characterized by enhancement in plasma density and ramp pressure, and also enhancement in the magnetic field magnitude. So this represents PIR, or rotating interaction region. If we see the CMH index, here also the minimum value of CMH is around minus 20 to minus 30 nanotesla. That means there was no geomagnetic storm caused by the CIR or the high-speed steam. But if you see the SML and SME indices, you can see that during the interval of high-speed steam, the auroral activity was very much drastic. And the bottom panels from H to M, they show the variation of topside ionosphere. If you compare this plot with the previous one, we can clearly see that all the parameters in general are stronger, like the electron density, oxygen ion density, and temperatures, they are higher during this high-speed steam interval compared to low-speed steam interval. So here is a perfect comparison actually. So here the left panel, they corresponds to the local night time, and the right panel, they correspond to local daytime. And these data points shown by pink, red, and yellow, they represent the interval of the high-speed steam. And this blue or sky blue, they correspond to the interval of low-speed steam. And as I told, in general, you can see that all the parameters, they are higher during high-speed steam, and they are lower during low-speed steam. So and the similar thing is presented here actually, but in different format. So what we conclude is that during the high-speed steam interval, the topside ionosphere density becomes very high. The transition altitude was high. Temperature was also high. So topside ionosphere became heated and also expanded in altitude. Now, before going to the explanation, let us consider the time interval from where I have taken the data. The data is collected from the years 2008 and 2009, which we know that very famous interval, because it actually corresponds to the prolonged solar minimum of solar cycle 23. And there are several works on different aspects of this interval. I have summarized here some major points. From several studies, we found that this interval is characterized by very low number of equatorial or low latitude coronal holes on the sun, very low magnitude of the interplanetary magnetic field, very low solar wind speed, and RAM pressure. As a result of which, we found that during this interval, the energy transfer from the solar wind into the magnetosphere was very low. And consequence of this low coupling between solar wind and magnetosphere is that the ionosphere thermosphere system during this interval became very cold and contracted. But during this interval, we identified a high-speed steam hitting the Earth system. And we found that the high-speed steam did not cause any geomagnetic storm. But the topside ionosphere responded to that high-speed steam dramatically. The topside ionosphere became hotter and expanded in altitude during the high-speed steam. So the question is why it happened. Actually, in the detailed paper, you will see that we have explained all the possible explanations. But here I would like to focus on two major explanations. First one is super fountain effect. Now, most probably in a paper, Bruce Surutani, in a paper published in 2004, coined the term of super fountain. He suggested that during very intense geomagnetic storm, E cross B drift over magnetic equator can be very high. That can uplift the equatorial ionosphere to high altitude, and that can give rise to very strong fountain or super fountain effect. But this explanation actually does not go well with our present case, because we found that when the high-speed steam hit the Earth system, there was no geomagnetic storm. So super fountain effect cannot be the cause of ionospheric heating and expansion of the ionosphere. Another possibility is wave-particle interaction, for which I will show the data. So here is the same high-speed steam interval. All the panels, top panels, I have explained already. In bottom 5 panels, I am showing the dynamic spectra of geomagnetic field H component from high latitude regions. And in this spectra, you can see some pockets where you can identify very strong magnetic pulsations in the frequency range of 0.1 to 2 Hertz. They actually represent emic wave, electromagnetic ion cyclotron wave. So emic waves are created during high-speed steam interval. How? Actually, the high-speed steam interval, you can see they carry Alban wave, and southward component of the Alban wave, they cause magnetic reconnection with geomagnetic field, and they lead to substorm and convection events through which energetic particles in this range, they are injected inside the magnetosphere. Now, the anisotropy of the electrons, they cause porous wave, and anisotropy of the protons, they cause emic waves. And now you can see that we actually see emic waves during the high-speed steam, but we see the emic waves in the high latitude regions. Do they propagate to low latitude region? Because the RSCO observatory is around the low latitude region where we really don't have any data to identify emic wave. But there are several studies, they confirm that the plasma waves, they can actually propagate from high latitude to low latitude. So if the emic wave can propagate from these high latitude region towards the RSCO observatory, so then it can there can be some wave particle interaction between the emic wave and the thermal ions and electrons in the ionosphere, through which the emic wave can be Landau damped and the energy can be transferred to the electrons and protons, thermal electrons and protons, and they can hit the ionosphere and ionosphere can expand actually. So here is the summary. What we found is that we choose an interval when the solar activity was very low, and during that time a high-speed stream hit the Earth system, but that did not cause any geomagnetic storm. But even though the topside ionosphere actually responded drastically, it became very hot and it expanded in altitude. Also, the density, everything became very high, and this can be actually explained in terms of wave particle interaction that can hit the thermal particles in the ionosphere to that can hit the ionosphere as a whole, and that ionosphere can expand in altitude. Also, density can increase. So here is the detailed reference to that paper. You can go through this paper. So thank you very much.
Thank you. Thank you for your talk. Let's see if there are any questions in the chat box for you.
Yeah, I cannot see the chat box, so could you please read some of the comments?
Read that. If something comes up, he'll read that.
Yes.
Maybe you can read later. Yeah. Okay, I don't see any messages there in the chat box. So anyway, for want of time, I think we have to move on, I suppose.
Okay, thank you very much.
Thank you very much, Rajkumar. Thank you for the nice talk. So this ends the three presentations for this session. Over to the organizers, please.
Yes, I will say.
Thank you very much, Dr. Gurubaran sir, for having made it so lively throughout the session, and also our thanks to the speakers who have spoken in this session, Dr. Dibyendu Nandi, Dr. Gita Vichare, and Dr. Rajkumar Hajra for your presentation, and as well as the interactions which have happened during the session. And this concludes the session 2, and we are having a short lunch break, and we will resume the meeting sharp at 13:30 hours. I repeat, we will resume the meeting at 13:30 hours sharp. Thank you very much.
Yes, yes. Yeah.
Good afternoon and welcome back to the National Meet on Aeronomy Research. So in the session 3, we are having a dedicated slot for the discussions on potential applications of near-Earth space variability. And the session will be chaired by Dr. Tarun Kumar Pant, Space Physics Laboratory, VSSC, ISRO. Over to Dr. Tarun.
Thank you, Professor Das. So thank you for giving me this opportunity to chair this very important session of today. We have 3 talks in this session. The first one is by Professor Ashik Paul, who is at the Institute of Radio Physics and Electronics at Calcutta University. And he is an expert in the area where he studies the signal in space conditions under adverse ionospheric changes like the space weather. So I invite Professor Ashik Paul. You're muted. We are not able to hear you. You are still, we are seeing that you're muted. Yes, I think now it's fine.
Okay. So thank you. At the onset, I'd like to thank Indian Space Research Organization, the Science Program Office, for organizing this National Aeronomy and giving me this opportunity to present some of the results that we have obtained using low Earth orbiting satellites and other kinds of satellites from the Institute of Radio Physics and Electronics, University of Calcutta. So let me begin by sharing my screen. So is my screen visible?
Yes, it is visible.
Okay, great. So this is the title of my talk today at the National Aeronomy Research Meet. So the equatorial and the low latitude ionospheric irregularities, we are well aware of that they cause significant impact on transionospheric radio signals. And that impact is extended over the wide spectrum of frequencies, which may range from the high frequency, like around 50 megahertz, going right through L-band, and sometimes even at S-band. Now, the issue of concern when using satellite-based systems and services for the modern society, which knowingly or unknowingly utilizes a large number of such applications, when there is signal outage due to different kinds of space environment issues, then it can sometimes cause life-threatening situations as well. So characterization and the diagnostics of these effects are extremely necessary and for advancement of this present understanding. And as on date, we can say that in the region around the equatorial and the low latitude, the level of prediction of the occurrence of these irregularities is not even accurate with a value of, say, around 50%. So, the Institute of Radiophysics and Electronics, we have operated, and some of the systems are still there. Number of ground-based instruments ranging from a VHF radar, which is just in the process of being finally commissioned, around 53 megahertz. Then we had worked with low Earth orbiting satellites and at 150 and 400 megahertz. Then the geostationary around 250 megahertz, and of course GNSS in the L band, and more recently the IRNSS, which is in the S band. So the global scenario, when we consider that, we could understand that one of the most disturbed regions in terms of the satellite signal outages due to this kind of ionospheric structures being developed, they occur either in the region around the magnetic equator up to the northern crest of the anomaly, or in the polar region. One of the major differences which we should consider while designing any kind of new space mission is that in the equatorial and the low latitudes, these effects could happen even in the absence of any kind of major space weather event, because space weather event, the term being coined primarily in the mid and the high latitudes, there they become almost synonymous with the occurrence of geomagnetic storms. But in the equatorial and the low latitudes, one of the more interesting but perhaps more challenging situation for the system designers is that these events could occur even in the absence of any kind of geomagnetic disturbed condition. So that will add additional metric to the already complex electrodynamics that we have to encounter. So this meeting, the theme of this meeting being to plan something, some science objectives for this DISHA, I could find some literature available in on the net about DISHA. This being a two satellite high and low inclination of about, one of them will be about 85 degrees and the other at having an orbital inclination of 25 degrees. And their orbital altitudes will also be around 400 to 450 kilometers. So these being low Earth orbiting satellites, other than the medium-induced perturbations, we should also be extremely careful while designing the receiver section, because we know that for low Earth orbiting satellites, the effect of Doppler shift could lead to complete outage of the signal if it is a narrowband receiver. So these are some of the payloads which I found on the internet, which may be present in the upcoming DISHA mission. The probable time period I found was around 2024-25 around period. So the F region of the equatorial ionosphere, we know, is characterized by two very prominent features, one of them being this equatorial ionization anomaly, and of course the occurrence of the ionization density disturbances. And there have been a lot of studies over the last almost like 40 to 50 years in this topic. And because, you know, this is a particular region of the Earth which attracts a lot of attention from the scientific community in other sectors as well, because of the wide day-to-day variability and the almost, you know, kind of intensity of the effects that we observe at these locations. So, although our country has a long tradition of ionospheric research going back to almost like the early 1930s, when the founder of our department, late Professor Shishir Kumar Mitro, he worked with a manually assembled ionosonde, at our field station during the early 1930s. But in spite of that long tradition in India, no long-term in situ data on some of the F-region parameters, they were available for until almost the middle of the 1990s. So in order to plug this gap, cross-situ satellite that was launched by ISRO in 1994 with a RPA probe on board. So I had very fond memories being the first, my first fellowship I got was from this cross-situ project that we had in our department. So one of the very fundamental observations that we could make from that, one of the passes was these fluctuations of the ionization density that we could see over there, and that gave us some idea about the relative irregularity amplitude, the delta n by n, for which was present in that section of the ionospheric volume at that time. And very interestingly, corresponding to that event, we also found signatures of these irregularities occurring both at VHF, this FSC, this was the FLITSATCOM, this was a geostationary satellite, Inmarsat, that's also a geostationary satellite, as well as a few of the GPS satellites, which shared the same ionospheric volume around that time. So this was a very fruitful, I should say, case study that we had done, where low Earth orbiting, medium Earth orbiting, as well as geostationary satellites were all, they intersected the ionospheric irregularities at some point of time or the other over a common ionospheric volume. That was followed by NOAA observations. NOAA, it was also a low Earth orbiting satellite. I will restrict my talk mostly to the low Earth orbiting observation because that is supposed to be the theme of this meeting, that what science we could do using that one. So this was around 136, 137 megahertz signal, and these were the kind of Faraday rotations that were observed typically from a NOAA track, from which one could calculate the total electron content along the path of this particular satellite. So this was a satellite which was aligned more or less along a north-south direction, polar orbit, and that gave us the option that we could calculate the latitudinal gradient of the total electron content in the early evening hours. Because we should remember that way back in 1989, Raghav Rao, he had predicted in one of his papers that this latitudinal gradient of the ionization density or the total electron content could be a very useful index for prediction of post-sunset ionospheric scintillations. So we did found that on a day when the value was high, the value of this gradient was high, there was a significant, almost saturated scintillations being observed on the 1.5 gigahertz geostationary link. While on the day when it was less, there was no scintillation observed. So when we extended this work to measurements done over 2 equinoxes, in August to October 2000 and February to April 2001, we could also identify that there was some kind of a threshold value of this latitudinal gradient of TEC, above which the scintillations were being observed. Of course, there were a few misses as well, but we could see that there could be some kind of a threshold value of the slope being identified, which had, of course, a statistically significant correlation. And then over this period, we also found that this S4 value at L band, I mean, this was an important thing because we were measuring the TEC at around 136, 137 megahertz. This was a very simple kind of experimental setup needed for tracking these NOAA passes. And then if we could map that to L band, that would significantly reduce the cost of resources in the way that we do not have to put, these expensive GPS receivers at different locations. If this TEC slope, which we found out from the low Earth orbiting satellite, if that could act as a proper proxy or a precursor for S4, the scintillation index at L1. Then DMSP observations, they also taught us that, typically the DMSP satellites, that was also a low Earth orbiting satellite, that was having an orbital altitude of around 840 kilometers. So if the trajectory was over this particular altitude, because DMSP was looking in a particular direction, so it will have a flat top. On the other hand, that means if the anomaly peak had risen to heights above this level, then there is a over the magnetic equator, then there is a very strong possibility that there will be occurrence or mapping of these irregularities to off-equatorial locations as well, like Kolkata. While on other days, if the peak was lower than this orbital altitude, then there was a much less possibility. So following this kind of a hypothesis, we did test with some days of DMSP observations that the red curve that corresponds to September 17, when we had very strong, situations observed on the Inmarsat link. While on the other night, when there was more of a rounded peak observed by DMSP, just 2 days here and there were no scintillations observed. So this also puts forward the question of the extremely dynamic or high day-to-day variability of the occurrence of this kind of events in the equatorial and the low latitude. So that is also...
You have 2 minutes.
Yeah, sure. I will wind up quickly. So DMSP observations, they were also followed in this fashion, the flat top and whether there was a flat top or not, and the corresponding correlation with the occurrence of these scintillations. Then cosmic observations, we could remember that was from roughly around 2007 to 2014. So the cosmic tracks over the Indian subcontinent, they were analyzed for one particular month in 2014, March 2014, which was extremely active in terms of the scintillation activity. And there also we could find some new information that in the post-midnight hours, the occurrence of L-band scintillations. This is a topic which has not been very extensively in Indian longitudes, so to say. We are more familiar with the pre-midnight occurrence of this scintillation. Then the St. Patrick's Day storm, that event also over the Indian longitude sector from Sinoph, it did show the values fluctuating in the ionization density as well as the rapid rise of this velocity over the magnetic equator. And then finally, more recently, the TIP observations from that same cosmic these are of course optical measurements. So they could also be used because Disha, I had seen, had some kind of a plans of putting a photometer on board. So that could also be observed for detection of these ionizing density irregularity. And very recently, this month itself, last 2 months before, we were also having observations of this kind of structures, the IRNSS S-band. So this is a very significant observation because S-band observations of ionospheric scintillations from the anomaly crest like Kolkata has not been very extensively reported. And this new facility which I had talked about in the beginning is coming up, and there are also already some initial results which are published. So this could also be a very important ground-based network, ground-based system to complement Disha. Thank you.
Thank you very much, Professor Ashik Paul. So from the chat box, can we take up a few questions?
Thank you.
Over to Dr. Tarun.
I don't see any question. Probably what we can do is I can request all the participants to put in their question here, and we can take up some of these questions towards the end of the session if the time permits. So, I'll request Professor Paul to respond to in the chat box. In the meantime, we'll start the second talk. There is a question. So now I'll invite Ms. Payal Agrawal for her talk. Ms. Payal is at the URSC Center of ISRO. She is actually an electrical engineer by training and is an expert in the area of satellite control systems. So she will be talking about the aerodrag modeling and its applications in the spacecraft control. Ms. Payal?
Yeah, thank you, sir. Good afternoon. Am I audible?
Yes, you are audible.
Yes, sir. Okay, sir, I would like to thank Science Program Office for giving me opportunity to talk in this national meet. So today I'll give a brief introduction on aerodrag modeling and its application in spacecraft control system. Next slide, please. So I'll quickly go through the content of the topic. So I'll talk about what is atmospheric drag, that is commonly called as aerodrag. A brief introduction on this, then effect of atmospheric drag on spacecraft, and then what are the various factors that are affecting atmospheric drag in the space environment. Then aerodrag modeling for spacecraft with a sample simulation and its application in control system, followed by conclusion. Next slide. So what is atmospheric drag? Most of us might be knowing that it is also called as air resistance and is the force exerted on an object by the atmosphere surrounding it, which acts opposite to the relative motion of an object. That is, it acts against the velocity of the object and tries to slow it down. So among other perturbing forces that are present in atmosphere, this is one of the major cause of perturbation in the orbit of a low altitude Earth satellite. So to account for the various impacts caused by this aerodrag, corrective measures should be taken, which is commonly called as orbit maintenance, and which we are doing frequently to maintain the spacecraft in a desired attitude, orientation, and orbit altitude. Next slide, please. So effect of atmospheric drags includes two major components, that is atmospheric drag force and torque. So as you can see in the figure, FAD is the atmospheric drag force which acts on any object which is moving with a velocity v0 in a direction opposite to its velocity. Whereas TA is the atmospheric drag torque, which depends on the arm length between the center of pressure of the object and CG of the object. So this drag force is the main reason of orbit decay, whereby the orbital trajectory of an object degrades over time until it collides with the object it is orbiting. So as discussed, this is addressed through corrective orbital boost through thruster firings, which will reposition the object in its designed orbital trajectory. Then another component, atmospheric drag torque, acts as a disturbance torque on the spacecraft, and it tends to change or alter the attitude from the desired spacecraft attitude. And in this process, to maintain the desired attitude, our control actuator, that may be a momentum exchange device, that may be reaction wheel, or mass expulsion device, that is thruster, may tend to saturate or will be ending up in the extra fuel consumption. So we need to address these issues before we send the satellite in the orbit. Next slide, please. Now, what affects the atmospheric drag? The major factor affecting aero drag is atmospheric density, which decreases with the increasing altitude. With increasing altitude, atmosphere is less dense and thinner, and more dense atmosphere will cause more atmospheric drag. Also, in addition to atmospheric density, other factors such as spacecraft structure, its area exposed to the velocity are also the factors that dictate the amount of drag acting on the spacecraft. So, with this brief introduction on aero drag, we will now go discuss the modeling of aero drag and its importance. So, being able to accurately predict the aero drag helps in planning the mission and its life, as we can better estimate fuel consumption in order to correct orbit, which gets disturbed due to aero drag. However, aero drag can also be used in a process called aerobraking, wherein this force is used to slow down the satellite in orbit, and it will slowly decay the orbit. That is, apogee will come down, and we can circularize the orbit. So, if you can see the figure towards the right, initial orbit is some 48 hours, that is in yellow color. So, by orienting the spacecraft such that it gives maximum aero drag in the orientation at perigee, we can bring down the orbit from 48 hours to 2 hours, which is that last green circular orbit. So these reasons becomes extremely important to model aero drag for spacecraft and study its impact in the orbit. Next slide, please. So this is the basic aerodynamic drag model, where aerodynamic drag force is given by half rho CdA, V dot n into V vector. So here rho is atmospheric density, which is a function of height and latitude, longitude, and sun activity. CD is drag coefficient, A is area of the object, V is velocity of the spacecraft, and n is the normal vector. So if you see the figure on the right hand side, with the object of mass m moving in the orbit with velocity v, drag force will act in opposite direction of the velocity and tries to slow it down. Hence, rho and CD, that is atmospheric density and drag coefficient, are the critical elements which dictates the atmospheric drag in various phases of the spacecraft mission. Next slide. So this is the atmospheric density model that we are using here. So as we all know that density decreases with the increasing altitude, there are different models available to model atmospheric density. The simplest one is this patched exponential model, which is just a function of orbit altitude. And this is fairly simple and accurate for modeling the disturbance, torque, and force that are experienced by the spacecraft. Other models are Jakia atmospheric model and MSI SE90 model, which also depends on temporal and latitudinal effects and takes sun activity also into consideration. But for all our practical purposes, we are using patched exponential model for modeling aero drag. Right? So this I have just shown what is patched exponential model. So empirical relationship is given as rho naught E minus H naught H divided by H, where rho naught is the reference density as tabulated in the table on right hand side, for H naught as base altitude. H is the actual altitude where we need to compute the density, and capital H is scale height, which is the height by which altitude should change from base altitude to reduce the density by a factor of E. So we have been using this model for our all elementary computation, and we are fairly able to match the results with the onboard observations. Similarly, another factor that dictates the aero drag is drag coefficient, which is a dimensionless quantity. and it is used to quantify the drag or resistance of an object in a fluid environment such as air or water. So this depends on many factors such as geometry, flow condition, that is Reynolds number, Mach number. But for all our analysis, we are taking it in between 2.2 to 2.7, since our more or less our spacecraft structure remains a cuboid, and major contributing surface is solar panel, which is a sheet structure. So for worst case, we will take it as 2.7, and between 2.2 to 2.7, we will tune based on the observation. Next slide. So this is the sequence of aerodrag study that is carried out here for satellite in orbit. So step 1 is collecting inputs required for modeling, which includes spacecraft and other appendages dimensions. So this includes basic spacecraft cuboid and solar panels and any other reflectors, antennas, which needs to be modeled. And then center of gravity of the spacecraft should be known. These two will define the total area of the spacecraft and center of pressure of the individual elements. Then next is orbit data of the spacecraft, which is position, velocity of the spacecraft, orientation of the spacecraft, and orientation of other appendages such as solar panel, reflector with respect to spacecraft. So these last three inputs will define like how much area is projected along the velocity, how much area is contributing for the aerodrag. So and the next step is aerodrag computation for various phases of the mission. So having collected all these inputs, then we carry out modeling of surface, different spacecraft surfaces and aerodrag force contribution from individual surface. So this is based on projected area along the velocity vector of the particular surface. So if you see the figure on the right hand side, if V is velocity of the vector and N is surface normal, then projected area will come out to be A into cos of angle between these two vectors. So that is the area that will be contributing for aerodrag. Then torque will be computed as a vector sum from all individual surfaces of the spacecraft. Having modeled and being computed this aerodrag torque, then we will adopt the appropriate control strategy, wherein we will decide upon the actuators to be used, sizing of the actuator to account for this force and disturbance caused by aerodrag. Then next step is validation and further improvement of the model based on onboard observation. Next slide. So now I'll just quickly show one example simulation of a spacecraft with single-sided solar panel. So a figure on the right-hand side shows a spacecraft cuboid with single-sided 2 solar panels. So this spacecraft is supposed to be put in orbit with perigee height of 170 kilometers. So at this height, as this height is very low, density will be high of the order of -10, AT -10. So aerodynamic torque will be dominant and disturb the attitude of the spacecraft. So to analyze this, all the 6 surfaces of this cuboid along with solar panel surfaces will be modeled, and we'll find out the projected area based on the velocity vector, and then individual components will be vectorially added to compute the total torque on the spacecraft. Now here, since this cuboid is symmetrical, torque given by this cuboid is almost negligible, whereas major contributor is solar panel because of large exposed area along the velocity of the spacecraft and relatively large moment arm. That is difference between center of pressure of solar panels to CG of the spacecraft. That is huge. So this will tend to contribute maximum for the aerodynamic drag torque. Next slide. So these are the simulation results. So altitude considered here is 170. At this height, atmospheric density is around 80 minus 10 kg per meter cube, and velocity is above along roll axis, that is 10 km per second. So as we had seen in the previous slide, solar panel was oriented in yaw pitch plane. So its surface normal is roll axis, which is aligning with velocity vector. So that will contribute for maximum aero drag. Whereas spacecraft body is symmetric, so contribution by body is negligible. So as we can see the numbers, spacecraft body is giving only 80 minus 2 Newton meter, whereas solar panels are giving around 3 Newton meter aero drag torque. So figure on left hand side down is showing variation of atmospheric density with altitude, which is exponentially decreasing with the increasing altitude. Whereas figure on the right hand side shows aerodynamic drag torque. So the peak point is the point of perigee where distance of satellite from the Earth is minimum, that is 170 kilometers. So here we will be seeing the maximum aero drag torque, which is 3 Newton meter. Now, in our spacecraft control system design, we have two types of actuators, that is momentum exchange device and mass expulsion. So this torque is quite high, and momentum exchange devices such as momentum wheel, reaction wheel, they cannot sustain this. Hence, we pre-plan to use the mass expulsion device, that is thruster as actuator during perigee crossing, and after that we can switch over our control to another actuator, that is reaction wheel. So in this way, this modeling and prior estimation of aero drag helps in overall mission planning and planning the mission life. Next slide.
Payal, you're about to, yeah.
Yes, sir. So to conclude this, drag force is one of the major perturbing force on the satellites in low Earth orbit, where atmospheric density is most variable element. And to model this, we are using high fidelity disturbance torque models to estimate the perturbation experienced by the spacecraft, which helps in estimating the fuel consumption for accounting these disturbance torque and forces. And we need to improve our model in the fact that drag coefficient, the number we are considering constant, should be taken as a function structure of the spacecraft and other atmospheric conditions. So we are working towards that, and I would like to ask if anyone has done this and share some references would be of great help, because this is not our expertise domain, sir. So I would like to gather the information and how to how to model drag coefficient for the satellite. So with this, I would like to end my talk. Thank you so much.
Thank you, Payal. It was very informative talk. Any questions? I think we can take one or two questions, quick questions. Yes, there is one question from Professor Dibyendu Nandi. He asks, for estimating dynamic satellite drag and satellite orbital decay, one must have continuous in situ measurements at the relevant altitudes. I'm aware that the ESA swarm satellites provide such data. Does India have satellites providing this data? If so, at what altitudes?
Sir, we are continuously having this orbit estimation by our flight dynamics group, wherein we are getting the information of altitude, that is position and velocity of the spacecraft. So based on that, we are able to compute that what altitude it is flying, and then we can estimate the drag for that particular altitude, and also orientation also we take into the consideration.
Okay. A related question to that is that in context of geomagnetic storms, because these storms also create changes in the density, atmospheric density, and therefore in drag. So is there any expertise within ISRO to assess such changes in density or drag, satellite drag, because of geomagnetic storm?
Okay, sir. Right now, currently in URSC, we are not doing this study of geomagnetic storm, but I am sure that VSSC, who are experts in this launch vehicle, they are definitely doing all these. They are taking these factors into consideration while doing the design. But yes, we have to improvise a lot on this modeling.
Okay. And one more quick question. I wanted to ask whether how frequently for a typical satellite, say at 400-kilometer orbit, how frequently do we need to do these drag corrections?
Sir, yes, sir. So, like it highly depends on what structure what is the structure of spacecraft, how asymmetric is that. So, if we consider nominal fairly good symmetric spacecraft at 400 kilometers, twice or thrice in a month we are doing these orbit corrections.
Okay. Okay. Yeah. Thank you. Thank you, Payal.
Thank you, sir.
Yeah, there is a suggestion by Dr. Geeta Vichare in the chat box. You can have a look at the chat box.
Okay, okay. Thank you, sir.
And we move forward to the third talk of this session. This is by Dr. Debroop Hui, who is a professor in Ghani Khan Chaudhary Institute of Engineering and Technology. Dr. Debroop is one person who has expertise in both areas of the that is the science and technology of aspects of plasma, the measurements of plasma. So he gets the better view of both sides, what we want to do with respect to Disha. So we would like to hear from him when it comes to what is involved when it comes to plasma measurements. Professor Hui.
Hello, am I audible?
Yes, you are audible.
Yeah, thank you, Dr. Tarun. Yeah, thanks for that nice introduction. Just a small correction. I'm an associate professor here and I teach physics to undergrad kids. So yes, thank you, Science Program Office ISRO for inviting me to talk on this topic, spacecraft charging in the context of plasma measurements. Since morning, we have been hearing a lot of physical processes in the Sun-Earth system. Experts have spoken about why we need this Disha mission. And here in the evening session, we are hearing, just like Payal has very nicely raised an issue of atmospheric drag, we will focus on some of the operational side of the mission and the necessary risk that we take and the return, the gain that we get in the risk that we take. So some of those topics I will try to cover. But before I start my actual presentation, this is my motivation and pretty much this summarizes my talk. This comes from Dr. Kunz, who is the system manager for International Space Station for the last 20 years for the space environment sector. And he says, people say that the space environment destroying spacecraft. And I maintain it really doesn't. The design and operation team destroyed the spacecraft by ignoring the environment upfront. It's 100% human error. But that's just me. It looks that way to me. You can use in-flight operational hazard controls, and at the end of the day, you want to test like you fly, and you fly like you test to the extent possible. So what he is telling us is, before we throw up a spacecraft in the space, in the place where we do not have any physical control, much physical control, we must be aware of the environment and the challenges that this piece of metal or electronics that is being thrown in the space, what it can encounter there, and we should be able to address those issues. If we do not do it, then we pretty much are responsible for any kind of destruction that happens or harm that happens to the spacecraft. So this is why we are here estimating the risks and the necessary steps which needs to be taken. And one of them is estimating the spacecraft charging as a whole for the spacecraft. And also for this talk, I will try to focus, as my title says, that how this spacecraft charging will interfere with the scientific measurement, which are very important and crucial for this mission. But before I even start defining spacecraft charging, which may be something very new to many of us, I want to start with very basic example. When you boil your tea and you put a teaspoon on that boiling tea, what happens? It's a metal, good conductor of heat, so it becomes hot, and it becomes hot until it reaches the temperature of the boiling water. It's the same thing. It's a conducting surface. A satellite is a conducting surface, and we are putting it into a plasma environment, which is nothing but a ionized gas. It's a conducting gas. So naturally, it will accumulate charges on it. It's nothing fancy. It's very easy to understand that if it is both of bodies are conducting, if one has different potential than the other, then charges will transfer just like heat transfers from the boiling water to the spoon. So the processes by which the spacecraft body or any part of the spacecraft, including payload, develops an electrical potential or voltage with respect to the surrounding plasma is called spacecraft charging. If different electrically isolated parts develop different potentials, which I tried to kind of show by cartoon here, by color coding, that if your different parts of the spacecraft has different potential, which are electrically isolated, then you have a situation called differential charging. And if the differential charging are too high, we know that even from our common experience here, that if the voltage difference is too high, we have electrostatic discharge, which can burn up to the whole spacecraft. So spacecraft charging happens because of charge exchange between the spacecraft body and the surrounding plasma. Eventually, they reach an equilibrium when the potential of them become equal. And just by cartoon, I tried to show this, that the spacecraft is exchanging charge with the surrounding plasma. It can take in electrons, it can give out electrons, or you can think in terms of ionized proton, etc. So the equilibrium where it comes to that we are talking about is called plasma potential. That is where the spacecraft is at the potential of the plasma. But at that time, a lot of electrons comes, because I'm not going into, okay, for this talk, because I know my audience is broad, coming from a broad sphere. So I tried to keep mathematics as minimum as possible, and also technical things as less as possible, so that we have an appealing understanding of the subject before we get into the technical details. So the only equation I promise here is this one, which is very easy to understand. It says that at the floating potential phi 0, when there is no current or no charges are getting interchanged between the spacecraft and the plasma, we have contributions from each kind of current which can come. Electron can come, ion can come, secondary electrons due to electrons and ions can come, backscatter electron current, photoelectric current because of the UV spectrum of the solar radiation. Every kind of current that you can think about, they should sum up to 0. Okay, it's a very easy to understand thing. So that potential is floating potential, and you can see each of this term, these currents are function of the floating potential. So the whole purpose is to measure the current and estimate the floating potential of the spacecraft. That's what we are trying to do. Now, the spacecraft is a huge body, metal body, which is continuously exchanging charge with its surrounding. If the potential is not same, but we cannot draw the current from every point of the spacecraft. That's why we need a special instrument which does basically the same thing, same mathematics, same physics, same methods it follows. We are using this instrument invented by Langmuir around 9 decades ago, 90 years. We are probably going to celebrate centenary for this wonderful instrument. It's working. It started working in laboratory plasma. Now it is working in space environment. Here in the left, you can see it is International Space Station. Astronauts are making an extravehicular work. And on the top, we have this here, Langmuir probe. This is what it looks like basically. You have this square here. If you can see my pointer of the mouse, the square here, this is the Langmuir probe, and it is separated from the main spacecraft, because you see, whenever you dip a metal structure, conducting surface in the plasma, I will go back to this picture. You see this box here. This box, this is Microsoft PowerPoint. It was very nice to give me this advantage. you can add glow to the side of it. Okay, it looks like a halo. So this is exactly how you have a sheath region. We call it sheath region. Usually plasma is quasi-neutral. That means the number of positive charges is equal to negative charges. But in the sheath region, that quasi-neutral condition is violated. So actually, even though we are trying to study the ambient plasma, around the conductor, it is kind of, we do not have that quasi-neutrality of space plasma, but we tweak it around by taking different assumptions and try to measure the ambient plasma. That's the whole business. We do it this way. And here in the bottommost picture here, you can see we have a, this has been talked about in the morning also. Raju sir has shown this picture to you. It's a Langmuir probe used by PRL for around 40 rocket launches. So we have a very rich heritage here in India to use this instrument. But basically, what it does is same what the whole body of the spacecraft does. It exchanges currents and gives us information about the potential of the spacecraft. So this is a specialized instrument which we will use for the, even Disha has proposed this, so it will use to determine the floating potential. And here you can see the collected current is a function of plasma temperature, geometry of the probe, plasma density, its material properties, very importantly surface properties, and effective collection area, etc. I'm not going into the detail of the technicalities here, but this is just to give you an idea that we have different parameters to look into before we calculate the actual current that is being collected by the instrument. Here, the Sun-Earth picture has been shown by Geeta, has been shown by Dr. Nandi also, Professor Nandi. Why I am showing you is just to tell you that you can see different region, they have different statistically typical values for plasma parameters, plasma sphere, plasma sheet, solar wind, you have different parameters for different regions. So when you throw up a spacecraft with the instrument to measure certain parameters there, you must know what kind of range of values you want to measure. So that will give you an idea where your spacecraft is going. Now, when the charge is getting accumulated, it is mostly because of electrons, kinetic energies, and the flux of the energetic electrons, which are responsible for this charging. Now, when we talk about charging in our community, we generally talk about surface versus internal charging. When this electrons kinetic energy is up to 50 keV, then we have kind of surface charging. Only the surface gets charged. But 50 to 100 keV, the powerful, the highly energetic electron tries to penetrate the surface of the spacecraft. You have instrument, they will try to penetrate the surface and go deeper inside the spacecraft body. 100 keV, it usually penetrates deeper. That's why engineers put a lot of thick aluminum sheet to stop this. They are very much aware of all these things. And if you have even higher energetic particles, like in the order of mega electron volt, they are practically threatening. And the geomagnetic storm and the substorm that were being spoken in the morning, during that time, we can experience such highly energetic particles in the outer atmosphere, in the outer space. Now, why should we care? Now, see, this charge being transferred, it's because of the flux and kinetic energy of high energy charged particles, local plasma density and the temperature, and then you have an E cross B motion of the spacecraft. The spacecraft is moving in the Earth's magnetosphere. You have Faraday induction, so that also contributes to an electric field, and that also makes the charges to move. And operating high voltage systems can cause currents to flow through all parts of the spacecraft and sometimes damage it. The anomalies which it can cause are not restricted to avionics hardware failure, structural damages because of electrostatic discharge, electrical power system failure, communication or control system anomalies, and focus of this talk, unreliable measurements by payloads. Just to bring this to your notice, INSET 2D, our own satellite, it was launched in June 4, 1997, exactly after 4 months, October 4, 1997. it stopped working because following a power burst anomaly and associated problems. So what it is believed here, you can see I have highlighted this here in yellow. It was because of a spacecraft charging problem that we lost the whole spacecraft just within 4 months. And this table here shows a list, it's just a very small list. It shows the list of problems that different missions experience because of spacecraft charging. And all the cross that you are seeing there, they are the missions which has been killed by the spacecraft charging. It's a very, very expensive affair in the spacecraft industry. I'm not showing you in terms of $1 million, but that's an astonishing figure. Now, coming to the plasma measurements and its connection with the spacecraft charging, there has been a lot of studies. I'm just highlighting one of them to draw your attention. This comes from this paper, Effects of Spacecraft Potential on Three-Dimensional Electron Measurements in the Solar Wind. A few authors, this highlighted part, I want to read it out to the audience. A few authors have noted the danger in equating particle trajectories measured at the spacecraft with the actual particle trajectories in the ambient plasma. These authors has calculated possible corrections to moments of this electron distribution due to the particle trajectory altering effects of spacecraft charging. So here you can see, as I was saying, that heat that we talk about, or the electric field that the whole spacecraft generates, it actually alters the trajectory of the incoming charge, particle, electron, proton, ion, whatever it is. It changes it, it's altered. So it's very difficult to actually understand the ambient plasma in the space. So lots of corrections are needed, and this is exactly what we would focus on for this Disha mission also. I'm not going to read this out. This has been read out by Raju sir in the morning. Here are the parameters to be obtained from Disha mission: plasma densities, amplitudes of plasma waves, plasma drifts, electron temperature, neutral and major ion components of the densities, air glow intensities at visible and X-ray spectral regions. I have colored them in 3 different colors, and I'll start from the bottom. This air glow intensities, they mainly collect photon, that's my understanding, which is a neutral particle, so they need not be disturbed by the electric field or magnetic field around. So I think they are quite safe from this perspective. Neutral and major ion composition and density, that the spectrometers, I don't have much idea about the instrumental detail of this particular instrument which are being flown on Disha, but I kind of think that at some point, I think the PIs need to think about this. So I have put this in dark yellow, but for the top 4, plasma density, amplitude of the plasma waves, plasma drift, electron temperature. So I think I'm talking about this instrument here, which I marked in red: high frequency Langmuir probe, ion drift meter, electron temperature analyzer. These instruments, so far my knowledge goes, will definitely need to take care of the spacecraft charging. And for them, the floating potential information which comes from both ETA, I was very glad to see that ETA will give us an estimate of the floating potential of the floating potential of the spacecraft, and Langmuir probe also. We need these 3 instruments need to take care of this spacecraft charging problem. So Disha H and Disha L. Okay, sir. Thank you. Disha H satellite with circular orbit in the inclination greater than 85 degrees. So they will experience a lot of cold and hot plasmas in the polar region. And Disha L will fly at around 400 kilometer, 25 degree inclination, will experience higher radiation doses, and also both of them will see Appleton anomaly or fountain peak. All the in situ measurement, plasma measurement that payloads making using electric field can possibly get contaminated by this spacecraft charging. It can deteriorate further during geomagnetic storm or substorm. So an estimate of the charging by means of measuring floating potential is very essential to understand the level of contamination in measurements. Eventually, corrections are needed. I, as an example, tried to show you something from my own work when I did this modeling work for International Space Station, which is being used by many people I see. how this is an easy way to estimate in a very without going into a lot of complex mathematics. Is here you can see we can break down the whole international spacecraft or any satellite into different parts like solar array, conducting surface, and the insulated surface. And here is our probe, Langmuir probe. Each of these surface exchanges charge with the surrounding. So we have electron, ion, and photoelectron current for each of this sector, which you can convert into lump element circuit theory and then do some analysis. So we will have resistances, impedances, capacitances, but the complexity of this electric circuit, it looks electric circuit, but you have to understand that the circuit parameters are not static and depend on the space environment. So these values are continuously going to change with the space environment. For example, here you can see from some of our simulation results, solar array capacitance, oxide layer capacitance, sheath of the conducting surface, sheath of the ion insulated surface, solar array sheath. So these values continuously change with plasma density, temperature, and so on. So concluding remarks, test like you fly and fly like you test. Every IV curve, that is the current voltage curve generated from the LT, will help estimate the floating potential of the payload. ETA will also provide floating potential estimate from Disha. So the mission specific advantages, it will help estimate the local charging level and eventually quality of data, especially during geomagnetically disturbed time, will improve a lot. Long-term science benefit, the knowledge learned will help in every such scientific measurements in future missions. And long-term engineering benefits that I see, the data set and the methodology that we develop here indigenously. The data set will give good insight into charging issues of any LEO space mission in future, like Earth observation to defense satellite. That's all from me. Thank you.
Thank you, Dr. Debrup. It was a fantastic talk, and on an aspect which is very, very important for the satellite missions that we are planning. I'll just have a look at the questions. I don't see any question in the chat box. I have a question, if I may. No, there is a question. If we isolate the payload like LP, DM, and ETA with the spacecraft, can it reduce the charging measurement errors? Asked by Pankaj.
Yes, without any doubt, that is the strategy most people do. And even in the picture that Raju sir was showing in the morning, that this Langmuir probe are on the end of a stick. So that's what you do. You try to take it as much as possible. Okay, so from here I'll try to go back to one of the figure that I shared. So this is what they do. They put it on the end of a stick. So you isolate them from the sheath of the whole spacecraft, which can be considerable, and you have a very smaller sheet to take care of. So that way we do a compromise. Even I saw ETA, there is a special requirement in your document. I saw even they have proposed something like this. So yes, I'm thinking ETA is a mature instrument which they know about this problem. So that's why this special requirement came. That's what I'm thinking. Thampi madam would know much better than me. Yeah, I'm looking forward. Yeah, thank you.
Thank you. Thank you, Dr. Debrup.
Thank you.
So with this, I think we have come to the end of this session. So now I thank you once again, all the speakers, for the fantastic presentations. And over to Dr. Das.
Thank you very much, Dr. Tarun, to have driven it so nicely and meticulously. And thank you very much to all the speakers, Dr. Ashik Paul, Ms. Payal Agarwal, and Dr. Debrup Hui, for this informative and so beautifully explained technical aspects. And this concludes the session 3, and we are going to the session 4, which is a panel discussion on interministerial views for the applications of near-Earth space observations from satellites. And now I welcome everyone to this session. So this is a special session of this national meet, which is dedicated to this panel discussion in connection with the observations of the effects of the space weather events on Earth, as we have discussed, which is first captured by the Earth's upper atmosphere. And that's why the need for the satellite-based Aeronomy observations is felt and constitutes the background for the Disha H and L mission, which are conceptualized by ISRO. Today, we are happy to have here with us senior officials from several ministries from government of India who will share their valuable views on the importance of the space-based Aeronomy observations to study the effects of the space weather events. We have as our honored guests in today's panel discussion, Shri Sanjay Agarwal, DDG from the Department of Telecommunication, Air Vice Marshal Devi Kaur, Aviation VM, who is the Director General from the Defense Space Agency, Shri Anurag Gupta, Assistant GM Gagan, representing the Ministry of Civil Aviation, Dr. Ashok Kumar, Deputy Director General, Bureau of Energy Efficiency, Ministry of Power, Dr. Arvind Singh from NCPOR and Dr. John P. George from NCMRWF, representing the Ministry of Earth Sciences. Dr. Arvind Singh is from NCPOR, Dr. George is from NCMRWF, Dr. Akhilesh Gupta, Senior Advisor, Head Policy Coordination and Program Management Division, Dr. Gaurav Agarwal, both representing the Ministry of Science and Technology, Dr. Manoj Kumar Khade, Senior Director HOD, Emerging Solutions, and Ms. Akshara Kaginalkar, Senior Director of HOD HPCC Group, CRAC Pune. Both of them are representing the Ministry of Electronics and Information Technology, and Ms. Anuradha Agarwal, Additional Director General Technology, Prasar Bharati, who is representing the Ministry of Information and Broadcasting. I welcome all of you, respected madams and sirs, to this panel discussion. Thank you for being with us today. And before going to the panelists, let me say a few words about the organization of this panel discussion session. So we have representatives from 8 ministries in total. I will request each ministry, one after the other, to please share your views. Not necessarily you may have to share a PowerPoint presentation. If you are speaking out your views, that is also okay with us. Each ministry is requested to kindly speak for a maximum duration of 10 minutes, and thus we will have 80 minutes to complete listening to all the 8 ministries. Scientists from the ISRO payload team will also be available in this forum for discussion, and at the end, they may also provide a few information or say a few words before we conclude this session. So with these few words, I start this panel discussion. And first, I will go to the Ministry of the Department of Telecommunication, Sri Sanjay Agarwal, sir, for your views. Over to you, sir.
Thank you very much. Am I audible?
Yes, sir.
Hello? Yes. Okay. So thank you very much for allowing me to participate in such a wonderful event, and more so that you have allowed me to express the views of the Communication Ministry here. It is very difficult to speak something in the presence of so many senior scholars and academicians and professors from esteemed research institutes. And however, I'll cover my concerns about 3 points. First is the probability of disaster happening due to solar superstorms. Second is the need to increase coverage, bandwidth, and reliability of satellite communication. And third is that research in radio wave communications. So first of all, coming to the possibility of disasters, as we are seeing that the dependency of the social and economic activities is greatly increasing on the communication network, And with the advent of IoT and 5G and other technologies and GPS-based controls, we can say that the lifeline is now running around the communication technologies. And in such a situation, any event like Carrington event of 1859 may create a lot of issues and may create a kind of stopping of the entire social and economic activities for a period of, say, months together. And because the reasons are that the communication devices are highly fragile. They generally operate only on 5 volt or 12 volt. And their protection devices are going to take care of some few hundred volts. So in case if there is a superstorm, not even as big as Carrington event, then also the devices, the end devices may get impacted to a large extent, and this may result into a major disaster. That means stopping of all of the activities, as we have seen recently during the COVID time, that we didn't expect that some health hazard will really stop the life of everyone. So similar kind of event may happen in communication sector. Secondly, communication is solely dependent, rather I can say that mostly dependent on the radio communication as well as the satellite communication. So these are the two regions that anything of any superstorm may affect the communication network. And in case there is a damage to the devices, then it will take a number of days, maybe months, to again restore the services. Now for disaster management, what we require that there are two parts of disaster management. One is alerting, and then second is the preparedness, being prepared for the disasters. So we look forward towards the twin satellites of Disha, that yes, we can be having a lot of research-based data about the kind of things which may happen if any of the superstorm happens, and what preparations, what precautions, what preparedness we should have. That is one thing which is required. Secondly, the alerting system. If we get an early warning, as we are getting from IMD and for all other sources, so of course satellite-based early warning systems are there, but we have a more accurate and more time-based alert, so that the things can be taken care of. So that was the first part about talking about the possibility of disasters and then being prepared for that and having an alert mechanism. Second is that now we are more and more depending on the satellite communications, and because there is an increasing demand of high bandwidth in the remote area and reliable communication, which is really, I mean, which can be provided by satellite communication nowadays. And now we are seeing that more and more LEO satellites are being launched in the near future. And in the remote area, the connectivity by radio is also very difficult as well as costly as compared to satellites. So we require some more research in this area, so that the more reliable kind of communication can be provided. Third is that in the radio wave propagation, again, there is a demand from world over that the more and more channels are open for communication for high bandwidth transmission in radio also. So there are many frequencies which we are not using as of now because of some ionospheric or other kind of interferences. So if there is some more research, then we will be really in a position to operate on those frequencies. This is from me, and that's it. Thank you very much.
Thank you very much, Sri Sanjay Agarwal, sir, for very briefly telling from the communication perspective how important this kind of observation would be. And I'm sure this is just the beginning, because once we start getting observations and we make it a practice in a programmatic fashion, this will aid to the facets which you have just mentioned. All of them are very much, just like backbones of our country. and they will be strengthened with such kinds of mission. Thank you very much, sir, for your views. And we go to the next speaker from the Defense Space Agency, Air Vice Marshal D.V. Court, Aviation, VM, Director General, sir. Over to you. Air Vice Marshal D.V. Court, ji, are you there? Okay. Okay, we'll get back to him. Meanwhile, we go to the Ministry of Civil Aviation. We have with us Shri Anurag Gupta, Assistant GM, Gagan. So over to you, sir. We are eager to listen to your views. We'll check back. So, do we have Dr. Ashok Kumar, Deputy Director General, Bureau of Energy Efficiency from Ministry of Power here?
Yes, Dr. Das.
Yes, sir. We would like
Am I audible? Am I
yes,
audible?
Sir. Yes, you're clear, sir.
First of all, thank you, Chair, for the invitation. And it is really a learning for people like me. And I also join Shri Sanjay Agarwal to not to venture into the technical aspects of the subject that has been deliberated so far. So I would limit to my area of work representing Ministry of Power. So we see the application of satellites, images, particularly for in the power sector from two perspectives. What I would say is one from the supply side and for the demand side. So for all the supply options that we cater to, like thermal power plants, right from assessing or exploring the resources like coal or transportation of the coal from the pit heads to the say power plant situations, all these can be enhanced very effectively to the availability of the information that we get from the satellites. As we move forward, we would have much better understanding of the location and also the optimization. So that is where we look at the application of satellite imagery, and also in the hydropower sector to assess the potential, assess the level of inundation, volume of the reservoir, and several other type of vegetation that are going to be affected, so on. So satellite images are very, very effective in all that activities that the Ministry of Power does. So there we see, then we come to the current times of renewable energy. You would appreciate that the renewable resources can also be kind of through the satellite information, we can have better assessment of the resources that are available across the country, and so we can plan accordingly. So from the supply side, that what we see is that a lot of application from the imagery or the information that the satellite can provide for the power sector. And towards the demand side also, the way we can distribute, way we can transmit the power from one place to another. Certainly the topography and geology of the positions of transmitting towers and everything needs the information of the ground, of the place. So again, the information that we get from the top is very, very crucial. So, and that way, how we distribute ourselves. For example, just imagine a possibility of putting a transformer in a locality. We can, if we have a view from the top, you can have very much better assessment of the situation than you are looking from a horizontally. So those are the fundamental, I think, advantages of the technology related to satellite that can provide us the kind of edge to the traditional ways of doing things, so that we can better use the resources and serve the community better than what we have so far been doing. So this is, I think, just a few points, how we use the land, for any purpose, not just for the power sector. So the satellite imagery is very, very important. So, but just to end the point of my intervention is that often such informations are very difficult to understand. You have thermal images, you have different frequency images and different color coding, which possibly, of course, learned people like you may be able to understand very well. But even at the middle level administration, semi-learned people in the government needs little more kind of a, you can say, a little more of a simplification, so that those are well understood and also well utilized. So one is the such useful information's availability is very critical, and also available in the forms that the people can use effectively in a very useful way. If those are the the experts of the August experts here can look into those aspects, it would be of immense use. And just I am limiting myself through the use of energy and energy's usage, efficiency, distribution, that all that can be touched by some of the aspects of satellites information. And as you know, that we are moving further and further into the more towards the electrification of life, and the communication is getting so much embedded in our lives. So the satellite is the possibly the you can say a heart and brain of a thing that can circulate or keep us alive. So since I would just at the end thank for this opportunity, and looking forward for any knowledge, any learning from the group here and the institutions in the later part as we move forward. Thank you very much for the opportunity.
Thank you very much, Dr. Ashok Kumar sir, for your views. You have told about the space-based observation platform, especially the imagery to identify the resources and connecting two locations with electrical power lines. So in addition to that, this mission will also be helpful to understand how much vulnerable these electrical lines which run over the Earth's surface to the space weather events. So we take forward your valuable views, sir. Thank you very much for joining us today in this discussion. And we go to our next ministry, Ministry of Earth Sciences, which is represented by Dr. Anand Singh from NCPOR and Dr. John P. George from NCMWF. Over to you, sirs.
Is it okay? I can make one show one PPT. Is it okay?
Yes, sir. Please.
Am I visible?
Yes,
my PPT is visible?
Yes, visible.
Yeah, okay. I will quickly go through. See, the Ministry of Earth Sciences is mandated to provide services for weather, climate, ocean, and coastal state, hydrology, seismology, and natural hazards. So this is the this is the main mandate of the Ministry of Earth Sciences. So various what you can say organizations are attached to this ministry. They are doing the they are giving the they are doing the research and development and the modeling and the forecasting of these various components of the Earth system. So in that aspect, as already we discussed that as we know that it affect the critical infrastructures. The space weather can affect the critical infrastructures, whether it's communication systems or transport or energy or satellite. In that aspect, in the Ministry of Earth Sciences is highly dependent on the satellite observations of the Earth systems, in whether it's atmosphere, land, or ocean. It is more than 95% of the observations we are using it for the forecasting or understanding of the weather or the ocean conditions, ocean state. Everything is coming from the satellite observations. So any impact on the satellite observations is very critical for the Ministry of Earth Sciences operations. That is the most important thing. Second is that the ministry is involved in making observations using different using different components of the Earth systems, using various instruments, including of course the microwave radars. So and many of the observations are from the polar regions, whether it's from South Pole and in the Antarctic region and in the North Pole, near North Pole regions. So these where the space weather matters more. So these activities can be affected by the adverse space weather. So another thing is that we are highly depends on the high performing computing and communication infrastructures. We are getting data from various parts of the globe. So all these things will be affected if that is affected by the adverse space weather. But the impact of the solar variability, which is solar irradiance on the weather and climate, is the solar cycle and all those things are very, very small, and it is not a very, we are not taking into account of this one in our weather models, especially in the climate model up to a certain limit. So I am not going to what we can do or anything, but the only thing is that one component is that the forecasting using the forecasting of the space weather using the physical based or the physical based models. So there the coupling of the atmospheric models are needed. So in that context, the ministry can MOS can contribute to the forecasting systems of this space weather. So another thing is that as I already mentioned, that MOS is mandated to explore the polar regions also. So the polar regions are more susceptible to the space weather. So my colleague Dr. Anand Singh will quickly go through some of the aspects which is very particular to the polar regions. Over to Dr. Anand. Dr. Anand?
Am I audible, Dr. George? Can you please confirm?
Yeah. Yes.
Okay. All right. I would like to thank ISRO for this kind of opportunity to the inter-ministerial representatives. And having worked closely in the space weather, I am delighted to see colleagues from PRL, SPL, IIG, and such institutions, and hearing their presentations. On behalf of Ministry, this presentation where Ministry involved and where we see scope for improvement in space weather observations and forecasting. Basically, Ministry of Earth Sciences has pole-to-pole presence, right from Arctic to Antarctic and also the oceans in between. So, I mean, we understand that typically the infrastructure in the tropical region is not much affected by the space weather events, but the polar regions are highly susceptible to space weather events, especially for communication, navigation purposes. Dr. George, can you switch the slide to next? Right, so this is just a screenshot of
Ministry presents in Antarctic, Arctic, and Himalaya, and also a slide on Whistle, which is standing close to Antarctic coast. Next slide, Dr. George. Now, Ministry as such had very limited workforce on space weather. But in Antarctic and Arctic, there are more than 10 national and international organizations are working closely with the Ministry for research in space weather and atmospheric sciences in Antarctic and Arctic. So there are a suite of experiments like radar, magnetometers, GPS receivers, gyrometer, all-sky camera, etc., which work around the clock. Madhuri. Next slide, George. Right, so this is where we see close involvement of a scientific community for the polar program, especially which is in Antarctic and Arctic. The satellite footprints are very limited in Antarctic, so the communication very frequently, especially the short-range communication, very frequently depends on high frequency and very high frequency communication, HF-VHF, what we call. So, I mean, it used to be in earlier times of expedition, the HF communication was quite frequently used, but we understand that, and we saw in an earlier presentation from a scientific committee that there are inherent issues with the HF communication, especially during the disturbed atmospheric conditions. So for that reason, now, and also with the advancement of other modes of communication, like satellite communication, HF communication has been dismantled. VHF also faces issues during space weather events whenever it's extreme. So that is one place where I think, and also it was pointed out by the earlier Deputy Dr. Agrawal, Sri Agrawal, that communication is one place where we should be looking more for active involvement, especially. Navigation, we are highly dependent anywhere on satellite navigation. In places like polar region where compass mostly don't work or are not reliable, that's where GPS, handheld GPS is mostly used. So there are dump locations for like fuel or pipelines. So those require very high level of accuracy for the locationing, basically, location or positioning. So we understand that the navigation is not reliable, especially the times when there are extreme events. So for that, we would probably be interested in getting more better picture on the navigation. Next slide, please. Right, and Dr. Nandi highlighted that there are, especially for the flights, navigation and communication becomes a problem. In addition, the radiation dosage that passengers receive. So especially for polar regions where persons travel about 8 to 10 hours in the polar region, so that's where the radiation dosage can reach up to one chest X-ray in about 8-hour flight or 10-hour flight. So, and this kind of forecasts are not incorporated in flight operations. So I think it would be great if we understand and have prior information. So if possible within limits, they would be interested in avoiding unnecessary radiation exposure to our crew, which is being deployed in the polar station like Antarctic or Arctic, wherever it is. So with this, I think I'll close this presentation, and I would request ISRO that with coming Disha mission and Aditya L1, I think it would be a very good move for the scientific community. And I would appreciate if the data sharing policy can be,
share with the interested party that this is where data would be available. So that would be a great move for researchers. So with this I would like to close. Thank you very much.
Thank you very much, Dr. Anand and Dr. George, for this comprehensive presentation. And we would like to mention here that all these data which you have mentioned will be made available in the public domain. So that is one part of it, and very important takeaways from your views. I understand one is for the overall understanding of the Earth system science, you need to have a very clear understanding of the solar forcing onto the Earth's upper atmosphere. And also, very important point you have mentioned that not only the forecasting aspect of the space weather events, but also how to couple the atmospheric models with the space weather models, and how to quantify the effects of space weather events to what is really touching our lives. So this kind of connection is really an open area which we understand, and this is one of the areas where we can really join hands. And thank you very much for your views in this regard. And we go to our
thank you very much.
We go to our Ministry of Civil Aviation, Shri Anurag Gupta, Assistant GM Gagan. Are you there, sir?
Yeah, I am there, sir. Actually,
Yes,
there
sir,
was brief. Yeah, am I audible?
Yes.
So I will make some brief presentation. I will share my screen. So is it visible, my slide?
Yes, sir.
Good afternoon, one and all. First of all, thank you ISRO for giving me this opportunity for presenting my view from Airport Authority of India. I am representing Ministry of Civil Aviation, AI under being under CPSC under Ministry of Civil Aviation, and we are one of the ANSP. We are the NSP who provide the navigation services in over Indian region. So my talk will be as given in the agenda, application of near Earth space observation from satellite, from civilization point of view. So how we are affected by the space weather and what we expect from the Disha project which is being launched by the ISRO. So these are the contents of my presentation. Introduction, the ANS services which is provided by Airport Authority of India, and the system and services affected by space weather which we use in AI, and requirement of space weather monitoring and prediction. So what is our requirement for space weather monitoring in terms of space weather monitoring and prediction? So as I told this, I am from Airport Authority of India. It is a central public sector under the Ministry of Civil Aviation. So AI is responsible mainly for creating, upgrading, maintaining, and managing civil aviation infrastructure in India, and it also provides the CNS ATM services, that means communication, navigation, surveillance, and air traffic management services over Indian airspace and adjoining oceanic area. So being ANS provider, so here I will talk from the point of view of the ANS, air navigation service provider, because here we use the technology which are satellite based technology and radio. We deal in the radio communication. So these are the technology which are affected by the space weather event. So just I will give a brief introduction about the technology used, equipments used in Airport Authority of India for the in the communication. So we use the this communication devices, communication services for providing communication between pilot and air traffic controller. And for this service we use mainly two bands, HF band which is in this frequency range, and VHF band is 1182 137, and we provide the search and rescue service which is which is given then in the this frequency band. Other than that, there are one frequency band 1200 to 14 megahertz, which is used inside the aircraft. So since I am representing Ministry of Civilizations, I thought I will cover the other than AI. Who are the user of the frequency? Where we use the different. So for the sake of completeness, I am covering those frequencies. And we use the satellite communication. Then these are the frequency band for the satellite communication. And for navigation point of view, we use the terrestrial navigation system, that is ILS, that is Instrument Landing System, DVR, DME. All these equipments are used for navigating the aircraft. And we use the satellite-based navigation system, that is Gagan. That is Indian SWAS. Gagan is GPS-aided geo-augmented navigation, which is a satellite-based navigation system, which is actually this project is being executed in joint effort with ISR. So currently I am posted in Gagan. So I will be mostly talking about the Gagan because Gagan is the services provided. Gagan is mostly affected by the ionosphere, and the ionosphere is a major area in the Gagan. So we are the you can say biggest victim of the ionosphere and the space weather events. So frequency used in navigation systems are low frequency, medium frequency, VHF, UHF, and L-band. L-band mainly for GNSS, that is GPS, GLONASS, and Gagan. And we use this L1 frequency in Gagan, L1, L2, and L5. So we have the 3 GEO satellite which broadcast in the L1 band, L1 frequency, that is 1575, and L5 1176. These are the we have 3 Gagan GEO satellite which broadcast in L1, L5, and since we augment the GPS signal, so we use the L2 frequency also. We have reference receiver which receives the signal from L2 frequency. So we deal with all this L1, L2, L5 frequency. And apart from the Gagan, we have the GWAS system, that is ground-based augmented system, which is GPS based, but it is a local augmented system in contrast to the Gagan. Gagan is a wide area augmented system which provides the navigation services over the Indian FIR, over the Indian airspace, including the oceanic area. And we have other frequencies in the surveillance which are used by the radar, like 1215 to 1400 to 2700 to 3000. So we have different type of radar used by the ground. The ATCO. The ATCO will track the location of the aircraft in real time using the radars, and we have the approach radar also, which are used for landing purpose, and there is airborne weather radar also with aircraft images. So my idea of giving this brief introduction is that these are the frequency used by the Airport Authority of India in particular, and and by civilization in general. So later part of my presentation, I will talk about which are the frequencies which are affected by the solar storm. So these are the system or services affected by the space weather. So as I told earlier, Gagan is a GPS augmented navigation. It provides the satellite navigation for the aircraft over Indian airspace. So as I think people may be aware, the GPS we use error in the GPS, and in GPS the major source of error is ionosphere. So model, that is mathematical model, maybe aircraft or ground-based user, which has the Gagan receiver. So as my other speaker in the morning, they have talked, the Indian region, the ionosphere is very disturbed. We have equatorial Appleton anomaly, which is characterized by the evening morning to till evening, the TC value increases because of this anomaly. So we have the peak in the noon, noon time, and we have other problems like scintillation, which is the post evening phenomena. And my other speakers also spoken about scintillation, and we have another anomaly like depletion, which is like a depletion bubble, and those also mostly post evening phenomena. So these equatorial anomaly and scintillation, depletion, all these events are there even in the calm day, and even in the quiet ionospheric day. Even there is no solar storm also, because India being in the equatorial region, mid latitude region, low latitude region, we are affected by all these anomalies. So Gagan, we have the model ionosphere model. We try to model all this abnormality in the ionosphere, and this is the model can take care some kind of anomaly and up to take care the disturbance up to some level. But whenever there is a solar maximum, solar cycle is there, when solar disturbances are at peak, or because of that there is a solar there is a because of that there is a solar disturbances, or because of that there is maybe the uh, solar geomagnetic storm, as we heard about this storm, which mostly affect the ionosphere layer of the atmosphere. So because of that, our model we are not able to correct the error 100% because of error, because our model it has assumed some error, but because of the solar storm, because of the geomagnetic storm, uh, the ionosphere is disturbed. Because of that, we have the variation in the ionospheric delay. So since we are approaching toward the solar cycle, so we should, if we have the idea about this solar storm, the geomagnetic storm, when it hits the Indian landmass, on what is the timing, in all this information will help us to improve our model, Gagan model, the ionospheric model. So as we can see in the slide, it is ionosphere affected by. I will not go through all the points. Already it has been enough has been talked about this ionospheric Indian ionosphere. It is affected by solar cycle, seasonal changes, day-to-day changes. So a lot of unpredictability is there in the ionosphere. So currently we are running in the solar cycle 25, and it is expected to reach the peak around July 2025. So during that time we have to take care. We should know in advance whether this how much the solar storm is going to affect the Indian area. So that information is very crucial to us. So again, I will not go to all the details. Like I discussed, the Indian ionosphere is affected by the bubbles, ionospheric depletion bubble, which cause the integrity issue for the user, because these are the local disturbances. But equatorial ionosphere, that is, we have larger scale disturbances and are the local disturbances. So scintillation and depletion, these are the local disturbances which affect the satellite SWAS user, which use the GNSS signal. So those signals are affected by scintillation and the depletion. So, what is the impact of the scintillation? So because of that scintillation, receiver can lose the log, and so position accuracy will reduce. So we will have less number of satellites to track, and similarly, if Gagan Geo, which is providing the correction to the user, if that signal is lost, then user will not have the correction for the GPS. So because of that also accuracy will reduce. So it indirectly the availability of the Gagan service may be affected due to the scintillation. Depletion mainly affect the iono delay, which is the major error in this one. Scintillation is affect the availability of the signal. So both these phenomena, which are difficult to because these are the local phenomena, difficult to model and difficult to predict. So these are the currently major challenges we are facing in the Gagan system. Next part of the system which is affected by in airports at India is HF communication. As we discussed, mostly the space weather will affect the HF frequency. So these are mainly affected by solar flare, which are radio blackouts. Suddenly the HF frequency will be cut off. HF communication will be cut off, and it is also affected by solar radiation storm and the geomagnetism up to some extent. And we have, as I discussed, because of scintillation, even the satellite communication may be affected. So scintillation will affect the availability of the signal. So it may be the satellite GPS signal which is used for navigation, or geo satellite again for navigation, or the communication satellite which is used by the aircraft. Similarly, the other area which we are affected, civil aviation communities affected, is because of the solar radiation storm. So where aircraft flying at the higher latitude, like polar region and all, they may be exposed to the radiation risk due to the solar radiation. So we need to alert the user in advance about the threat caused by the space weather. So requirement from our civilization point of view is the intimation of geomagnetic storm, solar radiation storm, and solar flare events in advance, which are likely to affect civilization users, like Airports Authority of India, airlines, or airport operator, so that we can take preventive measure if possible and for situational awareness. So that if there is an outage in the system, we can correlate this outage to the other phenomena, the space weather phenomena, if it is due to the space weather phenomena. So accordingly, we can take the preventive measure also. And our next requirement is, if we know the lat long, as envisaged by this DISA project, that latitude and longitudinal profile of the electron density. So which will be very much useful to locate the impact of the space weather effect. So where it is going to have impact. So we need to know the area where it's going to affect and the timing of the such event. And we need to know the parameter. We need to develop some new parameter which directly affect the user and which defines the effect, not the cause of space weather event. So we know the cause, what caused the space weather event. But we want to know the effect, how it is going to affect end user. So we need the parameter which is coupled with the end effect. So which are directly impacting the end user. And these parameters should define the event qualitatively and quantitatively. And the next requirement is we should have continuous monitoring of the space weather event as well as the forecast of the event. So we should, even after event has happened, we should be able to recognize, okay, this event has happened, and at this point, at this time, and this point, and this location on the Indian region. So all this information will prepare us better to take care of the unforeseen the solar space weather to tackle in more effective way, and take the preventive measure if at all possible. So that's all from me. Now.
Thank you very much.
Yeah.
Thank you very much, Sri Anurag Gupta sir, for telling in so much details, and we have understood. Basically, one very important point which you have touched upon is the next level of Gagan. Okay, so when we have to take Gagan forward, these kind of observations which we are envisaging to do from an altitude of say 400 kilometers, along with the observations which we are already having from ground, and with the Aditya L1 observations, which will give us a holistic picture to tell what actually happens when this sun starts disturbing the thermosphere system too much, and how much does it percolate the aviation altitudes, civil aviation altitudes. So that is one very important area which Disha is one of the prime steps, I should say, towards that direction. And also you have also brought in the importance to envisage an index which may represent severity of a space weather event with respect to the civil aviation perspective, which may be a combination of all the parameters which we are measuring. And also, you have also made an indication about whenever you were speaking about the models, the effects of the solar cycle, as one solar cycle is 11 long years, and if we have to see multiple solar cycles, it will take 22, 33, 44, this kind of years, several decades. Also indicates that this kind of in situ observations from higher altitudes should be a programmatic activity, and it should not end in one set of satellite missions. It should continue with some overlap, which will not only insights in terms of physics, but also open up the opportunity for big data analytics. Thank you very much, sir, for joining us and sharing your perspective.
Thank you, Gurmeet.
Thank you, sir. So we go to our next ministry, Ministry of Science and Technology, which is represented by Dr. Akhilesh Gupta, Senior Advisor, Head Policy Coordination and Program Management Division, and Dr. Gaurav Agarwal. Over to you, sirs. Ministry of Science and Technology, anybody? Dr. Akhilesh Gupta and Dr. Gaurav?
Sir, my name is Gaurav Agarwal. I think Dr. Akhilesh Gupta is not here.
Okay, sir. Over to you, sir.
First of all, I would like to thank you. It's a very enriching experience to learn many new things today. Since I didn't come from this field, so far as DST is concerned, DST is an external funding body. Main object of DST is to provide funding to R&D in the country. So we have a project called the National Large Solar Telescope, which is an upcoming mega science project, which is presently under consideration with us. So it has some objectives which are overlapping with the science which we are doing now. So I will just read out one thing, that NLST will address a multitude of crucial, well-posed scientific problems in astrophysics and critical issues in the sun's influences on the Earth, space weather, and understanding the release of sun's energy into the solar system on a gigantic scale. This is one part, and the scientific objectives also include understanding the origin and evolution of magnetic field and its connections to the solar cycle. So what I understand is that this upcoming solar telescope will also be able to look at some of the scientific issues which may be of concern of our interest. So this is one thing I would like to make, and definitely ISRO, we would like to have collaboration of ISRO in not only in the scientific and the technological aspect of the project, but also in the financial aspect of the project. The project cost of NLST is around 563 crores, and it is we are taking it forward. So we hope that we will collaborate in a more cohesive way on all the fronts of scientific, technical, and also financial. And secondly, the IIG Mumbai, Dr. Guru Baran is here, so he is already taking parties, and we would also like to have more and more collaboration on the scientific and technical aspect. This is the only thing I would like to make here, sir. Thank you very much, sir.
Thank you very much, sir. And this precisely tells us our own objective, what we are planning to do. Same thing has come from you. So scientific objective wise, they're very much overlap. And also you have made a very important mention of making this activity pan-India. Okay, and the efforts which DST are going to put is really in line with whatever we see in future. The way the previous presenters also have mentioned, ministries also have mentioned, to take it forward. DST will definitely have a very significant role to play, sir. So I request you, sir, you be with us, not only in this meeting, but also throughout our endeavor and in the programmatic process. Thank you very much for having joined us, sir.
Yes, thank you so much.
We go to our next presentation or next views from the Ministry of Electronics and Information Technology. We have here representing the ministry Dr. Manoj Kumar Khare, Senior Director HOD Emerging Solutions, as well as Ms. Akshara, and who is the Senior Director of HOD SPCC Group, CDAC Pune. Over to you, sir and ma'am.
Yeah. Good afternoon. This is Akshara. I'm representing Center for Development of Advanced Computing, that is CDAC, from the Pune. That's our headquarters. And I'm working in a group called HPC Scientific and Engineering Applications, which includes weather, environment, air quality, and CFD applications. And with me, we have Dr. Manoj Khare, who is mainly heading the group on the geospatial applications. So before I give our points, we are very thankful for the opportunity to participate in this important program. And we are listening since morning, and we are getting Disha on the Disha, and we are very happy that this is a multi-sectorial as well as multi-ministry program, and we look forward to participating in this. We are little odd one out because we are not the domain people in this, but we find an opportunity after listening to insightful talks since morning that there are three major ways we can contribute. We look at it as a more of a community development in terms of research, then the development activities as well as the service activities. And we are looking at it as a when it comes to research, there are opportunities where we can contribute it into the computational modeling frameworks, because this will require very complex modeling. And for that, large resources, computational resources, tools, and models will be required, and we can contribute to that. The next important thing, as we've seen since morning, large data will be generated, and this is not only the satellite data, but also the impact data. So what we would like to propose in this case is we can have not only the modeling data in terms of forecasting, but also the impact-based decision system. The decision support system, right from converting the scientific data, technical data into the products which are useful for different sectors. We just now we listened to the aviation needs, also energy needs, and health impacts. So we can have a comprehensive cyber infrastructure where cross-sector community stakeholders can contribute. And very important in this thing is we can have a big data analytics where interoperability of this data as well as the products in terms of a easy and understandable communication depending on the sector who would like to use this data. And third important thing is there will be multiple modeling efforts. So what we foresee over here is the standardization of data operating procedures as well as the modeling procedures, and definitely our ministry and we can contribute to that. And also we have been working on few of the weather models, and on the computational aspects we can contribute in terms of optimization and developing of the tools. And I request Dr. Manoj can elaborate on that.
So basically, as Akshay Madam has says, we are working in the HPC and a lot of data is going to come here and a lot of modeling is required. So we can also work together like HPC with computational modeling to basically to study the impact of weather, space weather in various areas like communication network and other impacted areas, which our previous speaker has said. So in that way, we can definitely contribute. So, as Madam already has said, this big data is also one of the important areas because a lot of data is going to come. Data observation data also you are going to collect. So this will also need for big data framework for this kind of data analysis, for space data analysis.
One important thing is we have a national supercomputing mission where there are around 70 plus installations all over India where petaflop to exaflop systems are getting installed, and already 10 plus such systems are already there. So we look forward to we can define this as a common project or a program where the modeling efforts where you would like to have multiple different types of models to be developed as well as compared and analyzed and taken a decision to convert them into a decision support system. So we can also make use of this national supercomputing mission, and we can have a strategic partnership on that.
And and like we are also working for this disaster management. So we have to just link how whether it is also impacting disaster management in the current disaster management activities like flood forecasting, other thing also flood and other disaster. So we can also have to link somewhere. So that I don't know, means just we have to study, and maybe some link up can be that whatever data is coming from the space weather, so that we can link up this, especially for landslide predictions and flood predictions and things.
Thank you very much, sir and madam. You have brought out a very important aspect that we have to do modeling, and for modeling we have to have a lot of computational resources, especially if we have to be broad in coverage and accurate, high resolution in accuracy, both spatially and temporally. So I envisage Aditya is there looking at sun to see the cause. Disha system is there to see the effect on the upper atmosphere, and you have the ground-based system, which are observing from bottom to the top. And with this, you are generating a lot of data, and basically you are covering near sun to ground. And this really requires enormous amount of computational resource. And one very important point which you have mentioned during your deliberation is not only the forecast aspect of it, also the decision support system is very important, and which will make our country strong with respect to this heliophysical event, which is no longer an astronomical event, no longer merely an astronomical event, but also are going to touch human lives on ground. And thank you very much, and we take this forward. And here at this juncture, I would like to mention these data are also going to be made available with some data within the ambit of the data policy of ISRO. And this will be made available, and on the space data, ground data, and Disha being one of the very important components, will provide an opportunity to have a better picture in this direction, and CDAC will definitely be a very prospective strategic partner, as you have rightly mentioned. Thank you very much for joining us today in this discussion.
Thank you, sir. Thank you, sir.
So we move forward to the next ministry, Ministry of Information and Broadcasting. And we have today with us Ms. Anuradha Agarwal, ma'am, who is Additional Director General Technology from Prasar Bharati. Over to you, ma'am. Thank you very much for joining. Madam, you're muted.
Am I audible?
Yes, madam, you are audible. Only the echo was coming. You are audible. Can you try once again?
Okay. Am I audible? Is it okay now? Okay.
Yes, madam.
Thank you so much for the opportunity to listen to so much of technical information that is, being taking rounds, and so much of research that is going on in the field of space weather. And I would like to present how the Ministry of Information and Broadcasting is dependent on the satellite communication system, and how we are going to be effective. Like, it's really, listening to all these things, we are spectacle of how our systems, our services are probably going to be affected. So can I share my screen for a short presentation?
Sure, ma'am.
So some of our views, I'll first try to define how the network is, and then so Ministry of Information and Broadcasting is one of the vital ministries that represents the face of the government in reaching out to the masses. And the mandate is to disseminate the information about the government policies and schemes. And it also takes care of the policy matters related to print media, print electronic media, and as well as majorly the broadcasting sector. So the main functions are divided into three. I won't go into details. The broadcasting wing is mostly important. It not only takes care of the Prasar Bharati, and that is radio and Doordarshan, and it also regulates the private satellite channels, the network of MSOs, the local cable operators, and the private DTH platforms.
Madam, your slides are not moving. We are seeing the title slide.
Why?
Yeah.
Has it moved now?
No, ma'am. What you may do is you may unshare, and while you share once again, you may go to the full screen mode of sharing.
Just a minute. Stop sharing.
Full screen. Complete screen.
Entire screen. Okay. Not taking the entire screen.
Ma'am, we have the presentation here. Shall we present it from?
Yeah, you
from
can
our
present
end?
it. Okay.
Yeah.
You can do it.
Okay. Yeah. So is it visible, ma'am, at your end?
No, it's not. Yeah, it's visible to me.
Okay. Yeah, ma'am, please go ahead.
You can go ahead with the next slides. Yeah, we can go to the next slide. Next slide. So basically, All India Radio and Doordarshan, we are using a lot of satellites, GSAT 10, GSAT 16, GSAT 17, GSAT 18. Although all these are geostationary satellites, and these are being used for both distribution and contribution of AIR and Doordarshan channels. So a large capacity is being used on the satellite. So our dependence, I would like to emphasize that our dependence on the satellite communication is great. Most of our services are dependent on that. Next slide, please. Can we next move to the slide? So we have in all 7 national services, then we have a lot of regional services, and we are also using it for our All India Radio uplinking, connecting our radio channels. Although we have a lot of network on the ground, a lot of transmitters on the ground as far as AIR is concerned, but still for connecting those stations to the mother stations, we are dependent on the Earth satellite services. Next, please. Can we switch the slide? Yeah. Besides that, DD Free Dish, the DTH service that Doordarshan uplinks provides, is also on GSAT 15 satellite. And presently, we have a large bouquet of 167 TV and 48 radio channels. This is a unique platform that everybody already knows, and this is totally dependent on the satellite communication. Next, please. So all in all, as you see that most of the broadcasting network is linked with the geostationary satellites, and these satellites are parked at various locations, and all the contribution and distribution which is done through the terrestrial network also, and the DTH platform, the cable networks, it's all based on these satellite communication. So any possible disturbance by the space weather or a space storm, it needs to be assessed in advance. And this research that is going on would be a great step towards that, because if in case such an event happens, which is a rare possibility, but if it happens, it's going to disrupt totally the communication, the broadcasting sector altogether. So the impact on the broadcasting of TV and radio services, it may lead to the damage of the entire transmission infrastructure, and this needs to be addressed. That is what I mean to say is that any setup which is dependent on the geostationary satellite, in case of any storm that is affecting a particular area of the space which has the satellite, maybe if it is located regionally, we should have options of moving to another satellite, all the services to the other satellite, or some other method to mitigate and overcome the problem that is going to happen in case of any storm which would affect these geostationary satellite communication. Next slide, please. Next slide, please. So I would suggest that guidelines. The previous slide. The previous slide, please. So the guidelines need to be prepared by the departments, especially for the especially space department, for the safety and survival of the broadcast network in case of emergency which occurs due to space weather storm. Also, advanced preparation by all stakeholders needs to be carried out by making alternate arrangements of the ground segment to overcome the blackout of the transmission. One of the ways could be the fiber cable networks, but that also, if in case if it gets affected by the geoelectromagnetic, I think I was hearing about it. If that is also affected, then we need to think of some alternatives, how to handle this situation. Next, please. It's a little difficult, to mitigate once somebody else is doing the presentation. So the delivery mechanism to the end consumer, one is the distribution of the signal, and then the end receiver, the consumer has to be able to receive the signal. Especially this is important when any such disaster is happening. The normal information is okay, but when in case of a disaster, All India Radio and Doordarshan have been major communication services which have been able to communicate with the public to handle and mitigate the disaster. So it's very important to keep these services alive even in case of a space weather storm. So as and when required, advanced publicity needs to be made to educate the broadcasters of the distribution and contribution platforms as well as the public. And obviously there can be one way of mitigating is to have local generation of content and local transmissions to reduce the impact, but that would be to some extent only. But majorly we are dependent on the nationwide coverage and nationwide reach out of the messages and the information. So a lot of advanced research needs to be carried out, and that is very, very important. Like Disha is one step, we need to take it forward and have more research in this area to be able to forecast, because having an infrastructure put in place would need a lot of time and it needs a lot of investment also. So we need to have a lot of research to be conducted in this area, especially to address the issues of the broadcasting sector. Next slide, please. Next slide, please. Also the protection, no, the previous slide, just one last slide. The protection parameters for the equipment in case the storm is not very heavy. Even if it is a lighter storm, which could affect the broadcast equipment. So the protection parameters would be important, that we know the protection parameters that are required, and this needs to be reviewed to minimize the damages and the blackout time of the broadcast services in case such an accident happens or an incident happens. Also, because this is going to be a worldwide situation, it may not be localized and only India may be affected. It could be a worldwide situation. So the OEMs of basically the various manufacturing companies who are developing the equipment, who are the major broadcast equipment manufacturers, they need to be informed of integrating suitable protection features into their equipment so that they are well aware and all that is in place. The protection mechanism is already in place to be able to mitigate the effects of the storm. And feasibility, as I already said, feasibility of migration of satellite services to either some other satellites which may not be affected at that particular moment or that particular event, or to fiber or some other alternative solution has to be worked out, to be found out. And also the end user needs to have the equipment and a power supply set up, which he will be able to receive the information that will be broadcast in the event of such an eventuality or a disaster happening. So these were the concerns from the Ministry of I&B. Thank you so much. I'm sure the research will be looking towards that direction and provide us with solutions that could be taken care of so that the services are not disrupted.
Thank you very much, ma'am, for your views, and you have comprehensively mentioned about how much role satellite technology is playing in making the backbone of our country, which is information and broadcasting. And in this regard, you have mentioned a very important aspect which is required to make our country safe land in terms of immunization against space weather events. One is SOPs. on space weather events for major stakeholders. So in the previous deliberations, we have been hearing about prediction, and also we have also heard about decision support system with lot of computing, and after having that, how to safeguard our assets, okay, space-based assets as well as the ground-based assets in the extreme events. So this will complete the chain of this thing. Apart from the scientific contribution of what is happening between sun and earth connections. So apart from the pure scientific aspect, these are the aspects which will have a long way to go, and Disha is an apt step towards this. And before I come to the end of the session, I would like to check whether from the Defense Space Agency, Air Vice Marshal D.V. Court sir is there with us. Okay, I think he's not there. Okay. So I would like to request Pallamaraju sir from PRL in this panel to share your overall views of this discussion which we have heard.
Okay. Thank you, Dr. Das, and and thanks to all the ministry representatives who have made an excellent observation, also provided their views on the importance of this space weather research and how their ministry or their work will be benefited by the Disha mission, and what are their concerns which need to be or should be addressed in this by this mission. And it's really and it's very heartening that several ministries are speaking the same language as we are. So I'm very happy to see especially Minister of Civil Aviation and Madam here in terms of information broadcasting, in terms of the various CU band, Ka band, and Q band, that production, the bandwidth that they are using for AIR and Doordarshan, and the importance of understanding this and providing the kind of I should say the nowcasting or the forecast that is being envisaged. So I should say that this is a very interdisciplinary field, and it's a very challenging field also. And we have some of these points were considered in coming up with basic parameters that need to be measured to really come to or deliver these products. For this data that comes out of Disha will help in generating parameterized and also assimilative based types of models, wherein we can assess the effects and which sectors, sometimes depending on the storm occurrences, there are some sectors, midnight sectors, get affected more than the midday sectors. But if it is a solar flare event and CME is coming, that may come in the daytime also. So in that sense, knowing from the space weather science point of view, we'll be making progress, and definitely while we are doing so, we'll address the concerns of the users, end users also, which there are many, and I'm very happy to see their participation, and I'm sure that we'll continue to engage with these various stakeholders in building up further and better systems. Thank you.
Thank you very much, sir. We would like to listen from Dr. Divyendu Chakravarti, PRL, his views.
Okay. Am I audible to you?
Yes, you are clear.
Okay. Okay. First of all, it's a
wonderfully educative experience to hear from not only from the scientists from all academia, universities and IITs, in addition to ISRO and DOS organizations, but also to hear from the ministry representatives. Generally, we don't interact so closely on most of the occasions, although we are probably most of the time telling the same things but using different languages. And to start with, I'll say a few points. But the first point is, I remember there was an. I'll start with an analogy. There was an artwork by Dutch artist N.C. Escher, and you might have seen that one hand is drawing another hand. I mean, they are sort of creating each other. And why I'm saying this? Because Disha is a low Earth orbiting satellite, and for a low Earth orbiting satellite, for a LEO satellite, Disha measurements, although it's primarily a science mission, it will help to sort of fine tune the operations of other LEO satellites. And so, in that sense, they are complementary to each other. And we know that for various applications, there are LEO satellites that we need from that particular kind of orbit. The second point is that if we don't know the road, how do we navigate? In that medium, LEO medium, because we require that orbit for various kinds of applications, whether it is Ministry of Electronics or Ministry of Information and Broadcasting, we need to understand the LEO medium very well. Not only the LEO medium, but we also require the GEO medium very well. And we need to understand the variabilities during quiet times as well as in the distance. So not only so when we say that, if we want to fine tune and focus our applications or improve our applications, then we need to understand the properties of the system very well. And we need to start now because hallmark of that brings me to the third point, that hallmark of any developed nation is generally characterized by how much space assets they have. And we would like to consider India as going towards being a developed nation. So it is not surprising that we will have more space assets in future. And when you are investing that much in our space assets, we need to know this medium very, very well. And that being said, we didn't understand this medium that well so far, although the operational part of it, we have done it quite a number of times in bits and pieces, but there is no integrated approach as such to understand the variabilities of that medium under different conditions in the sun or different conditions in the climate. So the very fact that we are bringing in private industry in the space sector, that itself needs to that tells us that eventually we'll come to a stage where this medium needs to be understood in a much more detail than what we understand now, and for that we need to start now. So that highlights the importance of Disha at the present state. So this is the time. And as Dr. Tirtha pointed out at some point, that it's a continuous process, and we may require a few decades to reach there. But if we don't start it now, we may miss the bus, because we'll be increasing more of our applications from those spaces, but we don't know the medium that well, and so we'll be facing problems eventually. So we need to start it now. And from the first mission, suppose this mission, if we make it operational, from the first mission, we'll be measuring something like plasma structure, plasma turbulence, neutral drag, radiation dose, and GIC, the ground-induced current, the effects on the power lines, astronaut safety. All these things will be a fallout of the measured parameters indirectly and sometimes directly. One direct application I can, in this context, can share with you is that when we measure the plasma irregularities, as our Ministry of Airport Authority of India highlighted, that when we measure through radar or through GPS, we are locking ourselves to a particular frequency that actually fixes the kind of scale sizes of the turbulence that we are trying to measure. And that's an incomplete picture, because those structures, plasma structure, which affects the communication or satellite communication or navigation or all kind of application, it's only one figment of the whole story. Because those structures, they have a whole spectrum of scale sizes, starting from centimeter to the hundreds of kilometer sizes. And we are only sampling one particular figment of it. And so that cannot give us the full picture. And so therefore, unless we understand, so when you fly an LP, it's just an example. And when you fly an LP, this is the only instrument which can give you in situ all scale sizes, right from the smaller scale sizes to the larger scale sizes. And remember, although our country is localized, but our satellites are global, because you can't put a satellite over a country unless it is a geosatellite. In that case, also you need to know the geo orbit. But a LEO satellite will eventually have to go through all regions of the Earth, including the polar region. And so we need to know the global conditions very, very well and how these parameters are built. Having said that, that brings us to the last 2 points, that when we generate, if Disha goes and in coordination with Aditya Ewan, it will generate big data and it will facilitate big data analytics and eventually to the forecasting. That is where we actually plan to reach. This will happen gradually once we have measurements and we feed it or we understand the medium slowly, and then it will get into those operational model, and in our country we will have models which will be used by all ministries. And unless we start it now, those objectives will not be fulfilled. And remember, we are not going to be less. We're not going to have less space assets from now on. We will have more space assets from now on. And the last point is the electronics damage and the mitigation strategies. The moment you are putting more space assets, there are spacecraft charging, there will be other effects that will come, the single point failure and all other issues will come into picture. And we need to understand those effects very well from the LEO and the GEO orbits. And so one can understand, and I think it's a really eye opener for all of us today, having heard each other from close quarters, that we need to work together and both the science and technology. Science will pave the way for technology as one hand draws the other, and the technology will pave the way for science. And thank you very much for giving me an opportunity to share. Thank you.
Thank you very much, Dr. Devendra Chakravarti, for your views. I now request quick views from Professor Devendra Nandi from ISL Kolkata.
Tirtho, am I audible?
Yes, you are clear.
Okay, so first of all, I really appreciate the effort that the Science Program Office and ISRO has put together to get not just the scientific community together to speak about space weather, but also different government agencies. To my knowledge, this has happened for the first time. And I think although it's been in our understanding that various agencies like telecommunications, the aviation sector, the power sector are susceptible to space weather, there has not been an avenue for us to talk to each other. And I really appreciate the comments and the awareness that was in demonstration today from these agencies regarding the hazards that space weather poses. Now, having said that, I would also like to make some few comments. So space weather is really a system-wide thing. It's not just something that's happening in the ionosphere. It begins in the sun, it ends in the ionosphere and has Earth impact. So only one satellite is not going to give you a system-wide understanding of space weather. So I think it is up to ISRO as well as other agencies to come together and appreciate the importance of having system-wide, domain-wide understanding of space weather, starting from the sun all the way down to the Earth's ionosphere. So there, Aditya L1 and Disha together will play a strong role. Now, many people actually talked about forecasting and having an advanced warning system. I want all of you to realize that when you are looking at advanced warning systems, you need to have a headway of something like a day, at least a few hours. Aditya L1 is going to be sitting at Lagrange point L1. From there, the solar wind disturbances reach Earth within 45 minutes. When there's a strong storm, within 30 minutes. Disha is sitting at 400 kilometers altitude, where you do not have any early warning. It's just an assessment. Herein comes the role of models. Models that utilize solar activity and in advance drive dynamical equations forward in time and predict what the atmosphere might feel in a few days from space weather. And this is the kind of modeling that requires large volume data analysis, integrating different partial differential equations, requires huge amount of computing power. And this is where TDAC and other agencies also come in. So one needs to really have a holistic approach, a holistic view to space weather, starting from space missions, observatories, big data analytics, machine learning, and dynamical model-based forecasts for space weather. I would also like to urge the Department of Science and Technology, in consultation with other agencies, come together and fund development in space weather research at a fundamental level in this country, like it does other campaigns, for example, nanosciences, quantum technologies, etc., etc. Space weather is something that every agency that is dependent on satellite system is dependent on. It is unfortunate that we haven't had a very big, large, overarching funding mechanism for developing space weather sciences research from the basic to the transformative applied domain in this country. And I hope that all the government agencies will take this recommendation seriously and work together with ISRO in achieving this. Thank you very much for your participation, and I really enjoyed interacting with all of you.
Thank you very much, Professor Devendra Nandi. And we would like to listen from Dr. Smita from SPL. Dr. Smita, are you there? Yeah, she is there. Only thing yeah.
Hello.
Yes, Smita, you are audible.
Thank you for this opportunity to talk here. And also it was very nice to hear from all of us, many of the academics and from the mission and also from many ministries, and understand that space weather has become a common concern for all of us and of interest also for all of us. And also the missions Disha L and H will definitely help to understand space weather as impact of forcing from sun to the ionosphere, and also the ionospheric weather as impact of or forcing from below, that is the lower atmospheric forcing, which is very importantly equal to understand the variabilities of ionosphere, as well as the day-to-day variability of plasma irregularities, which is of another major concern to us. And along with Aditya L1, this will generate a very comprehensive data set, which is of ionospheric plasma parameters and also the thermospheric neutral parameters, and also the solar parameters from Aditya L1. So this will be a very unique and very useful data set. And when I just wanted to talk about the thermospheric neutral, importance of thermospheric neutral parameters, as because the determination and prediction of neutral density is one of the major components which is important for precise orbit determination, as in the case of low Earth orbiting satellites, also in terms of space, the collision avoidance, re-entry prediction as such. And these neutral parameters, which we are uniquely going to measure, are of extreme importance because they are actually affected both by the solar forcing in terms of solar irradiance, as in the case of quiet condition, as well as the Joule heating and particle precipitation related to the space weather events. So, and when it comes to real space weather events, sometimes this forcing can be as important as the quiet, or in magnitudes are comparable to the even the quiet time variabilities. And we have very abrupt changes in the term due to solar flares and geomagnetic storms. we have diurnal variations, and we have multi-day variabilities due to CIRs, that is co-rotating interaction events, and then which is driven by the changes in the solar forcing due to the solar rotation effects, and the semi-annual and or seasonal variations, and the solar cycle, and even the long-term trends in neutral densities which are caused by the changes in the CO2, etc. Also, we have the spatial changes like latitudinal variation, which also is affected by the ionosphere therein. That is the ion drag, which actually controls the neutral density variation, the latitudinal variation of neutral density in the spatial terms. So that's a very exciting or important example of how ionosphere controls the structure of neutrals therein. And also we have the longitudinal variation brought about by the lower atmospheric forcing, etc. So to understand this is very important, and model this is very important in terms of the drag estimations, as right now we are dependent on models like MSIS, which can predict the seasonal or solar cycle variations to some extent, most of the extent, but they fail when it comes to the abrupt events like geomagnetic storms or forcings from below are very poorly represented in such models. So generating a data set which is important for space weather in characterization of space weather is very, very important in terms of understanding the neutral atmosphere, neutral thermosphere, and the drag therein. So also, as it was mentioned just now, the effects of energetic particles or solar events when it comes in terms of spacecraft charging and energetic particles becomes very, very important, as we can see in the during the 2003 Halloween storms. We have many satellites were malfunctioning, or some of these satellites I can see in the chat box about that discussion. EDUS 2 was completely lost due to the spacecraft charging issue. So this actually brings or reiterates the importance of understanding the variabilities of space weather, and Disha will be a very suitable step for developing such an understanding. Thank you.
Thank you very much, Dr. Smita. And we have come to the end of this session, this panel discussion. And thank you once again, respected madams and sirs from ministries, for having joined us today and having shared your valuable views. I summarized this discussion by stating that Disha is just a beginning towards building of the space infrastructure towards achieving self-reliance of our nation against the space weather events. Now, fulfilling this ambition necessitates drawing a long-term plan, which in turn requires a programmatic approach with the confluence of the wisdom of all the ministries, which we have witnessed today. And Disha H and L will surely add to the space and ground-based infrastructure for achieving better understanding of the space weather effects, which will eventually lead to a better planning for the protection of the space and ground-based assets. Thank you very much once again to have synergized your thoughts. I hereby conclude the session 4, and this is the beginning of the session 5. Session 5 is dedicated to the discussions on dynamics, composition, and structure of the quiet time ionosphere-thermosphere system. And this session will be chaired by Dr. K. Rajiv, Director of the Space Physics Laboratory, Vikram Sarabhai Space Center, ISRO Trivandrum. Over to you, sir.
Yeah. Good evening to all, and thank you, Dr. Das. We are going to the session 5, Dynamics, Composition, and Structure of the Quiet Time Ionosphere-Thermosphere System. We have 3 speakers. All of them have joined. Without losing much time, let us straight away go to the session. And I request to the speakers to restrict to the allotted time, as there's a request from ISRO headquarters. Dr. TP was telling about the criticality of the time, time that it has to end. First is by Professor Kalyan Bhuyan on low latitude low and equatorial latitude ionosphere thermosphere processes. Professor Kalyan is an ionospheric scientist and a professor of physics at Dabrigat University. Over to you, Professor Kalyan.
Yeah, thank you, sir. Am I audible?
Yes, you are clear.
Yeah, you're
Yeah,
audible.
and
You're audible. Your
yeah,
video is coming up. Yeah.
okay. Thank
You
you,
can
sir.
go to presentation mode. That would be better. Yeah, please go ahead. You're not audible, Professor Kalyan. Hello.
Yeah, you're not audible.
Your video is coming, but it is not changing. The audio is not audible, and your slides are not changing. I think he's not able to hear, or maybe is it muted by any chance? Hello.
Professor Bia, you may unmute yourself from your end.
He is not muted. He is not muted, and he is in presentation mode. But somehow we are not able to hear him. Microphone is on. Yeah, he has left. He will be joining now. It takes time. TP, should we go to Fazlul Laskar and come back?
Yes, sir. If they're available, we can go to the next presenter.
Yeah, both are available. Probably because it is taking more than, I think, 1 or 2 minutes. Maybe he's having some connection problem.
Sure. Yeah.
Dr. Fazlul, you are available, no?
Yes.
Hello.
Hello.
Yeah, you're audible. I think we will go to the next talk and then come back to Professor Bowen's talk. Okay, we'll go to Dr. Fazlul Laskar. He's from the Laboratory for Atmospheric and Space Physics, LASP, in University of Colorado. He's an expert in the ionosphere thermosphere system, vertical coupling of the atmosphere and ionosphere. Over to you, Fazlul.
Good evening. Thank you very much for providing this opportunity. Can you hear me well?
Yeah. You're audible. Your video, your slides are okay, but you can go to presentation mode.
Is it okay now?
Yeah, it's fine. Go ahead.
Yeah.
Okay, so I thank the organizers for providing me this opportunity to talk on particle coupling of atmospheres, and it is indeed a great pleasure to present some of my works with the great scientists from India. So today's talk is on particle coupling of atmospheres, and so these slides have already been presented many times. And so what I want to say is that there is a region in the atmosphere which is called thermosphere, which is above 90-kilometer altitude. And this part of the atmosphere is highly vulnerable to solar and geomagnetic forcing. So there's the solar forcing gives us the background variations, but the geomagnetic variations, they comes in the form of particle precipitations. They give rise to the highly variable atmosphere or thermosphere. And because of the ionization from the sun, we have ionosphere that exists. And these both ionosphere and thermosphere are impacted by the waves from the lower atmosphere. And so these waves and the geomagnetic forcing, they distort both thermosphere and ionosphere, and they give rise to various perturbations in that thermosphere ionosphere system. So in this particular presentation, I will be talking about some of these perturbations that we see in the thermosphere ionosphere system, and particularly using some of the data like DayGlow, equatorial electrojet, and TEC. And then I will present some of my works related with the data assimilation using some of the well-known data assimilation system like NCEP reanalysis, NAPGEM, and right now the work I'm doing on thermospheric data assimilation. So for the studies of the particle coupling, we have used great data sets. For example, starting from 30 kilometer to thermospheric altitude like 100, 130, 230, and up to ionosphere, thermosphere altitudes. And so what I'm showing here is some of the variations that we have observed. So the variations in the form of days on the x-axis and y are the amplitudes of various perturbations that we have seen. And these are two different years of data that I obtained during my PhD period. So they are from different altitudes as listed here. And so particular interesting thing that we can see on the left panel is that many of the variations that we observe in the lower altitudes are also seen in the thermospheric parameters. But the solar ones, like that in sunspot number, is only present in TEC. And if we go to another year, the 2012, it was like mixed kind of variations. We see that the thermosphere has both lower atmospheric perturbations and the solar perturbations. And there was a different year. We have like 2001. There was like a high solar activity period. There we see that sunspot controls most of the DayGlow variations. And from this slide, these 3 years of data, where for 2011 sunspot was like 35, 12 it was around 52, and this particular year it was like 120. So we see that as the solar activity progresses, we see that control of the thermosphere governs by transition by, initially it is like for lower activity, it is mostly lower atmospheric forcing, but in between between 35 and 52, there happens a transition from lower to mixed, and 52 to 123, there happens another transition, like mixed to solar only forcing. And so how this solar activity does these changes? So solar activity changes the neutral density of the atmosphere, and neutral density change leads to the molecular viscosity and thermal diffusion changes. And these parameters decide which waves are getting dissipated. So that's how this relation between wave propagation and solar activity changes. So there was another work that we have used like lower atmosphere data and electrojet and total electron content for about 10 years of data, and we have seen that like so in the previous one we have seen that during high solar activity thermosphere is controlled mainly by the solar activity, but in this particular one we have seen that in addition to solar activity there is another case that is important, which is called sudden stratospheric warming. And this sudden stratospheric warming, what we did is we analyzed about 8 events here, and we have seen that whenever there is a strong perturbation in delta T, which is an indication of strength of the sudden warming, so we see that the amplitudes of the quasi 16-day waves in the atmosphere or in the ionospheric parameters is proportional to the strength of the SSW. But in addition to that, we have seen that when, like for the year 2013, the sunspot was higher. And even though in the higher activity, we have seen there is a strong coupling with respect with lower atmosphere. And that's because this in 2013, we had a major stratospheric warming. So like in the major warming cases, the atmosphere is highly coupled even during the high solar activity. And so another very interesting thing we have observed is that during SSW, what happens is like these are some of the day glow observations that we obtained from Hyderabad in India. And we see that during SSW, like SSW happened around this time, and these are the post-SSW days, like January 19, 20, 22. And during those days, we see increased air glow emission or day glow emissions. And so this has been observed for multi-wavelength day glow observations. And how this kind of enhancement could occur, there are possible causes are like solar UV changes or low atmospheric waves or changes in composition. And changes in composition can be driven by low atmospheric waves also. So we did a detailed study using other data sets, and what we found out that during sudden stratospheric warming, what happens like winds becomes meridional wind becomes equatorward, and that transports atomic oxygen from high to low latitude. And once that circulation mixes up with the summer to winter, so this kind of process leads to the enhanced emission at low latitude. So that particular study was done using some local data sets, and then I was interested to see if we can find out similar kind of circulation in the high altitude assimilation system. So for that, I have used the NAVGEM, NAVI Global like high altitude assimilation system. And what I found out is that, so what I'm showing here is on the left is like pre-SSW time, and on the right is SSW time. And during pre-SSW, you have like the lower plots are like removing all the tides and the planetary waves, and then you plot the zonal mean wind. So in these plots, you can see clearly that on the right side that during SSW, the filtered wind or filter meridional wind is completely negative. That means they are going towards towards the equator or to the south. So this study again confirms that what we proposed earlier, that there is a circulation that goes from high to low latitude, and that circulation gives rise to the increased atomic oxygen there, or the emission intensities at low latitudes. But the thermospheric part of this circulation, like this one, has not yet been verified or demonstrated using a very rich local time global data. So for that, what we need is we need again a thermospheric data assimilation system. And as many of us know, that thermospheric data assimilation needs a lot of thermospheric and ionospheric data sets. So having a satellites like DISHA with a lot of ionospheric and thermospheric observations will be really useful for this kind of investigations. And so in terms of current perspective, we know that space weather is very vulnerable to the geomagnetic activity. And as an example, you might have heard that during February 2022, SpaceX has lost about 38 of the 49 satellites they launched. And so as the society is going towards a lot of space-based communication, so we need to have a very good forecasting system for the thermosphere and ionosphere. And so I am currently working on one of these forecasting and assimilative system. And here is an example that I just want to draw your attention is, so what I did here is I assimilated NASA gold mission temperatures in one of the whole atmosphere data assimilation system. And what I found out is that the changes with respect to true state. So like we have a temperature from the known state, and we have a temperature from after assimilating gold data. And if we do see the difference between these two different runs, we can find out that the differences are lower within the field of view of the gold, like in between these two lines. But beyond these two lines, we have the differences are higher. So this again shows that we need more data sets or more global data sets. And again, the data from the DISHA will be helpful in this regard. So, and there is another, one of my recent work that I just wanted to highlight here is that we are working with the NOAA to find out a configuration or satellite configuration that best suits for thermospheric forecast study. And as part of this investigation, so I have used about 40 satellite configurations. So they're like different altitudes, different local times, different inclinations, and different number of satellites. So there are a lot of information in this plot, but I just wanted to highlight that which particular configuration does best for the thermospheric assimilation and forecasting system. So for that, what we did is we found out the RMS errors between one of the true state and the assimilation state. And what we found out is that, so out of all the cases that I showed in the previous plot, some of the cases like case 5, 7, 11, and 16, that have like about 2 satellites, 1 satellite and 2 satellites, provides the best forecasting or assimilating capability for the thermosphere ionosphere. And so, like as I have seen in the morning sessions, that the DISHA will have 2 satellites, one in high inclination and one in low inclination. So this again says that this is an excellent choice of choosing two satellites, one in the high inclination and one in the low inclination, and both the satellites are mostly identical. So with this, I will summarize my talk. So we have seen that the particle coupling of atmosphere is solar activity dependent, and we see the coupling is very stronger during low solar activity. But even during high solar activity, if there is an SSW, the coupling gets very effective. And there happens a strong interhemispheric meridional circulation during SSW. And so the thermospheric part of that meridional circulation is yet to be demonstrated using a global and rich local time data, which we can get from the data assimilation systems. And so again, emphasizing that having a Disha-like satellite system that has both high inclination and low inclination identical satellites would be very helpful towards the studies of the particle coupling and thermosphere ionosphere forecast studies. With that, I thank you all for your attention, and if you have questions, I'll take them. Thank you.
Thank you, Dr. Fazlul Laskar. It was a very nice talk on the vertical coupling, including the modeling, assimilation, and the satellite observations. Are there any questions? I'm not able to find anything in the chat box. If there are any questions to him. If not, I think we can proceed with the next presentation. Professor Kalyan Bhuyan has joined back. And thank you, Dr. Fazlul, for the nice presentation.
Thank you.
We will move on to Professor Kalyan Bhuyan. He's a professor. He has just had a break in his connection. Now he has joined back. So is it okay, Professor Bhuyan? Shall we go ahead?
Yeah, actually, I'm not sure what happened to the connection. Yeah. So,
Yeah.
can you hear
You're
me
audible.
now?
You can go ahead. Yeah, you're audible.
Okay. So,
Yes, please go ahead. I mean, now you can go to presentation mode. Better. Yeah. You can go ahead now.
yeah. So, keeping in view the broad spectrum of audiences, I have actually organized my presentation to include a review of what has been quite well understood in the ionospheric thermospheric processes and what needs to be better understood. And when you look at the ionospheric fluctuations, you will see there are variations with altitude, latitude, longitude, universal time, season, solar cycle, and magnetic activity. Now, the variation of the ionospheric parameters results not only from the coupling, time delays, and feedback mechanisms that operate in the IT system, but also from the ionosphere's coupling to the other regions of the solar terrestrial system, including the sun, the interplanetary medium, and the magnetosphere, and also the mesosphere. So basically, it constitutes a coupled, complex and dynamical electromagnetic and photochemical system, the energetics, dynamics, and chemistry of which is significantly altered by various external factors, which include particle precipitation, electrical currents from the magnetosphere, incoming solar radiation, etc. Now, when you look at the ionosphere thermosphere system as a whole, you see the F region, E region, and lower thermosphere is basically influenced by auroral precipitation, joule dissipation, solar extreme ultraviolet radiation, then plasmaspheric downflow, starlight and scattered radiation. The D region is basically influenced by meteors, UV radiation, X-rays, very energetic particle precipitation. And also the D region and mesosphere is basically influenced by tides and gravity waves. And the D region and F region, E region, they are interconnected. Now, when you look at the ionosphere thermal system as a whole, you see there are high latitude processes which influences the magnetospheric disturbances, and they influence the electric fields, which basically gives rise to plasma, fountain, and drifts. The electric field also influences the equatorial electrojet current, then in the formation of sporadic E layer, F3 layer, then the winds and waves are actually comes from lower atmospheric forcing, where gravity waves, tidal and planetary waves play a very important role, giving rise to equatorial spread and plasma bubbles. Now, when you look at the ionosphere thermal space system as a whole, the sensitivity of the system to. Sir, am I audible still? Hello.
Yes, sir. You're audible, but your screen, your screen is now not seen. Your screen is seen, but your figures are not there.
Okay.
It is showing sharing your screen.
No?
Yeah, that's fine. Yeah.
Thank you. Okay.
Yeah,
So
go ahead.
when you look at the sensitivity of the ionosphere thermal system to external factors, the sensitivity actually results in large yet often unpredictable changes in many parameters like density, temperature, neutral and ion winds, TC, neutral and ion composition, electric fields, currents, and conductivity, and so on. Now, depending on the different time scales of the external forcing, the ionospheric variability may be having 11-year solar cycle variation, quasi-biennial, seasonal, diurnal, and large day-to-day variabilities, etc. And over and above all these quiet time variations, you have solar storms and substorms, which can lead to abrupt reconfigurations of the magnetospheric field, aligned and horizontal currents, setting a number of electrodynamic processes in motion. Now, if you look at the overall overlapping physical and chemical phenomena which are occurring at various temporal and spatial scales, they are actually very difficult to understand as a whole. So a more detailed understanding and accurate modeling are urgently required in this regard. Now, our understanding about the various ionospheric, thermospheric, and magnetospheric processes has come through satellite missions since the middle 1970s and early 1990s to this date, and also from modeling activities like
Sir, we are not able to hear you.
Your voice is not heard. Hello? Is he audible to others?
It's not audible to headquarters.
Dr. Das?
He's not audible to headquarters.
Not audible to any of us also, I
And
think.
his slides are not moving. Yeah. Slides are not moving.
It's stopped at status of correct.
Yeah. Hello? Hello? Professor Bhuyan? I think he's not audible. His connection has a problem. Just we'll wait for 1 minute. He may be able to connect back.
Can you kindly
join back?
Yeah, sir, can you kindly carry on with the next speaker? I am having a serious network problem here. It is all the time it is causing problem. Sir, can you hear me now?
Yes, you're audible. It is breaking in between, but you're audible. Yeah.
Should I continue or?
Yeah, you please continue. Please continue. You please continue.
Okay, so our understanding has come from models also, like NCR models, TIE GCM, Time GCM, MTI GCM,
Hello.
PTI. We have a. Yeah, sir. Yes.
But your slides are not seen, Buyan. Your slides are not seen.
Now, is it visible now?
Yes, it is visible in headquarters.
Yeah, now it is visible.
Yeah, thank you. So we have a
Visible. Please go ahead.
model developed at Dibrugarh University, about which my colleague Dr. Victor will be speaking. And now people are regularly using whole atmosphere community climate model with thermospheric and ionosphere extension to understand the ionosphere, thermospheric, and magnetosphere coupling. Now, when we scale and realistic is key, when ionospheric distances, gravity was accurately understood. As we all understand that the electric fields, plasma drips, and ionosphere are mostly from the dynamics of E and accretion neutral winds, but this can be actually significantly perturbed by atmosphere during magnetically quiet times, and also by solar wind, magnetosphere dynamo, and ionospheric disturbance dynamo effects during active periods. The accurate specification of the temporal and spatial variability of the ionosphere plasma drifts constitutes the main challenge for improved forecasting of ionospheric weather, which can strongly affect the rapidly increasing number of space-based systems. Now, when you look at the low and equatorial latitude ionospheric thermospheric processes, our understanding has come mainly from measurements of low latitude ionospheric plasma drifts and currents during the last 4 decades using ground-based radar, ionosphere and magnetometers, both in American and Indian sector, and also determination of the basic electric field and plasma drift mechanisms by using theoretical and numerical simulations. So there lies the very importance of theoretical and numerical simulations in understanding the processes. Now, when you look at the climatology of equatorial plasma drift, you see my concentration will be mostly on the pre-vessel enhancement of the electric field, vertical electric field. When you look at the pre-vessel enhancement of the electric field, you see this has important consequences for the equatorial ionization anomaly and also the stability of the nighttime ionosphere. As we understand, there are 3 competing theories of the pre-vessel enhancement of the electric field. Basically, one is called CFM, which is curved electric field response to rapid changes in the vertical electric field associated with nighttime effusion dynamo. There is a called HDM, which involves a divergence of Hall currents in the U region away from the magnetic equator, and third one is moderating effect of the large clouding conductivities in the equatorial E region. And now, Eclis et al. Actually has performed a modeling study to understand which mechanism becomes important under what conditions, and they have found that equatorial clouding conductivity creates an important current path that limits the other 2 mechanisms prior to the equatorial sunset and releases them after the sunset. The CFM mechanism is dominant mechanism when the terminator and the magnetic meridian is aligned in part due to the accelerating effusion zonal wind. And when the solar terminator is not aligned with the magnetic meridian, there is an interaction involving all 3 mechanisms contributing to the magnitude and timing of the pre-vessel enhancement. So, in a recent study by Ghosh et al. And Abadi et al. Done very recently, they have found that both Stewart neutral wind and the EEJ are involved in the pre-vessel enhancement, and hence 2 parameters to influence the PRE magnitude in a balanced manner. And they have also found that latitudinal and longitudinal extension of equatorial plasma bubbles is controlled mainly by the magnitude of PRE and the peak value of H prime F at the initial phase of development of the equatorial plasma bubbles. And now, when you look at the planetary waves affecting the evening F layer and PRE and the ESF, you see their signatures have been identified in the EEJ strengths and mesopause temperatures, EI and ESF layer heights and vertical plasma drifts. So The PF influence can modify the intensity of the PRE and post-sunset F-layer heights and hence play an important role in widely observed day-to-day variability of the ESF or EPBs. Now, there has been observed evidence of PW manifestations in mesospheric wind and PRE with the consequent variations in the ESF intensity and occurrence. Now, the PRE actually influences the sporadic E layer, and they actually both act in an interactive way. So the sporadic E layer formation can be interrupted or detected under development by sufficient intensity, which means that PRE of smaller value than a critical value does not interrupt sporadic E layer development. The rule of evening sporadic E layers is that appears to operate in interactive ways and is the latitude of their occurrence closer to the equator, they are and the interactive rule of sporadic E layers from latitude far away from the deep equator still needs to be evaluated in a better way. This is about the average on zonal depth. This is quite well understood. This seasonal and solar cycle dependence of the average on zonal depth is shown here. Now, when you look at longitudinal variation of equatorial electric fields and plasma depths, you see these are also quite understood. Seasonal variation and longitudinal variation is quite well understood. And this is the diurnal variation of EZ peak density during Mars is insensitive, and this shows that the EZ has been superimposed by the wave number 4 structure. When you look at quiet time short-term electrodynamic variability, the electrodynamic fluctuations from a few minutes to about an hour is basically related to atmospheric gravity waves. When you look at longer period fluctuations, you see there is a effect of complex changes in tidal forcing of global winds and planetary waves and irregular winds in the dynamo region. And there has been evidence of strong quiet time EZ and E region and F region plasma dip perturbations during sudden stratospheric warming events. Here in Dibrugarh, we have been studying sudden stratospheric warming. We are trying to understand the statistics of these events for 4 decades of data. And we have seen that there are large variations, perturbations, ionospheric perturbations due to these events. And these are basically considered to be caused by the disturbed E region dynamo or by altering the vertical propagation of planetary waves. Then we have studied the periodicities recently of FOF2 for 3 stations latitude to the high latitude, and we tried to find out what are the major periodicities available in the FOF2. For that, what we have done, we have looked at the time series of the expansion coefficients in the empirical orthogonal function analysis of ionospheric FOF2 data for 4 decades. Data for spanning 4 solar cycles from 20 to 23. We have done this with an objective that an understanding of these periodicities will help us in a better understanding of the physical mechanisms involved in the coupled ionosphere, magnetosphere, and thermosphere system. So this shows the long spherical periodogram of the short-term periodicities of the ionospheric parameters FOF2, then solar Sputnik for a solar cycle 20. This has been published in ASR in 2019, and the short-term periodicities we have observed is 9 to 14 days, 22 to 30 days, and 64 to 128 days. These are observed in all certain solar parameters and indices together with the FOF2. Then there is the most short-term periodicity, which is shown by the ionospheric parameter is 27 days. There was another most dominant amplitude found in the spectral analysis was 13.5 days periodicity, which is basically due to the occurrence of 2 high-speed streams per solar rotation at 1 astronomical unit. And there are midterm periodicities which are found to be more dominant. The most dominant is 154-day periodicity, and this is actually related to the variation of solar radius. And we have observed annual periodicity of 365 days with a variation between 315 to 380 days, and also about the semi-annual periodicity of about 183 days with a range from 154 to 217 days. These are observed in all the stations for all solar cycles. There is the most dominant long-term periodicity that has been observed is 11 years periodicity, which is of course well known. This period variability has been found in F10.7, R, BZ, rho, P, alpha proton ratio, KP, DST, AP, and all these indices. And one particular periodicity of 121 days has been detected in almost all the expansion coefficients of the 3 ionization and the stations. This periodicity has not been observed in any of the solar parameters or geomagnetity indices. And actually, we could not explain the periodicity of this 121 days in the time series of the expansion coefficients of the FOF2 data. When you look at the disturbed low-latitude ionosphere,
Professor Buyen, can you come to the conclusion in another maybe 2 minutes?
Yes. Yeah, I'm coming to the conclusion right now.
Yeah. Yeah.
So when you look at global climatology of the low-latitude ionospheric electrodynamics, it is fairly well understood. The longitude-dependent climatology of the low-latitude quiet time electric fields and currents is now fairly well understood. And these are basically reproduced by global ionospheric models, at least for moderate and high solar flux conditions. The basic responses of the low-latitude electric fields and currents to the solar wind electric field and high-latitude convection during moderately disturbed times are also well understood and simulated by the global convection models. The major challenge, of course, is now in the study of low-latitude system, the electrodynamics is now centered on their complex spatial and temporal variability, particularly during large magnetic storms. Our university also working towards this. This includes the effects of preconditioning, magnetospheric reconfiguration, storms, magnetic clouds, high-speed streams, and ionospheric conductance on PP, as well as the interaction of prompt penetration and disturbance dynamo mechanisms. The electrodynamic effect of atmospheric gravity and planetary waves and tidal-driven thermospheric winds still needs to be better understood. And to resolve these processes, groundbreaking measurements are required, particularly in the 100 to 200 kilometer region. And there is a need to provide measurements in the upper atmosphere to complement and calibrate remote sensing measurements and to help accurately model the upper atmosphere. So I hope that DISA will greatly contribute in this direction. And thank you for your patience. Thank you very much.
Thank you, Professor Buyen. It was a very nice talk on the mid and high latitude ionosphere thermosphere processes. There are a couple of queries. I'm not able to read it. Just 1 minute. Yeah. Just 1 minute. We'll go to quickly. What is the comment? How? Can you read it? I'm not able to read. Vineet? Can you read the question?
He's asking how okay, sir, I will send the answer in the comment.
Yeah, okay. Okay, so now we will move on to the next presentation. That is by Dr. Shivakantan Mani. He's from the Institute of Atmospheric Physics, Germany, on the mid and high latitude ionospheric thermospheric processes. Over to you, Shivakantan.
Hello, sir. Could you hear me?
Yeah, you're audible. Yeah. Your PPT is seen. You can go to full screen mode.
Yeah, thank you.
Yeah, that's fine. Please go ahead.
Yeah, thank you very much for this nice opportunity. Today I am going to talk about the mid and high latitude processes. Here, as you know, this is a wide topic. Rather than focusing on the specific results, I wish to give a broad overview about the various processes, and some of them I want to emphasize more in detail. So before going to the scientific part, I want to give a brief overview about the region which we are talking about. That is the ionosphere, thermosphere. In this cartoon, you can see in the right side, there is a red line, which is the electron density. It is starting from around 60 kilometer onwards vertically. The lower part is the T region, and then after that E region and F1, F2 layer in the higher altitudes. And these are all some of the radiations which supports the formation of the ionosphere in the atmosphere. So in this cartoon, you also can see the yellow line, which is the temperature thermal structure. As you can see, the troposphere, where the temperature is decreasing with respect to altitude, and the stratosphere, the temperature is increasing with altitude. In the mesosphere, again, the temperature is decreasing. Above the mesosphere, the temperature is increasing. And this region is called the thermosphere. And you can see the ionosphere, thermosphere, they are coupled together. And there are some of the processes which is happening in this ionosphere. For example, air glow, which is which is occurring due to the chemical reactions, and the aurora, which is due to the charged particle precipitation, and the fascinating noctilucent clouds, which is in the polar regions, especially during the summer. And these here, we also can see some of the observations or the instruments like a LiDAR or radar, optical cameras or photometers. These are all the instruments which frequently used to understand this region. And sometimes the rocket launching. And in addition to this ground-based measurement, we are also using the satellites to study this ionosphere thermosphere region. And in the next slide, before that, the important or the more important point here is that if you are looking the height range from 100 to 200 kilometers, it is the very least explored region, because for the ground-based instrument, it is very far. For the satellite measurement, it is very low. So collecting information about this region is very, very important to understand the dynamics as well as the coupling. So here you can see in the cartoon various coupling processes occurring in the atmosphere, ionosphere, magnetosphere system. In this cartoon, the yellow lines, which denotes the neutral dynamics, and the white arrows, which is denoting the plasma dynamics. You can see the red portion, which is called the auroral oval region. The maximum charged particle precipitation occur over there. There the aurora is occurring, and after that, this is the region called ionospheric trough region. Addition to this solar or the forcing, we also can see the forcing from the below, which is through the gravity waves, tides, and so on. In this study, we are mainly focusing on this region, which is highlighted here. Please remember that these are not a single layers, for example, high latitude or mid latitude, low latitude. Overall, they are coupled. Whatever happening in one region, that can directly or indirectly can affect the other region. So some of the interesting high latitude processes, what are they? For example, auroral electrojet, which is the intense current in a narrow region of the auroral oval. Let us take approximately 64 to 78 or 80 degree latitude belt. And then the high latitude E and F region irregularities. This is different from the low latitude irregularities, especially what makes the difference. In the low latitude, the magnetic field lines are horizontal, almost horizontal. When you are going to the high latitude, the magnetic field lines are almost perpendicular. So that makes a lot of changes in the processes, especially in the low latitude. The irregularities are mainly driven by driven by the Rayleigh-Taylor instability. In the high latitude, these irregularities are driven by the E cross B instabilities. So other fascinating phenomena is the aurora. As you know, the auroral study is having very long history, more than a decade. Before we know the ionosphere, people existence of the ionosphere, people started to see the auroral lights, and the in-depth study of the aurora gave many insights, like various kind of auroras, like a discrete aurora, diffuse aurora, pulsating aurora, and so on. And one of the examples, another thing is this stable auroral rate arc, which is also a part of aurora, which is detached from the actual auroral oval. And this is example for aurora. Many people have seen, and this is one of the tourism excitement for these Scandinavian countries. And here you can see this is the auroral region, which is between 64 to 74 degree latitudes, but the red sub-auroral red arc is detached from the main auroral region. The scientists are believing that they are mainly caused by the plasmaspheric charged particle injection. And there are some couple of new insights that is called, one is tune, another is strong thermal velocity enhancement that I will give more detail in the next slide, and traveling ionospheric disturbances that also I will give more brief in my later slides, and polar mesospheric clouds that also I will give in the upcoming slides. So what is tunes? If you are seeing in this figure, this is the typical aurora. In this, the people are started to see the wave kind of structures. Here, one point I want to highlight is that there are two new discoveries in the auroral region. One is the tune and another one is the steves. The both are not discovered by the planned scientific activity. It was discovered through the citizen scientists, which means they don't have any background about the atmospheric physics, but through their interest, through them, the scientists got to know about these events, the tunes. In the tunes, you can see there are some wave kind of activities, and further analysis, people understood that it is not caused by the magnetospheric charged particle injection, and the altitude is very low, let us approximately 80 to 100 kilometer altitude, and then people are believing that the mesospheric bore, which is commonly observed in other latitudes, also could be manifested in the aurora emission. Auroral emission, that's what we are seeing, but it needs more study to understand whether what is really. And this another interesting is the steves. What is steves? It is a purple emission in the near auroral oval region, and if you are looking its characteristics, it is very narrow in latitudes, and longitudinally it is extending very large distance. And moreover, using other instruments, simultaneous instruments, people understood that inside the steves, there is a very strong westward plasma flow that could be the so-called sub-auroral ion flow. So scientists are doubting that these steves could be the optical optical side of the set, but still more characteristics and their occurrence things are still under investigation. And one thing is very sure, that this is not a typical aurora, this is different from the auroral activity. And this is one of the last 30 years, it is well known study, the polar mesospheric summer echoes for the radar community and the noctilucent cloud for the optical community. This is 9 years of composite radar observation over Andoya, the northern hemisphere. Here you can see that there is a strong echo during the summer month above 80 kilometer. This is called polar mesospheric summer echoes, and the analysis shows that they are mainly caused by the irregularities in the electron density and combined with the aerosol particles. And in addition to these polar mesospheric winter echoes, people also observing other echoes in other months, which are called as polar mesospheric winter echoes. The investigations are going on to understand the characteristics and the controlling mechanism. And if you are looking at the optical side of the polar mesospheric echoes, which is called the noctilucent clouds, this is from the AIM satellite. AIM stands for atmosphere aeronomy of ice in the mesosphere, and this satellite is dedicated for the noctilucent cloud measurement. Recently NASA have done conducted a campaign which is called PMSC Turbo. In that, they used the large distance moving balloons. In that, they also installed lidars and cameras. Then they studied about the noctilucent clouds. I will show a very fascinating video. You can see here the noctilucent clouds. It looks like various wave activities in different scales, from turbulence to gravity wave. We can see in these things. If you are seeing the same analogy with our ocean waves in this here you can see they are almost looking similar, which means the MLT region is more dynamics. One part is to understand the underlying physical processes which causing the mesospheric clouds. And another interesting thing is using these clouds as tracers to study the dynamics of the MLT region in the high latitude. Recent times, people also observed that these noctilucent clouds not only bounded into the high latitude, even in the mid latitude, as low as 45 degree latitude, people started to observe the noctilucent clouds. Moreover, the brightness of the noctilucent cloud also increasing. People are the atmospheric community doubting that this could be the implication of or the implication of the global warming effect. Anyways, that need more study. And when we are coming to the mid-latitude IT processes, there are few processes just like sporadic key layer. As you know, the sporadic key layer is not only occurring in the mid-latitude, they are also occurring in the high as well as the low latitude. But the underlying physical, the controlling process are different for each latitude. Particularly in the mid-latitude, the wind shear mechanism is believed to be the driver for these sporadic ES layers. For example, in the top figure, you can see the zonal wind. When there is an eastward wind in the lower layer and westward wind in the upper layer, they can converge the ions and they can create the sporadic E layer. In the case of meridional wind, the northward wind pushes the plasma down, and the southward wind pushes the plasma up, then conversion can cause, then it can create the sporadic ES layer. So what we don't understand? In general, sporadic E layer is occurring maximum during summer. However, when we are looking the wind variation in the MLT region, the shear is present always almost most of the time. So why the sporadic E layer is occurring only during summer? Why not in other season? Though the wind shear is there. So still it is one of the open question for the middle atmospheric scientific community. And other thing I will explain here is that October fall effect. That is one of the interesting phenomena which is observed in the very low frequency range. And I will give a brief about the medium scale traveling ionospheric disturbances. Apart from a particular processes, the processes which is happening in other part like high latitude as well as the low latitude also can impact the mid latitude. How? When there is a strong geomagnetic activity, then the expansion of auroral oven, Joule heating can trigger the wind, then they can affect the mid latitudes. Similarly, in the geomagnetic storm time, the plasma bubble even it can reach up to 40 degree latitudes. And in addition to that, there is also a process called interhemispheric coupling. As you know, this ionosphere is not only bounded by the neutral and the magnetic fields. These magnetic fields are well connected through both the hemisphere, connected in the both hemisphere. When there is any changes in the electric field or currents, which can affect the other part of the hemisphere also. So, what is fall effect? This is the very low frequency amplitude measurement over Sodenkaila, a high latitude station. In general, the amplitude variation of the VLF is expected to follow the solar zenith angle. You can see the black curve with the solar zenith angle, and the dotted curve is the average 9-year average VLF amplitude. But in the September-October month, there is a deviation from the expectation. If you are reviewing the mean, we could see the deviation here. There is a sharp enhancement in the VLF amplitude. What could be the cause of this enhancement? And whether it is a local phenomena or it could be a global phenomena. We also they also checked other station VLF signal also. It is there in almost all the four different stations. It looks like it could be a global phenomena. And then what could be the driver for this enhancement? Then they also looked into the temperature and the temperature from MLS, which shows a sharp degrees around that month. and the tidal amplitude S2 tides are enhancing. So whether this dynamical change in the D region could cause this VLF signal, enhancement in the VLF signal or not, investigations are going on that direction. And other topic is the traveling atmospheric disturbances. It is a wave kind of undulation which is occurring in the high and mid latitude atmosphere, mid latitude region. Based on the scale size, they are divided into two categories. One is the large scale traveling atmospheric disturbances, which is mainly driven by the geomagnetic disturbances in the high latitude, and also some occasions from the polar vortex changes also can trigger the LSTIDs. And the medium scale traveling atmospheric disturbances, which is having the scale size of 300 kilometer, and that is again classified into two categories. One is daytime MSTIDs and another is nighttime MSTIDs. Here you can see the MSTID example. They are having very large extent of the large longitudinal coverage. And see what makes the day and nighttime difference? Mainly the propagation direction. In the daytime, they are mostly propagating southward or southeastward. In the nighttime, they are propagating into the southwestward direction. Further analysis shows that the nighttime MSTIDs could be caused by the electrodynamical processes, and the daytime MSTID could be caused by the gravity activity. Here I am giving an overview of the MSTIDs. Mostly the characteristics wise, then daytime MSTID is occurring during the winter time, maximum occurrence, and they did not show any longitudinal dependency. And on the other hand, the nighttime MSTID occurrence is maximum during the solstice month, and it shows very clear longitudinal as well as solar cycle dependency. The source, when you are coming to the source, their primary or secondary gravity wave could be the prime source for the daytime MSTIDs. The Perkins instability and ER and F region coupling, inter-hemispheric coupling could be the source for the nighttime MSTID. And what is an open question regarding this topic is... Yeah.
Hello.
Yeah.
In 2 minutes, can you come to the conclusion?
Yeah, sure. So this is one of the examples we are trying to understand the onset of MSTID. The MSTIDs are mainly occurring in the mid latitude. Then what extent it can occur? We used the Coulomb-Span airglow imager, which is near high mid latitude transition region. Our analysis shows that sporadically associated electric field could cause this MSTID. But the interesting part is this is observed during the equinoctial month. And what causes the MSTID? I mean, why how these sporadically occurring during equinox, and those things we are studying in detail. And other interesting thing is, it is another one thing called we have observed the plasma depletion in over Hanley in a low mid latitude transition region. And our analysis, it is not following a traditional MSTID, as it will have more consecutive waves. It is having only one or two strips. And what makes the onset of these kind of MSTID over low mid latitude transition region? More statistical studies we are looking forward. And what are the unresolved problem in these topics? The tunes, whether they are mesospheric pores or and how are gravity waves and how frequently they are occurring. And that people don't know. Then studies are going on regarding that. And the steves, what is the source region for the steves, that we don't know. Moreover, the sporadic layer occurrence is maximum during summer, even though the wind shear is observed almost all the time. And then the LSTID, what decides the occurrence of LSTID? Sometimes even large geometric disturbances does not produce LSTID. So those are all still an open question in this topic. So what are the challenges to address those problems? As we know, as I told in the introduction slide, this region from 100 to 200 is the least explored region in the sense of very high for the ground-based measurement, very low for the satellite measurement. If we could get the composition, electric field and winds temperature around this region, we can solve many problems. So what we can do for that, if we can able to make a dedicated satellite mission for the high and mid latitude measurement of winds, electric field temperature, we can try to understand the processes very well through globally. As another point is, most of the ground-based observations are located in the northern hemisphere. When the same kind of things can occur in the southern hemisphere, which is very less ground-based observation we are having. The satellite measurement is very much suitable things to study the unexplored southern hemisphere also. So why this study is important? It is not only for the scientific understanding, it is also essential for the better weather forecasting, because now recent times the growing interest in the re-entry spacecraft required more information and detailed understanding about the dynamics which can cause the failure of the re-entry. As previously Dr. Fazlul also pointed out, many of the satellites are re-entry spacecrafts are failed. And not only that, for scientific aspect, there are some scientific groups, they are looking for the very low Earth orbital satellite mission. To successfully implementing those kind of satellite mission also, we need to know the dynamics of we need to understand the IT dynamics. Yeah, thank you very much for your kind attention.
Okay, thank you, Dr. Shivakandan. It was very nice. I think there are a couple of comments here. I don't know whether we have time. Is there anything, Vinny? What is can you read it? I think it's yeah, that is by Bhuyan, the answer given by Bhuyan. The next is by, okay. Okay. There are no further comments and no further questions. I thank all the three speakers, Professor Kalyan Bhuyan, Dr. Fazlul Alaskar, and Dr. Shivakandan Mani for their excellent presentations. And thank you very much. And thank you, TP. Over to you.
Thank you very much, Dr. Rajiv sir, for this vibrant session. And also to the speakers, Professor Kalyan Bhuyan, Dr. Fazlul Alaskar, and Dr. Shivanandan Mani for your presentation. And this concludes the session 5. And we take it forward to the session 6, which is on the ground-based facilities for ionosphere-thermosphere system and challenges in modeling. The session will be chaired by Dr. M.P. Sunil Krishna from IIT Roorkee. Only request to Sunil Krishna ji is to ensure that the meeting, this session concludes at 18:15 hours because of certain technical reasons. Over to you, Dr. Sunil.
Thank you, Dr. Das. I'll try my best. Good evening, everyone. So I welcome you all to the session 6, which is ground-based facilities for ionospheric and thermospheric system and challenges in modeling. So this session aims to present understanding of various tools and methods like ground-based observations and modeling to complement the Disha observations. So the first talk today we have is ground-based facilities in the country for the IT system research and required augmentation in the context of Disha by Dr. A.K. Patra from National Atmospheric Research Laboratory, Gardanki. I would briefly introduce Dr. A.K. Patra for the audience. He is an accomplished and renowned researcher in the Aeronomy community. Dr. Patra is currently the director of the Atmospheric Research Laboratory, where he is also heading the atmospheric and space physics. He is a fellow of International Science Academy and Indian Academy of Sciences. So with this brief introduction, I would invite Dr. Patra to deliver his talk. Dr. Patra?
Yeah, thank you very much. Are you?
Yeah.
Is it okay? Can you see my slide?
Yes.
Okay, fine. Thank you very much. I have been asked to give the ground-based instruments for IT research in our country and required augmentation in the context of DISA. And I will be very brief. So I think here is a diagram where we are talking about the thermosphere on the left, the temperature, and then on the right side you have the electron density. So this gives us idea about that what kind of temperature and what kind of electron density we are talking about in that height region. Of course, you have the neutral density on the far east. Now, when we talk about the ionosphere-thermosphere system, so we are talking about the measurement, particularly about thermosphere. We are interested in neutral density, neutral temperature, and neutral wind. And when we talk about ionosphere, we talk about electron/ion density. ion composition, electric field DC and AC both, and of course current. So these are actually of interest to us. And now, this is okay, fine. So now in the country, if you look at that, what kind of experiments we have and where are they located. So I try to give some kind of a picture about those things. So one is the Ionosonde, which has been there in the country for quite a long time. And this is basically a sweep frequency HF sounder, and which measures electron density, basically, as a plasma frequency reflection comes from the ionosphere. And one can get up to the peak of the peak altitude of the ionosphere, and beyond which this cannot provide information. So topside informations are not provided by this system. And one can also get some kind of drift, although they need to be really calibrated properly. They need to be corrected for the production and loss processes. Something can be done, but this is not the right tool to get the drift, but it provides some information about drift at a certain time. So if you look at from in the map, you have at Trivandrum and Tirunelveli, there are two Ionosondes. They are actually digital Ionosondes. We have one at Gadanki, one in Hyderabad. I hope it is working. It's a caddy. Ahmedabad is working. Bhopal, I'm not sure. I have put a question mark. Delhi and Dibrugarh also. There was one earlier working. Now I think it's not working. So somebody can give me some information about that. So these are the kind of stations we have in the country. Now, magnetometer is also an important component for ionospheric research, particularly about the electrojet. It is very, very important in the quiet condition I am talking about. And of course, in the geomagnetic storm condition, of course, all these observations are useful. And IAG is known for its magnetometer chain, and right from the equator to Gulmarg, and also from left Rajkot to Silchar. So they have a very good observatory and they are maintaining well, and many publications have come. So this basically measures the magnetic field, so one can talk about the ionospheric current, total current. So these kind of observations are available in the country. Now, other thing is the Ionosonde. It's not Ionosonde, air glow photometer and imager. We have also a very strong heritage in the country about air glow instruments. And we have photometer, imager, multi-wavelength, of course, photometer, and then also with scanning capability. So this gives us some information about electron density structure, like people are talking about plasma depletion in the F region, which are linked with the equatorial plasma bubble. And also MSTIDs, people are studying using this. And we have also rotational vibrational temperature, that is at the lower part of the thermosphere, that is OH, and then 95, 97, those oxygen lines. And thermospheric wind can be derived using air glow instrument. I think right now there is one at Trivandrum operated by SPL. And anyway, I'll come up with that proposal that maybe at few more places we can have Fabry-Perot system. Coherent backscatter radars, also we have a good heritage starting from Tumba. And now we have 18 megahertz working from Tumba, and at Gadanki we have a 30 megahertz dedicated radar for ionospheric research. And also there are 50 megahertz radars. One is 53 megahertz, which is a powerful MST radar located at Gadanki. One is coming up in Kolkata here. So this figure you can see the radars. And Cochin, Guwahati and Nainital, they operate around 200 megahertz. Gadanki we have 53 and Kolkata is 50 megahertz. So these radars can be used to study plasma irregularities when the ionosphere becomes disturbed, and using those irregularities as a tracer, one can study the dynamics during that time. They, however, do not provide measurement about the background ionospheric state parameters such as electron density, electric field, except at 150 kilometers. Sorry, there's a typo here. Except at 150 kilometers during daytime, when you can see the daytime 150 kilometer echoes. So the background ionospheric information, however, are not provided by these radars. if they are properly upgraded and proper technique is used, it is possible to operate them in the incoherent scatter mode to provide us the background information, which we don't have right now. So coming to the required augmentation, so as I mentioned before, there is one at Trivandrum, and I think a few more if we can operate at different places where sky conditions are good and operational facilities are there, the logistics are available. It could be a good addition to study the thermospheric wind. Although it is not easy to collect data simultaneously because of the sky conditions, nevertheless, we'll have a fairly good information about the thermosphere, but this will be a good step because we can have continuous observation of the thermospheric wind, which we do not have much at this moment. Now coming to the navigation satellite, I think this is one many have in the country. If it is possible to gather all the data, I think it will be a good exercise to get the total electron content, and we can get a map that is the entire country, the way that total electron content is varying. This has important applications in terms of studying the ionospheric variability, the quiet as well as the disturbed condition, and more importantly, these information can be used for developing some kind of model which can be used for correction in the navigation. And also these receivers are capable of studying scintillation, which are linked with ionospheric plasma irregularities. So one can study that what kind of blackout is happening when the plasma irregularities are overhead. So here is actually an exercise that what would be the optimum number of this kind of receiver. These are actually navigation satellite like GNSS, which are all GPS, GLONASS, Galileo, Beidou, this kind of receiver, which are orbiting type. And so we found that about 60 receivers, if we put like this, then we will have a very good coverage about the Indian region, and those things can be used for the application. Now there is another one which is our own constellation called NAVIC, and so this has also its unique geometry, and unlike the other satellite GPS or GNSS satellite which are orbiting in nature, but there are some here out of the 7 satellites so which are stationary. So one can always monitor a particular ionosphere continuously. So this has some advantage. One can utilize that. So this is so the 3 geostationary satellites can be used, and then you can have wherever we feel we can have the receiver. I think NAVIC receivers are being built and upgraded continuously. Once they are available, I think they will be very useful tool for studying the ionosphere in a greater detail, because the orbiting part of it, those things can be avoided. I mean, whatever errors are coming from that. So this will continuously monitor at a particular location, and such information can be useful for both science as well as application so far as navigation is concerned. I think this is one tool which is a very powerful tool which we have been talking for quite some time, and I also mentioned before that incoherent scatter radar is a very powerful tool, and most of the model that we see today internationally, they have been actually enriched by the information provided by the incoherent scatter, right from equator to the polar region. So this kind of radar can provide electron density, electric field, composition, TE and TI, and also meridional lateral wind, particularly when we talk about the equatorial belt. So this is, however, very complicated. It's not complicated from hardware point of view, but the data processing is very complex, and it is an involved job. But this is something, if we can build, I think the IT research, because the advantage of this is that it provides high profile of all these parameters. So all these detail science that we are talking about, the IT system, those things can be actually studied in greater detail when we have the information coming from DISA. So I think that's all for the moment. Thank you.
Thank you, Dr. Patra. So let me see if there are any questions. Yeah, at the moment there are no questions as such. So
Fine, thank you.
Thank you so much. So with this, we can move on to the next presentation, which is by Dr. Sampath Kumar Panda from KL University. It is on assessment of ionospheric models through satellite and ground-based measurements. Dr. Sampath Panda is currently working as an associate professor in the Department of Electronics and Communication at KL University, Vijayawada. He is currently associated with the Space Technology and Atmospheric Sciences Research Center in the KL University. His research includes space weather remote sensing through ground-based and space-based DNS observation and modeling of total electron content. I now invite Dr. Panda to deliver his talk.
Yeah, thank you. Is my voice audible and PPT is visible?
Yes, yes, yes.
Yeah.
Please go ahead. You have 15 minutes.
Yeah, okay. So thank you for giving me this opportunity. So today my presentation will be on ionospheric and plasmaspheric contribution in IT system by collocated ground and space-based observation and some model assessments. So if you see the figure on the right side, the different layers of the atmosphere starting from the troposphere to the exosphere, we have the concerning this ionization, we have the ionosphere and plasmasphere on the top. The accurate representation of both top side and bottom side as well as the plasmasphere is a major concern in the community now, because the full altitude electron density profile specification is restricted by simultaneous lack of adequate ground and space-based datasets. So the a sensible assimilation can be done by taking the topside profiles from radio occultation data, which is space-based GNSS observations, and the ground-based DG sonde as well as the GPS measurements. And the full profile can be reconstructed by taking all these profiles from different ground and space-based observations rather than taking and making an extrapolation techniques. So here one study I want to explain here about one study in which we have considered about 39 globally distributed DG sonde from Giro network during 2007 to 2015. And we selected these topside profiles from Formosat 3 or cosmic measurements by taking a constant of 3 degree latitude longitude and 15-minute temporal resolution. And the GPS data, the collocated GPS data are also considered along with this DG sonde stations. A strict max pair criterion has been considered within the given space-time collocation. As for our observation, most of the GPS stations are within 1 degree from the DG sonde locations. So here what we have done, we extracted the electron content from different ground and space-based stations. One is this bottom side profile is taken from the Giro digisones, which acts as the growth profiles because of this. These are the direct. These are taken from the direct radar soundings. And in this, we have selected only this profiles with the confidence score in 100. Most of the observations are within 15-minute resolution. Bottom side profile is to determine the integral bottom side TEC, and the top side profile is taken from the cosmic as a top side TEC. So here, if you see the total electron, the ionospheric integrated ionospheric electron content is the combination of this bottom side as well as the top side. So here, rather than extrapolating this bottom side to top side or top side to bottom side, a strict coincidence is taken between this between this DG Sunday and cosmic profiles, and from that this through numerical integration the ionospheric electron content has been retrieved, and along with that this GPS TEC also extracted, which is a combination of ionospheric electron content as well as plasmaspheric electron. So by subtracting this ionospheric electron integrated ionospheric electron content from this GPS TC, we can get the estimate of plasmaspheric electron TC. So this is the methodology followed here. The decision data giving this bottom side TC, cosmic data giving top side TC. Then from IGS we can get the plasmaspheric electron content. So along with these observations, I would highlight these the estimations from this IRI model, then this standard plasmasphere ionosphere model, or it is popularly now called as IRI plus model, and the NEPQ model. These three models are considered how to see the performance of this model in calculating this bottom side, top side, and integrated ionospheric content, the total electron content, as well as the plasmaspheric electron. Some statistical measures are done to evaluate their performance. So this right side figure shows this one is a DG Sunday profile, the black one, and the blue one is the cosmic profile. Now in DG Sunday we considered this bottom side, and in cosmic we considered the top side, and both are combined to give the merged profile of this merged profile of the ionosphere at the DG Sunday location. And this plasmaspheric electron content is extracted from IRI with its default upper limit as a 2000 km, and from IRI plus and NEPQ 2 model with upper limit as 20,000 km. So basically we got around 600 profiles for which this study has been carried out. And here you can see the bottom side TEC from DG Sunday and the models with their type number summary statistics. And below I show this maximum absolute error between the DG Sunday bottom side TEC as well as and the model estimates. It shows that IRI and IRI gives the closest value than the other two models, and NEPQ underestimate the DG Sunday BTC, and the probabilities, these PDFs and the CDFs confirm more spread and lesser symmetric distribution of the residuals for NEPQ model here. So here we saw the scatter plots and regressions of DG Sunday BTC, IRI, IRI plus, and NEPQ BTC. And this shows that there is a good correlation. All of the models give good correlation and slopes with the DG Sunday BTC. But the IRI estimate performs relatively better than the other two models. Regarding the cosmic topside TEC and the model estimates, the upper limit of the cosmic profile is not constant; it is variable, and the general distribution of the observed and model topside TEC values are quite similar. Closest estimates of a topside TEC value from IRI and NEPQ models to the cosmic observation than the IRI observation is in here. And the IRI plus with the asymmetric distribution of the probability around median and overestimate the cosmic topside TEC can be seen in the figure. From this scatter plots, we can see that the correlations are above 80% cases. However, the better performance of IRI is seen here, followed by NEPQ, and the RMS values are also calculated from this values. Now this integrated ionospheric electron content is also determined by taking all these two, this bottom side and the top side profiles. Similar patterns with slightly varying statistics is observed in this case, and the this deviation of IRA plus from the integrated ionospheric electron content is comparatively more than the other two models. But here, now from this statistics, we can see IRA plus is slightly overestimating and NEPIC is slightly underestimating. Both are they are having an opposite characteristics, and IRA and IRA plus models having higher correlations. IRA give the better performance. All these models here. Now we here in this case the GP's total electron content is taken, and this comparison has been done. This slightly overestimation of IRA plus model is observed here, with its maximum absolute error lowest in IRA plus, but there is a discrepancy in the values among these models which are observed here. And from this statistics also, it is seen that IRA plus has the least error matrix, and any quick performance among these other two models, any quick performs better than the IRA. One thing should be noted here that unlike IRA plus, the topside configuration in any quick doesn't accompany any plasmaspheric definition. However, this is extended up to the GPS altitude, so here an exercise has been done to track the plasmaspheric content from this NEPK also. From our statistics, all the models underestimate the GPS plasmaspheric electron content, with maximum difference being noticed in IRA and minimum difference in IRA plus. This confirms IRA plus representing quite near PS plasmaspheric magnitudes to that of GPS PSA than the other two models. And this, if you see the scatter plots here, there is high correlation in GPS versus IRA plus estimation than the other two models. NEPK has a lower prediction error matrix and least negative coefficients of efficiency. In general, the prediction errors for the three models, low correlation and negative coefficients of efficiency observed for model plasmaspheric electron content, indirectly they are low agreement with the GPSP. So the summary can be this concurrent observation from these three different methods with space and time collocation enables to extract bottom side, top side, as well as plasmaspheric contributions. Though there are certain uncertainties are there, performance of empirical ionospheric and plasmaspheric models has been here. So all these three are global models. This complements the collective needs for real-time estimation bottom side and top side ionospheric present scheme. Though the present scheme is simple and unambiguous, and the number of matched observation is sparse, IRA bottom side estimates are closer to decision day observations, followed by IRA plus and NEPIC. Convergence of IRA top side estimates with cosmic profiles, followed by NEPIC and IRA plus are observed. And IRA plus and NEPIC highlight their opposite behavior between bottom side and top side. Concerning integrated ionospheric electron content, IRA plus slightly overestimate the observed value as compared to IRA and NEPIC. The discrepancy in the TEC estimations from models could be attributed to the limitations in the upper limit of the model, IRA model, plasmaspheric model overestimation, and non-inclusion of the plasmaspheric definition in NEPIC model. In fact, in the IRA model, recently there is one updation that the extrapolation option is there up to 10,000 kilometers than the than it was previously 2000 kilometers. Concerning plasmaspheric electron content estimation, all the models relatively offer very reduced, say subdued agreement with diabetic piece. Thank you. I'll be happy to take some queries.
Thank you, Dr. Panda. At the moment, there are no questions in the chat box. So you can reply to queries if somebody asks a question later.
Yes, sir.
Thank you. Thank you for finishing on time. So the last and the final presentation for today is by Dr. Bitap Kalita from Digbrugad University. He will be talking on challenges and opportunities in regional IT system modeling. Dr. Kalita is working as an associate professor at Department of Physics and Center for Atmospheric Studies, Digbrugad University. His main research area includes modeling and GPS-based understanding of equatorial ionospheric phenomena, conjugate hemispheric asymmetry, SSW impact on ionosphere, and so on. So with this, I request Dr. Kalita to deliver his talk. Yeah, Dr. Kalita, we are not able to hear you. Can you?
Yeah, are you able to hear me now?
Yes, we are able to hear you, but not your presentation is not visible.
Yeah, we are loading your presentation, Dr. Kalita. Is it visible?
Just a minute. Yeah, we can do like that also. It has come. Can I share it from my side? It will be much easier actually.
Okay, sure.
Yeah, is it visible now?
Yes. Yes.
Yeah. Okay. So again, a very good afternoon to everybody, and thanks for headquarters for the National Meet on Aeronomy Research. So today, actually, we have discussed almost thoroughly, most major issues relating to ionosphere thermospheric systems, very intricate detail, very new informations we have learned. So I will just try to focus on the modeling aspect of this informations. So my presentation will basically cover why we do modeling for a system, motivations, challenges to the modeling of the ionosphere, challenges to regional modeling system, the currently existing models and their issues, and the opportunities that lies in this domain. So why we model the ionosphere, basically we have all learned today that we are dependent so much on the space technology. So we need to know ionospheric effect for these systems to reliably perform and they keep in their healthy state. So that is the importance of ionospheric effect. But for doing that, we need to have a very good understanding of the ionospheric effect on these systems, and our understanding is not complete. So these models not only serve the purpose of an operational aid to the system, but it also improves our understanding of the systems. So ionosphere thermosphere is a coupled system. We have again heard because today we have discussed about all these things. Because the ionospheric plasma is only 1% of the ionospheric atmospheric mass, which is mostly neutral. And this system also takes input from both upper and lower altitude, that is from lower atmospheric neutral forcings and from magnetosphere. and the background interaction of the neutral and plasma is not very well understood. This already we have actually gone through, so I will not discuss, I'll just go through. But the major factor is that ionosphere and thermosphere, both systems are actually oriented in different reference frame. Like ionosphere is under magnetic oriented system where processes are controlled by electrodynamics and magnetic field lines, where thermosphere is controlled by the solar radiations, and so it is oriented in the neutral frame of reference. So they couple with some kind of an offset in major longitude sectors where geomagnetic and geographic equators are at different region. So that kind of complicates the system. So I'll briefly just highlighting what is empirical and theoretical modeling. We already know actually, but for the continuity, that empirical modeling, we are based on experimental observations on similar geophysical condition. We try to predict the future behavior, and definitely it requires a large set of data. Whereas in case of theoretical modeling, it is physics-based, equation is used, and data also used, but basically equations are used. Then we come to regional and global modeling. Global modeling means we are trying to model the whole system as a global coupled system, whereas in a regional model, we try to take a limited area and a limited problem for higher resolution to reduce cost, get some specific domain or area specific, like country specific problems. But the problem is that whole system is actually globally connected and it is coupled. So going to regional domain, although it is practical and cost effective, is not very easy. So what are the modeling challenges of the coupled system? We are already discussed that ionosphere, thermosphere is coupled to the magnetosphere and mesosphere, stratosphere below. Drivers that affect the systems are from different domains like solar radiation, chemical processes, dynamics of the waves and wind drags, and the electrodynamics or electric field and magnetospheric, local and magnetospheric electric field. So currently we have many models which address different aspects, different part of the system, like atmospheric models, which basically gives you the idea of the neutral atmosphere. Then the electrodynamic model, which consider the electrodynamics of the system. Then MSD model, which basically gives you the response of the magnetosphere, and the neutral ionospheric, neutral models like MSIS or compositions. The major challenge in this is the variability of the system. That again we have already discussed that it's a very, very variable system. The primary solar variation is per type at most of the times. The variation can be from minute to minute during disturbed times like solar flare and eclipse, and it varies with latitude, longitude, and altitude. The spatial variation is also very high. So even during the solar quiet time, the variation can be from minute to years. 11-year cycle is there, and drastic changes occur. But the problem is that even the 11-year solar cycle, which is sort of been studied for a long time, we are not exactly able to model the solar cycle variation of density or TC. For example, we have for a long time we have thought that the TC and NMF2 varies with solar activity and shows saturation effect, that at high solar activity TC and NMF2 does not change as much as it does in lower solar activity. But recently, many papers have shown that not just saturation, but amplification also, which can happen with solar activity. Like this is one observation that I have shown for Dibrugarh, but it has also been reported from other latitudes that your any NMF2 or TC can vary in such a manner that increases at a much higher speed when the solar activity increases. So this means that this knowledge or understanding of the solar activity effect in the ionosphere is still not clear, even in the long-term climatological case. Just forget about the short-time variability. And then the IRI, the International Referred Ionospheric Model, which is sort of the standard case of ionospheric model, still is not able to exactly provide the solar activity after so many years of effort and so many people being involved. Like I can show you this is the plot that we have shown again for 2 stations of Dibrugarh and Okinawa, which is showed in 2019. That if we see the observation IRI for high solar activity and low solar activity years, it performs differently. So let us go back to the fact that even very long-term climatological understanding in very simple and long-time studied things like solar variation is not very clear yet. The spatial variations are also there. we know equatorial anomaly, which produces a latitudinal variation, very high intensity crest, which can be 3-4 times the density of the trough. And the location of the crest and troughs can vary from day to day, from year, from month. And then longitudinal variation is there, which is recently reported that within the longitudes also there are peaks and trough structure. And this peaks and trough structure can be of the WN4 type or WN3 type, even WN2 type. That is, it can be 4 peaks all over the globe, or 3 peaks, or even 2 peaks. And this may exist in density, TC, and even drivers like electrojet, vertical drift, and O by N2, and temperature. Altitudinal variation is also there. That the third special factor also be there, because F2 layer altitude changes. There is sometime F3 layer, sometime it is not present. And then O by H2 transition height, which basically decides the top side profiles, as my previous talk, Dr. Panda has shown that plasmaspheric content and all this varies even in the model currently. Depends so much on the O by H2 transition height, which is again is not currently very well known. So all these variations are also sensitive to seasonal changes. So because the ionosphere is coupled to the thermosphere, we also have to know the neutral environment. And we have related effects like neutral mass anomaly, equatorial temperature anomaly, and midnight temperature anomaly in the neutral environment, which are again very complicated. And because it is a background process, and neutral measurements are even more scarce than ionospheric measurements. Probably some of the talks have highlighted that neutral spectroscopic mass spectroscopy measurements are very, very rare, and DISHA is something that is going to bring some changes in this factor. So neutral density and composition measurements are very, very limited. MSIS and NRL MSIS, which are the current model that we use, are not adequate, and most of the times are not able to represent the numerical background, neutral composition that is required for the ionospheric models to work. The chemistry to work. So basically, after the CHAMP satellite, there is no such neutral measurements at all. Okay, so neutral measurements, wind measurements, again another critical factor dynamics wise, which changes the plasma density, or in fact a lot of other factors like height and all these things. But again, neutral wind measurements are even less, because we need very sophisticated instrument like FPI or inherent scatter radar. So this is another challenge. And then storm-term variation, that is the big bull, because it basically scatters the whole quiet time situation, changes in all respect in a very drastic way, whether it is neutral or so lower atmospheric neutral waves. This is another very challenging thing that is coming up. It is this perturbation, the energy that it can deposit by the wave breaking mechanism in the ionosphere is very, very rare, less known. We don't have much method of studying all this. This periodicity of this wave, which can be vary for minutes, like atmospheric gravity waves, and planetary waves, which can go to up to days. And we don't know how well they actually couple to the ionospheric systems. And this actually gives rise to the day-to-day variability in the equatorial ionization anomaly, or electrojet, or equatorial spread F. Yeah, and that 80 to 200 kilometer region, that is where this wave breaking normally takes place below the F2 layer height, is a very difficult area to probe using satellite or remote sensing, because it's a very high thermospheric density, and satellites are not very easy to post there. And remote sensing also, because it's a less dense, less ionospheric plasma density, work very well. So, but this actually is the lower boundary of that ionosphere, and gives a lot of quiet time input. So it is very important to know about them. And one of the biggest issues for equatorial region like India is that post-sunset equatorial irregularity modeling is required for this. It causes severe scintillation and GPS and trans-ionospheric signals. We know that. Gives rise to positional errors. It varies from day to day and changes with solar activity. And it can be different in quiet and disturbed times. And because it's not a priority of developed countries, which are mostly in middle high latitude, this is something that India region, which are in the equatorial region, has to solve. And then disturbed time eruption that we have heard so much today. I'm just going through just to tell what are the variations that are there, the challenge for our modelers, because in the disturbances, the energy input is very huge, the high latitude magnetosphere, and the coupling through the neutral and electronic processes both can take place. And substorms and IMF can also be local time dependent and longitude dependent. The neutral compositions can vary with latitude and longitude. And these variations are so sharp that the models completely fail. Differences between two longitudes as small as 10 degree can occur. This is something that we have shown in this paper 2016. The St. Patrick's Day storm, Indian and the 95 degree longitude, very close, very similar situation, but there are huge depletion in the 95 degree east, whereas there is no TEC depletion in the Indian sector. So these changes can also last for a long time beyond the triggering event, making it even more difficult for modelers to take care. And we cannot actually even now estimate the energy input and distribution of the energy in the polar region when the storm occurs. So what we require or what is the challenge is a comprehensive understanding of the system, and this has to come from the quantized systematic observations, and global data sets has to be compensated by space-based observation of solar inputs and resultant magnetospheric responses. And India-specific problem must be encountered by regional positioning and regional systems, so that we can take care of the correction for INSS and India-specific problems. Challenges as a global modeling, major problem is the complexity or the requirement of computational power, because it's a huge system. If you take the whole globe, then the equations and the data set becomes very large, because when you solve the mathematically continuity equation and the momentum equation, it has to be done for at least 9 to 10 species and do it for a large area. Then empirical models where artificial neural network based or tomographic, it requires huge computational power. And for higher resolution, we need smaller grids, which again increases your computational powers. So these models also has to simulate lower atmospheric and magnetospheric inputs from outside the model. So additionally, modeling input, how it has to be assimilated. So data assimilation techniques, which are to be used, which is going to perform for a whole system, how it is going to perform. These are some of the computational challenges. In the Indian context of the regional modeling, the region is basically encompasses two gradients in density. Because of the EIA, there is a latitudinal gradient because of the EIA, and there is a longitudinal gradient because of the WN4 or the longitudinal. And the EIA itself is very variable, that we already know. It can be sometimes absent also, like a single crest phenomena, or it can be shifted in latitude. This is something that we have shown in a recent paper in 2022, Kalita et al., that the EIA can shift with season from summer hemisphere to winter hemisphere. And the northern region of the India is basically
Dr. Kalita,
sensitive border area.
Can you conclude in 2 minutes?
Yeah, sure. So where from we need to fix the boundary conditions, and the peak of the longitude also keep changing. So Indian context, we have a very vast area, so we need lot of cells. If you have to put into one grade, then we have to need lot of cells. And if you compare with GeoNet, which is Japanese network, then 20-kilometer interval they have a GPS receiver. So we need very high density receiver networks. We have an area which is surrounded by sea, where we cannot have much more data. So fixing those boundary conditions is another issue. So boundary conditions need to be formulated. Regional specific input has to be provided, like drift for the Indian region, neutral composition from the Indian regions, and then this may be possible using the DISA if it comes up. Okay, and I'll edit the L1 if it comes up, solar elections. So equatorial irregularity, again, there is another challenge. So I'll just skip, like there are other different methods, finite different methods, which are very numerically unstable when you do it in regional modeling scale. Fresnel scale and large scale plasma bubbles are also not compatible in a single model. So 3D nonlinear modeling, the cost. Current state of modeling, we have IRI. We have previously also discussed. It is not very successful for low and equatorial region. SAMI2, which is, I think, the theoretical model is doing well, but it requires input specific for that region, like electrodynamic drift and composition part. So we need measurements from this. So rest of the models I will just skip. And then current Indian model, we have a Dibrugarh University low latitude model for Indian zone, artificial neural net model from Tulsiram, a 2D tomographic model by Bhuya and Bhuya at Dibrugarh, nonlinear models of Sekhar and Chakrabarti, photochemical model, and regional scintillation model developed by IR sir at Rajkot. For Dibrugarh, it basically solves a continuity and momentum equation along the field lines and provides you ion and electron density, temperature. It uses the MSIS 90 neutral composition, Charles-Fraser drift, and HWM winds. Now we have replaced the drift model using Rockset vertical drift, and we are able to replicate the longitudinal variation from 75 to 95 east. Its limitation is it uses only O and H ion species. So we need India-specific drift and neutral density model for this. We also had a 2D tomography model developed by Professor Kalyan Bhuya, who has previously given a talk. Using singular value decombination, it provides electron density. It uses IRI as a regularization background. Using 100 and 200 grid sizes, it is able to replicate the equatorial anomaly, but it is only 2-dimensional. It can be 3-dimensional if we have more dense data. So we need denser TEC. The opportunities are that we have far more observational data in form of lot of GNSS, GPS, TEC networks, ionoson, photometers, and radars newly coming up. We have LEO satellite topside TEC, which is now widely available over the globe, which can be used for these tomographic purposes. Then we have new missions coming from NASA and ESA, like Swarm, Gold, Icon, and these old satellite actually, GRACE missions, which can provide additional data. And upcoming missions like DISA and Aditya can actually be a game changer because it will provide very good, small level detailed data. So opportunities are we can adopt new strategies like for modeling, like Monte Carlo inversion technique used by the art scientists and geosciences, which is a new idea over machine learning. We can have collaboration with other different domains like computer science and mathematics. We can have inter-institute collaboration between different groups which are working in modeling and having different domain knowledge. So we can also have a creation of national computational facility because computational facility is very expensive, so it can be shared. The conclusions from my talk is that regional modeling is the way forward for India. Observational studies must go hand in hand with modeling efforts. We must share the computational power, and new approaches must be taken for solving these mathematical problems. And collaborative modeling project across institutes and universities with new satellite data needs to be encouraged. These are the references. Thank you.
Thank you, Dr. Bhuyan, for highlighting the challenges and the opportunities in modeling the IT system. And I also thank all the speakers, Dr. Patra, Dr. Panda, and Dr. Kalita, for their wonderful lectures. So with this, there are no questions in the chat box. So with this, I can say that I can close the session and hand over Dr. Das.
Thank you, Dr. Sunil, to have nicely driven this session. And the session has indeed been informative, and it shows direction once these missions are materialized, how to go about in how to take on board the expertise of the entire nation. So to make it a success, and it is a major step towards the self-reliance of the nation towards the space weather effect mitigation. In terms of physics, understanding the physics, as well as in terms of applications, which are going to touch the lives of people living on Earth. So at this juncture, I extend my hearty gratitude to the academia and institutes for joining us with their valuable wisdom. Students, research scholars, and many of whom have been with us in today's meeting through social media as well as ISRO's website. Thanks to all of you. Respected session chairs, thank you all for having meticulously driven all the sessions with the sustained intellectual vigor. And special thanks to the Honorable Secretaries of the Ministries of Government of India, namely Ministry of Communication, Defense Space Agency, Ministry of Defense, Ministry of Civil Aviation, Ministry of Power, Earth Sciences, Science and Technology, Electronics and Information Technology, Information and Broadcasting, to have nominated senior officials to share their views on the importance of space-based aeronomy observations to build on the national capability to safeguard the space and ground assets. And thanks to the respective panelists who have been with us throughout this journey of panel discussion and shared their views with ISRO. Thanks to the speakers who have deliberated the important scientific and application aspects of the Aeronomy study from space. Here, I respectfully acknowledge Dr. P. Shikumar, Satish Dhawan Professor, ISRO Headquarters, and former Director of the Space Science Program Office, ISRO Headquarters, who have been the guiding force for this one-day national meet. And directors of several national institutions have participated in today's meet. That's very encouraging. And thanks to all of them for being with us today. At this juncture, I must mention here the relentless support of the Office of Media and Public Relations, as well as the Information Technology teams, OMPR and DISM of ISRO Headquarters, who have played significant roles to make this meeting reach to every citizen through internet. Directors of the ISRO Department of Space Centers have always been enthusiastic and supportive to take this endeavor forward. Also, I must mention here the persistent support we receive from respected Chairman ISRO, Secretary DOS, and Scientific Secretary ISRO, whom we have heard speaking during the inaugural session. My humble regards to Dr. Shikumar once again, without whose guidance this would not have been this much vibrant and focused. I must mention at this juncture the significant roles played by my colleagues of the Science Program Office, ISRO Headquarters, Dr. Girish, Dr. Praveen, Dr. Jagadish, Dr. Maria, Ms. Meghala, Dr. Hassan, Ms. Tejashri to have organized this national meet. Now here at this juncture, I must make special mention of two of my colleagues, Dr. Jagadisha and Dr. Maria, who are sitting with me, who have worked relentlessly to conduct today's meeting, starting from the planning, meticulously planning and taking every pain on them to make it a success today. So kudos to both of them. With so much of good wishes pouring in torrents from multiple corners, with so much of synergy of willpower, I'm sure this endeavor will surely be a success. With these notes, I formally conclude the meeting and thank you very much for being with ISRO Department of Space today and having contributed to the plan of making India's vision for this endeavor a grand success. Jai Hind.
Bye-bye.